ఎవరెవరున్నారు దీంట్లో చూడు.
వెంకటేశ్వర శాస్త్రి పుల్లెల సిఆర్.
Okay. Am I audible, sir? Hello?
Yes, sir, audible, sir.
Actually, there is no session is there only in hall A, sir. That's why, because it is shared. So, sir, talk will be shown. And if you want, you can join in hall A, sir.
Okay, sir. Okay, sir. Sir, just I came over here to confirm the session, sir. Whether
Okay. Because
Okay,
at 20:55, that again it will be starting.
yeah, okay, sir. Okay.
Sir. మీది
Hello. Hello,
Sir.
Are you able to listen me?
Yeah,
Yes, sir.
I'm CR now.
Yes, sir.
Yeah,
Yes, sir.
Fine. Thank you.
Sir, can I have host, sir? Video technologies. Sir, I hope you have received a photograph of Professor A.P. Shastri, sir.
We received, sir. No.
So while reading the biodata of Professor M.P. Shastri, sir, kindly display it, sir.
Yes, sir.
Oh, okay, sir. Okay.
Hello, sir. Hello.
Hello, good morning.
Good morning, sir. Actually, session is still going, sir. Let us wait for 5 minutes, sir.
Okay, fine,
Until
fine, fine.
Rashika Reddy garu
Ah.
join.
You have my number, no?
Yes, sir.
My cell number is there, no? Please call me.
Okay, sir.
Okay, fine. Unmute I am. Okay. Name visible outada? Now I am visible in the. Oh, fine. Thank you.
Professor Rashika Reddy garu, sir, shall we start, sir?
Yes, madam. Okay.
Good morning to all the delegates and participants. I am Lakshmi Himaja, and I would like to take the opportunity to introduce Professor Rashika Reddy garu, former Professor of Statistics, SV University, Tirupati, former Head of the Department and Chairman, BOS of Statistics, former Vice Principal, SVU College of Sciences, SV University, Tirupati, former Coordinator, UGC SAP DRS1, former Coordinator, MSc Statistics and Computer Applications, former Registrar, Dravidian University, Kuppam, former elected President of Indian Society for Probability and Statistics, former elected President of Operational Research and Society of Indian, former Vice President of Society of Reliability Engineering Quality and OM, former Principal Member, Bureau of Indian Standards, former Academic Senate Member, Andhra University, Visakhapatnam. And the awards received by Sir are 6 national and international awards. National Award for Teaching Excellence in Statistics, Indus HMTV Educational Awards by the Indus Foundation, Indo-American Education Summit and Expo 2013, Venus International Faculty Awards, 2016 awarded Lifetime Achievement Award to Professor Reddy garu. And his contributions are introduction of Sudarshan token system for Darshan of Lord in TTD on 4th February 1999 as Honorable Secretary ORSI Tirupati chapter. Thank you, sir. Now I request you to occupy the chair and introduce the speaker.
Thank you. For introducing me. So now, I am happy to introduce about, now I am chairing this session of Professor M.P. Shastri Endowment Lecture. So now I am happy to introduce our Professor M.P. Shastri. Professor M.P. Shastri was the founder professor of Department of Statistics, Venkateswara University. He has received the first PhD in statistics from Andhra University, Visakhapatnam. He served in the Department of Statistics during 1962 to 1984, and he is instrumental in establishing MSc Operation Research and Quality Control course at Kurnool, Andhra Pradesh in 1977, and MA Econometrics in Sri Venkateswara University in the year 1979, and at BA, BSc degree, various degree colleges, he is instrumental in establishing in the Rayalaseema of AP. Several degree colleges were initiated at that time. He has produced more than 10 PhDs and 7 MPhils. He has also published more than 50 research papers in various journals. He has widely traveled to USA, Japan. Under his able guidance, Professor V.L. Narasimham, the founder professor of Acharya Nagarjuna University, Professor L. Kanna Naidu, founder professor of econometrics, obtained their PhD degrees. The Department of Statistics is responsible for setting up the Indian Society for Theory of Probability and Statistics, ISTAPA it's called in the beginning, and later it has become ISPS. Professor M.P. Shastri was the first vice president of ISTAPA and was the first organizing secretary of the first annual convention of ISPS held at Sri Venkateswara University, Tirupati in 1980. On the request of government of AP, the department analyzed the data collected in AP Forest Department. Professor M.P. Shastri was the principal investigator, and he was editor for Telugu Academy books at degree level. He has very closely associated with Professor C.R. Rao for more than 4 decades. Now I am happy to introduce today's speaker, Professor Shilariji Raghavendra Rao. Completed his BSc from Andhra University and MSc Statistics from Usmania University, PhD in Statistics and MTech Computer Science and Engineering from Usmania University. He started his career as a lecturer in statistics at Usmania University in 1984. Since 1986, he is working in the School of Mathematics and Computer Information Sciences, University of Hyderabad. He worked as a dean of the School of Mathematics and Statistics, University of Hyderabad from 18th December 2019 to 20th July 2020. Presently, he is a senior professor in the School of Computer and Information Sciences, University of Hyderabad. His current research interests are simulation and modeling, rough sets, and knowledge discovery. Dr. Rao is a member of Operational Research Society of India, Indian Mathematical Society, International Association of Engineers, AP Society for Mathematical Sciences, ISPS, Society for Higher Energy Materials, International Rough Society. He was the founder secretary of Indian Society for Rough Sets and also a fellow of the Institution of Electronics and Telecommunications Engineers, Society for Sciences, and AP Academy of Sciences. He has received Lifetime Achievement Award Acharya Ratna on 2nd October 2019, 150th birthday of Father of the Nation Mahatma Gandhi by Indian Services. Dr. Rao guided 15 PhDs, 62 MTechs, 8 MPhils, nearly 83 journals, and 122 proceedings papers, and 1 Australian innovation patent to his credit. 5 books in his credit are published. Dr. Rao contributed enormously in the project of national interest. Few to mention are: 1, the mathematical model based on control system for swing out operation for the liquid nitrogen feeding boom for rocket launching pad in Sriharikota. Design optimal driving profile generation for diesel locomotives for Indian Railways consultancy project for MEDA servo control system. mathematical modeling for 6 degree of motion platform for building driver training simulator, mathematical modeling fuel air explosive system for DRDO, optimal design configuration methodologies for aeroscope applications with IIT Bombay for DRDL, modeling and simulation of scene of offense crime number 42 and 43 in 2015 for special investigation. Real-time data study and analysis, Medha Servo Drivers Private Limited 2017 and 18. Adding intelligence to second generation ADGM Gen Technologies Private Limited 2018 to 2019. So now I request Professor Sri Raghavendra Rao Garu to give his talk. It is about it is the Endowment Lecture. So this is up to 10. Now the time is 10:40. Okay, so you take it 35 minutes, 30 minutes, and come. Thank you.
Thank you very much, sir. Good morning, and I am sharing my screen. Is whether my screen is visible? Fine, thank you. Is it full now? Fine. Yeah. After listening, my talk is factored under the Professor MP Sastry Garu, knowing that he has contributed many things to the real world and focused more towards the optimization and best system configuring and other things. I picked up the topic related with the optimization, which is our interest in general. That is, we wanted to find it out. What is the solution in the solution space, which is going to be the optimal? So that optimal in general, maximization, minimization. When you take the function which you wanted to maximize or minimize, we take the derivative and equate to 0. So that means we are interested to find it out zeros of a function. So zeros of a function is known as a zero set. So in real world problems are much more challenging, and the problems I'm skipping the real context where this was needed and other things because it is related with the defense. I am going to put this more in a lighter sense. Suppose there is a foreign body in our body that has to be removed from this. Where it is need to be identified. So we need to do a scanning. So when we wanted to scan it, and we need to identify where the properties of the foreign body which we wanted to locate need to be identified, and it has to be removed totally. That means it need to be identified where all it is distributed. For instance, is something like a cancer cells, different cancer cells distributed over the body. All those things has to be treated. Otherwise, it will not be successful. So that's the reason zero set is very important, and that we need to identify. So with that, we started looking at it. So it is this problem molded as a mathematical problem, especially in applied mathematics. And then it is convert as an optimization problem. And by using some of the evolutionary methods, we addressed the problem and we provided, and that has turned out to be one PhD of the Vijayalakshmi. And in this, my colleague, Professor Raju Vankar, was also collaborator in this. So it is an outcome of a real world requirement in the operations, some operations. Okay. So I wish to, a bit ambitious now because of the time is very short. I wish to speak something about what is a zero set and a link with the roots of a function. And when you say the roots of a function, there are roots can be simple, or roots can be with multiplicity. You have something. So there are classical numerical methods are there. I may touch upon a little bit and I may not go into the detail. Then as a systems engineer, how to look at this problem as a design space problem. Can I look this problem as a design space problem? And can I look this problem as a computing problem, as a search problem? So most of the computing problems, in my view, it is a searching. So can I look this as a search problem? So how we are going to do this searching? By using one of the classical evolutionary method, which is genetic algorithms. So I give a little information about the genetic algorithms. Then how we customize the concepts of genetic algorithms for this purpose, and what type of mathematics, rigorous mathematics was demanded in the process. You are going to see in these three components, and other associated with real analysis and other things you can see. Okay, now f is a function. It can be univariate, it can be multivariate, whatever. So f is a function from this d, set d to r. For real world, because of the real world problems, we are taking the d is a subset of the r to the power of n. Okay, so we are taking that. So we are interested to find it out all x such that fx is equal to 0. That means d is restricted. You have a restriction of the d, and you are taking within that. That is, you can say in future, the region of interest is d, not the whole Rn. Okay, we are interested about the d, and so d d is the 0 set is a subset. So subset, discovery of the subset of it, even if capital D is a finite countable, the discovery of subset is having 2 to the power of order of n. So the problem complexity is non-polynomial. If you look at this, and then as we wish today, the machine learning and several other things are coming, we wish to see, is it possible to make a converge to ZS, that is 0 set, starting from the D, making and removing the unwanted things. Can I remove some portion of unwanted, construct D1? Is it possible to remove further? So can I shrink the design space for converging to DS? This is the philosophy went into the whole work. Okay, so that is something like we played in a childhood. There is a small needle is there, and we'll put a mod and put it that into the thing, and we'll put our hand like this, and other fellow should discover. So something of this childhood games has inspired to go for this. Okay, so roots of a function, simple root. That means if there is only one point x satisfies fx is equal to 0, then that is called as a simple root. If that point satisfies several times, that is, what is required in definition now, x minus alpha, if alpha is a root, if x minus alpha is a factor to the function, and after removing the factor, after removing that, if you take the remainder of f by taking x minus alpha with respect to x minus alpha, alpha should not be a root. Then that is called as a simple root. If remainder of f after taking the x minus alpha, if remainder of x that also happens to be alpha is a root, then it is called as a multiple root. How many times it is going to be called as a multiplicity. So it creates a lot of problems. Multiplicity is going to create a lot of problems. I am not going to those details because recently I constructed a probability density function associated with that. That may be next talk in future. Okay, so we have a classical numerical methods. The classical numerical methods aims at to find it out a point which satisfies that. So and it is assumes there are certain properties. So what we do is, the bisection method assumes that there are endpoints. You have the two positive and one is positive and negative. So there is something is there. That's the reason it says that if your interest is A to B or A to C, and there is a point in between which is satisfying the property, This is confirmed, or this gives the confidence because of the mean value theorems with the assumption that f is smooth. So this is a bisection method, and you have a secant method. You take this and fit a model for that. Fit a model. By using the model, you try to find it out a point which is likely to be closer to the 0. Then you have regular false method, which is a modification of secant method to guarantee that your sequence of D's, D, D1, D2, D3, these things will be containing the root. Whereas secant method may not give the guarantee that you will be landing upon an interval which contains the root. So that's the reason regular false method has come into the picture. So you have variations in this. Now, what we can do, that is all these three methods which are discussed, you start from A, B as interval, you go on constructing A1, B1, which is a subset of this. Like that, you go on, and likely that you will be getting that this difference is going to close to 0. That means you are shrinking the design space, such that the distance between the lower bound and upper bound is negligible. That means you converge it to the point. Now, what information is available? What information we have used? Can I make the process is rich? That led to looking at the derivative of the function. Can I look at the derivative of the function? I have the f. If I look at the derivative of the function, I am going to get some additional knowledge. So if I use that additional knowledge, if I take the derivatives and put it, I can go for Hermite interpolation instead of linear interpolation. I can go for the Hermite interpolation. I can get somewhat better results. Definitely, computational complexities will increase. When you are representing the with better knowledge, and that will become a little bit complex. The representation is becoming complex. Whereas if you take the secant method or regular false method, you are representing by linear systems are well understood. The approximation of the linear system can be handled much easier. When you are approximating by Hermite interpolation and other things, you are representing the system with the knowledge of nonlinear manner. So the process which is getting involved in that is becoming complex. So you are bringing one complexity to the other complexity. How capable your subsystems to handle this, you need to be wise in designing things. Okay, so this way we can proceed, and you can. So there is a mathematics. I am not interested to go into the mathematics at present. There is a Lagrangian interpolation is there. By using the Lagrangian interpolation, we can get the associated theory, and we can establish the rate of convergence and many other things. So you have, and to compare one method with other, how it is converging, rate of convergence is. So you see the interval is big, it is becoming small. So this is a interval is converging. So we need to say what rate it is converging. Then what is the method you have? In one method, you are using simple linear regression, linear model, and the other one you are using the Hermite means polynomial. So your function evaluations are going to be different from one to other. So that's the reason your resource also need to be brought into the picture. So there is another definition is there. Instead of just converging, the efficiency index. Efficiency index is the rate of convergence to the power of 1 by n. So it is some sort of normalization. So I am giving a higher rate of convergence, but if I need to spend a lot of money in calculating subsystem, is waste. So we need to normalize certain things. So efficiency index, that's the reason developing indices are very important when you are developing systems for verification and validation. So what type of indexes we are using for comparing a method A, method B? You see, in your statistical test, you have the method is better than this. That is a speaking about the efficiency, the null hypothesis, acceptance null hypothesis are rejecting. So where the p-value on here is associated with the cost and utilization of resources. So that's the reason we need to look at those aspects also besides the simple testing of hypothesis things. So this is some, I need not to go into the algorithm. So this is how we can do Hermite, and this is a incremental learning. This whole thing goes to the incremental learning. And if you go from the Hermite interpolation from the cubic to 5th order, 7th order, what it becomes in the today's machine learning, it is a regularization. The error, you are able to speak much from taking out from the error. So that is, your estimate will be more precise. That's the reason it is equivalent to regularization in today's scenario. Okay, so if you look at this, the bisection method and other things, you can see this method is slightly better in some sense. I'm not saying it is very great, but the problem once again is very serious. Okay, we have tested for several benchmark functions available in the literature. Okay, so how these things are pictorially working, you can see these are all I'm scanning because of the time. For different functions, x minus e to the power of sin x plus 1. For that function, how these things are mapping. And x 11 into x to the power of 11 minus 1, how these things are happening. This is nx minus 1 by nx into n minus 1 into x. So you can see these functions are, these are some typical functions listed in the thing, how interval, that is design space, is converging. You see, in this case, design space is converging skewly. So that is it. If you represent the design space convergence as a binary tree, it is highly skewed T. So we can look the complexity of the method for a given function can be viewed by looking how the intervals are shrinking, can be looked at it, what path it is observed taking, and by using the associated path of a full binary tree, we can speak something about the complexities of that function. That means if you take a method, I can say the function has this type of complexity. See, it is highly skewed. When it is highly skewed, it takes more iterations. Okay, so these are all some comparisons. Okay, so there are some references and other thing, but the basic problem here, is it sufficient to have one root? And other one is, if the root is, I'm not able to hear you. You have any question, Srinivas? Yeah, you're mute. I'm not able to hear you, Srinivas.
Sir, you have actually given me, I hope you can hear me now, sir.
Yeah, I am able to hear you.
Yeah, you're actually dealing with these Hermite orthogonal polynomials. You also
not
use them for me.
It is, sorry, it is not orthogonal, interpolating functions.
Okay.
It is not orthogonal.
Okay.
Why
you are not
Hermite interpolation
orthogonal polynomial, sir?
No, it is not an orthogonal polynomial. It is a Hermite interpolation. If you are interested, you can see more detailed information from the root. That is a handbook of mathematical formulas and other things by Ambrovich.
Yes, you have actually helped me with respect to image processing through Varsha Dogram. We have reconstructed the signal also.
That is a decomposition. Orthogonal polynomials are useful for the decomposition, but here it is a knowledge
only
representation.
Interpolation.
No, interpolation is knowledge representation.
Okay, but then how you are heading for the zero crossing?
That's it. See that you need to have. You wanted that. I'll come to that. You see. You see that instead of straight line, that polynomial, 50th degree polynomial will be there. Blue line will be 50th degree polynomial.
Okay.
So when it is a 50th degree polynomial, it can cross more than one place.
Okay.
So when it is crossing more than one, it is not mathematical now. It is not deterministic. So there is a vagueness. Statistics plays a very important role and helpful for addressing that vagueness. So I can pick up all the 3 points. If there are 3 points, I can pick up all the 3 points which are satisfying, or I can come up a zeroing to one only by using some additional rules.
Okay. Okay. That was the doubt, sir.
Yeah. So it is possible. So in this section, what we have done is computing only one root. We started with a classical approach only. So that is the problem. All these methods which are having classical methods are one root. and we, I think we factor it. If you want another route, we factor it out and compute the next route. So most of the algorithms available in the present packages are of that nature. Okay. Now what we discovered, it will do parallelly and in single go all the routes.
Okay.
Now why I have picked up is routes, the fx is equal to f dash x is equal to 0 is essential for optimization. So to when it is factored as under gigantic professor of the diversified, more focused to the serving to the systems with optimization, I felt we should speak something of that nature. Okay, so what is the limitation? It cannot find it out all routes of the in D. It sinks and it will be. So is it possible to have a design space shrinking process, removing unwanted region? Now what we did, whether it is we don't know whether we have, when shrink this, we don't know whether we have missed the wanted route. When you do off, then what it may be also having a route. You have taken this portion. So there is a possibility of missing the true positives. Okay, the positive. So that's the reason this method will not be helpful. So if somebody starts with this philosophy will not work. One should see the whole thing. So what is the philosophy? What type of knowledge we need to capture? What knowledge need to be converted as a technology for the purpose of computing? So as rightly you questioned, how zero crossings are going to be captured. So that was the fundamental principle we have. Now we are interested, find it out. We are interested to find it out a curve, which is curve crossing the zero. We wanted to find it out a delta neighborhood of the crossing. So we wanted to pick up a small interval such that it encapsulates that zero crossing. So when you say zero crossing, what it says, that before zero, it should be either positive or negative. After zero, it should be negative or positive. So sign should be different. But this property is not true when the root is even multiplicity. If the root is having a new even multiplicity, it just touch and go.
Okay.
So it cannot cross, it will stay there. That's the beauty, is that it stay. So zero crossing is visiting state in stochastic processes. And when multiplicity is there, it is occupancy in stochastic processes. How long the state is occupied. See, it is what happens in stochastic processes. It's reached to the state and bounce back. That means it going to some other. That is positive, zero, negative. Negative, positive, zero. So it is muse. So state transition will be there. It will not occur. But in multiplicity is there. It starts from positive, 0, 0, 0, 0, and positive, negative. Or it can go one, positive, 0, 0, positive. So this complexity will come. So we need to look at the occupancy time. If somebody wants to look at, I think there was some works, if I remember, when we were MSc students, Professor Shankara Narayana, I think, from Annamalai University, gave a talk of zeros of a stochastic processes. He took the stochastic process and he was discussing something. I vaguely remember his talk when I was a student. I attended that when he gave a talk at Usman University. Okay, so this is so the complexity. Now we need to develop algorithm, and integrand may be complex. So the acquiring the knowledge of the integrand is very tough. So if the function is, sorry, not the function, if the function is given, it is mathematically you may be said, but in real world, think of the scanning the body. I wanted to remove some lumps in the body which are likely to be cancerous. So I need to identify all those lumps in the body. How I am going to zero down all these lumps? So there is no function. There is no function. Still, I must be in a position to succeed it. But mathematically, scientifically, there is unknown function is there. So can we develop a methodology such that to address something of that? But we need to give a proof of concept after giving that. So what we have given a proof of concept, we have taken classical functions and demonstrated, but this method is not just for well described functions. It can be empirical, it can be experimental. Okay, there was something there are people are keeping their gold biscuits in wall. They constructed it. Now, how to identify the gold biscuits? Which portion of the wall I need to dig? Similarly, there is a choking in the drainage. Will you dig the each and every part of the drainage? So we need to identify where I need to explore that the choking will be cleared. So for that type of problems, this method will work. I don't have function expression for that. Is it clear? Okay, so we have now that is there is take the drainage. There is my drainage water is overflowing from this point to this point. So when I have this point to this point is overflowing, this is my design space. Now where I need to clear the choking, all those points I need to identify. So I need to shrink this such that all these points are included in my zero set, superset of the zero set. That is the idea of this whole work. So I am taking you people for the simple genetic algorithms. What is genetic algorithm? Is evolutionary algorithm. You take some population from the sample population, and you do certain operations on that. When you are doing operations, we evaluate each and every picked up object of the population, and from that you select, do the crossover, mutation, and selection. Generate, may say you have a offspring from this. So you start from the population, start this and have a offspring and call this as a new population. You go on doing this such that your requirements are met. It is expected to do it because Darwin principle says that fittest will survive. So that's the reason this. So these operations are mathematically modeled, called as a crossover operation, mutation operation, selection operations, something of this sort are there. And coming to the evaluation, they coined some term called as a fitness. So there are few terminologies need to be understood when we are going to adopt the genetic algorithms. So that we call as a parameters and a representation. So what is the solution? We need to represent the solution. The solutions are represented in genetic algorithms by chromosome, a string. That string length, the length of the chromosome is required. So how you are going to represent? At present, I am confined to fixed representation system. Can be, now people have come up with varying length representations also. At present, I don't want to confuse people with that. Let me take, I'm representing only by the. See, all of us received roll number as a fixed length in throughout our career. Have you received anyone? Your classmate will be having 5-digit roll number, and you are having 10-digit roll number. All are having the postal code as a 6-digit now. Each and every place in India has a 6 digits only. So that is a fixed length representation. It has its own advantage. Varying is also there, which has other advantages and disadvantages. Now, how much population you are taking? That is n, population size. Then crossover, how you are doing the crossover? It is with a chance phenomena. So the probability of crossover, probability of mutation. These are the things which are parameters. And some other parameters associated with the algorithm is how to stop my iterations, when to stop. So the number of iterations can be fixed, or I can say once I got the certain accuracy, I'll stop. So a termination criteria are fixed number of, that is depending on the budget and other things. I can say I cannot do more than 2 iterations, 3 iterations because of budget. And to conclude, I have received a thing, R selection. I need to have the fitness function. Okay, these are the things are required. So I'm not spending more time on this because of the sparsity of the time. So now I'm straight away going to our contribution, which we call as an innovative genetic algorithm. So it has 3 steps. These are sequential. These are not, it cannot be parallelized. First step is pre-processing step, which is a genetic algorithm. Second is a intermediate thing, which is also genetic algorithm. Third one is, it is not genetic algorithm. It is an exploitation of the genetic algorithm results. See, this is the the third is a high beauty. The beauty is very much because what is doing in the genetic algorithm, how we can exploit further the genetic algorithm is coming into the third. So I will try to explain a little bit more on that. Now I take a case, 3x cubed, some function is there. If it is, so if you zoom the -2 to 2 and with the scale y, you can see there are 2 more roots are there. So it has many roots between -10 to 10. How to get all these roots? So -2 to 10, -10 to 10. If you take a sampling rate, 0.001 is the rate distance between one point to other. You see how many sample points you need to evaluate to understand this signal. It is a, so if I don't have that much, or imagine I am doing certain study with associated with the enemy. Will they allow me to collect this much data? It's impossible, is it not? I may be able to collect some data which I can operate my things within no time. That means I must just go fly and come back. That means I can get only handful of readings. Reasonable. So with that, is it possible to build the whole information system? I may be able to do this several times also. That is another thing. So this. So what the parameters are used in the pre-processing is a N1, K1, LC, PC, MC. Those are things, and we have taken NC. Okay, we have taken. Oh God, it is coming all the way. Fine. We have taken 12. N1 is taken 12. There is no hard and fast rule. You can take more than 12. There is no problem. It can be 20. It can be 30. And K1 we have taken 10 for demonstrating all the benchmark functions. And please remember, LC is 2. Chromosome length is 2. What do you mean by length is 2? I have taken A and B. In between, I have taken 2 points. Now, I am going to say A2 X1 is the function has a different sign. X1 to X2 is the function is having different sign. X1 to A, B, is it having different sign? The number of different signs is my fitness function. But we started only with the LC is 2. It is the simplest. So in between I'm so by the why we have taken 2? People can ask the question, why you have taken 2? Why not 1? Why not only 1 point? But if I take 1 point, this will be likely to be 50-50. So it will not give you the comparison. It will not reduce the interval much. The golden ratio says that if you divide the interval into 3 parts and try to take 1 part is 1 out of 3, which is a complement is 2 out of 3 you are rejecting. So any optimization algorithms which is around the golden ratio performs better. See, the common sense which is working here is influenced by golden ratio. So that gave. So we did this, and this has done. By doing this, this has iterative. The whole learning process went into the pre-processing. What it learned, what should be the LC? It is a very crucial thing. What should be my LC?
Sir, last 5 minutes, sir.
Yeah.
Last 5 minutes.
Yeah, I'll close it. There is no problem. Okay, this the LC is important. So we have taken, and the LC which is recommended by the above algorithm went into the second genetic algorithms, and that used, and we have done only 2 iterations. We have taken only 2 iterations, recommended 2 iterations we got. So after getting the things, there are 12 chromosomes are there at the end of the second genetic algorithms. So what we did, we developed the fusion of the 12 genetic chromosomes. So fusion of the genetic 12 chromosomes appropriately gave us a sharper intervals. So that reduced design space drastically. It went, the reduction of this reduction order is 98% also. So that much achievement we got in this process. So algorithm, I am not, so just pictorially I will try to explain to you because of the time. You have taken only 2 points. So this chromosome is not giving me any positive interval, favorable interval. Whereas if you take, there are zeros or roots in this. So in this case, I have something. So I have, so by taking the fusion of this LC, fusion of the first interval, I am getting new chromosome of different length, and I am having some zeros and some sign changes. So I can have more intervals with, so my fitness value of this fused chromosome will be then, this length is not controlled by anyone. It is controlled by the function nature itself. And this is induced by the randomness inherited in the first iteration itself. Because of that, this is not possible to predict in advance. So there is some security aspects are also built in indirectly. So if you start with this, you have LC is this, maximum is this. So by what we are doing, what we recommended, if the revised fitness value is more 1.5 times of the maximum of the fitness value of the earlier iteration, go for twice of the length. You go for the twice of the refinement. So by using this, we converged for a given function 128 or something as the chromosome length for the second iteration. So it is a learning algorithm. First one is a learning algorithm, which is a that is hyperparameter of a genetic algorithm is learned by using genetic algorithm itself. That is the beauty of this whole contribution. Fine. So you see how dense, how you are in a position to get better knowledge about the roots, zeros. So if you do this and you have a fusion refinement, you see your pockets are becoming narrow. Your packets are becoming narrow. So okay, so you see roots are available only in the small intervals. So this work at the 63rd iteration, you will get there. So a lot of unwanted region is filtered. Lot of them. So it is very important in some defense activities. I don't want to destroy my resources. I will destroy the only regions which are need to be done. That means pinpoint operations. Pinpoint operations can be recommended. So there are several problems came with a simple root now. Yeah, please. Unmute yourself.
Sir, in the earlier slide, which is predominantly red, I'm talking about the last bar.
Yeah.
There are some black spots.
The change is coming. So the sign change, positive, negative. One, I think black is positive and red is maybe negative. Function.
Okay.
So wherever the changes are there, you are having the neighborhood. So neighborhood is shrinking.
Do you run into a situation where the situation is chaotic in the sense you cannot say whether it is positive, negative, and the like?
No, that is not possible. Precisely that happens if it is a multiplicity is there.
Okay.
So that's the reason. The other why the analysis is coming into the picture is that it is simply evolution algorithm. Why analysis has come into the picture is that. Okay, so this is what we have. Fine. So you have these things. You can see when this multiplicity is there, you have a problem. So you need to. So for that purpose, we introduced a concept called as a. There is a Tro has defined something. Gx is equal to fx by f dash x, which this will be always will have a simple roots. But this transformation brought a lot of nuisance parameters. Okay, this created problem. That's the reason we have given a much more generalization. And for this purpose, we developed a lot of algorithms. And this, I am not going to that. So the transfer function is like this. You see that spikes will come into the picture. These spikes will create a lot of problems when you do a signal processing things. So these are the transformer, and it is faster. Okay. that needed labeling. Whether are you getting the real root or pseudo root? So labeling algorithm we developed. For that purpose, we introduced the concepts, different concepts which are there, and their labeling algorithms and convergence divergence, which is something to the related with the Dedekind cut analyses. Went into it. You see, this will not converge. Left limit and right limit will not be same. Okay, then sequentially it is developed. The interval hauling is done in sequentially. So A and B start with come to the A new and B new. So finally we got this. For this function, we have 37 roots we got. I need to go to the design space reduction. How to measure the design space reduction? How to measure the accuracy? We have given the appropriate metrics, and these are the things. I wish to come to the final conclude something. Yeah, this is the function which is available in the encyclopedia of optimization, and I am happy or proud to say this reported 21 roots. Okay, it is reported 30 roots. Reference 21. It reported 30 roots, but we could discover 31st root. Suppose if it is a cancer, and by using the methods given in the encyclopedia, you are able to clear 30 spots. 31 spot is left. That person will die because of the cancer. That element is left out. So this is the important observation from our side on the benchmark functions. So 31st root is there at the bottom. Okay, as the time is over, I stop here. I cannot. Many things are there to speak, but I'm not going to get into it. How we can see two variables. There are challenges are there for two variables, multivariables. I'll stop. Thank you very much, sir. Mike, you can take over.
Yeah. Thank you, sir. Thank you, Professor Raghavendra Rao Garu, for your nice presentation. So it is very inspiring for the young generation, youngsters. So can any questions from audience? If no questions, because time is up, so that if you have anything, please contact with Raghavendra Rao, his mail ID or something. So thank you. Thank you. Yeah. Yes, Jai Shri, madam, please. Yeah.
Thank you, Professor Rashekar Reddy Garu, for chairing the session.
Yeah, thank you.
I am leaving the meeting. How to stop? How to stop? Next step. Stop the meeting.
Professor Neha Garg, ma'am, will wait for 2 minutes, ma'am. We'll start the session.
Okay, ma'am.
Neha, you are muted.
Good morning, sir. Good morning.
Good morning, good morning, good morning. I think, yeah. So the first speaker was not there. There are 2 speakers in your session, right?
Yes, ma'am. Yes, sir. I think first speaker is not available.
Okay, okay, fine. So then we can speak. You can speak for more time.
Yeah.
This is the same paper you are presenting here, the one you have submitted for ISPS, I think, no?
No, that is different.
Some calibration is there.
Yeah, that is also in calibration. Today I am considering adaptive cluster sampling, and the paper which I have submitted is different one.
Professor Anup Chaturvedi is the chairperson, no? About this session.
In the schedule it says that Professor Anup Chaturvedi is the chairperson, and there are two speakers. I think one of them is not coming.
Yeah.
Good morning, sir.
Good morning.
Good morning. Good morning.
Sorry, there is a small confusion over there. Let me take a privilege to introduce Dr. Neha Garge, madam. Madam is working as assistant professor in Indira Gandhi National Open University, New Delhi. And madam received UGC CSIR NET JRF and also UGC CSIR SRF. Madam, areas of interest in research are estimation and sampling techniques, statistical inference, and biostatistics. And madam's research contributions are, madam published more than 20 research articles and presented around 9 research papers. And madam has written number of chapters in the book 30. And madam is also a life member in the Indian Society for Probability and Statistics and Indian Society of Agriculture Statistics. And also madam is a member of Society of Statistics, Computer and Computer Applications. I'm very happy to see you here, madam. Please start your lecture, and thank you for being here, ma'am. Thank you, ma'am.
Thank you so much, ma'am. Let me just share my screen.
Thank you.
A very good morning to everyone. First of all, I would like to thank the organizers of this conference, Indian Society for Probability and Statistics, Department of Statistics, Mania University, Hyderabad, and the respected chairperson of this session. The topic of today's research is calibration estimation of finite population mean in adaptive cluster sampling, which is a part of research with my scholar, Ms. Meenakshi. In this talk, we will discuss about just a minute. So in this talk, I will just discuss about adaptive cluster sampling, what is adaptive cluster sampling, and how we can select adaptive cluster sampling, adaptive cluster sample, then the calibration approach to estimate the population mean in adaptive cluster sample, and the proposed calibration estimators and related simulation studies. So let me first just discuss about the adaptive cluster sampling. What is adaptive cluster sampling? So Thompson in 1990 introduced adaptive cluster sampling as an efficient sampling scheme in case of rare, hidden, and cluster population, such as some endangered species of animals, birds, trees, fishes, some contagious disease, like in case of COVID as well. Some of the researchers have used adaptive cluster sampling, and for some rare and precious plants, minerals, natural resources, and mud volcano cases, etc. So the procedure of selecting an adaptive cluster sample begins by taking an initial sample of size n. By using any traditional sampling design, such as simple random sampling without replacement, with or without replacement, systematic sampling, stratified sampling, two-stage, etc. So before selecting adaptive cluster sample, we define some pre-specified condition. This pre-specified condition is our condition of interest and depends upon the research interest. And if any of the initially selected sampling unit satisfy this pre-specified condition, then we select their neighborhood units. Neighborhood unit means the units which are especially surrounding, means in 4 direction, like north, south, east, or west, or we can simply say up, down, left, and right. So if these initial selected units satisfy these pre-specified condition, then we include its all neighborhood units in the sample. And if these adaptively added neighborhood units also satisfy the pre-specified condition, so we also include their neighborhood in the sample. So this procedure will continue till no more units are available which are satisfying this condition. So for clearly understand the selection process of adaptive cluster sampling, I have just considered a small data here. This is a part of blue-winged teal population, which is given in Smith et al. In 1995 paper. So these are the comprehensive count of teals, blue-winged teals. And this study region is divided into 8 by 8 grid, 64 quadrants. So as discussed, first of all, we should decide a condition of interest. Suppose we are saying this condition of interest is C. So we can choose any value of C based on our study. We can select all values yi which are greater than equal to 0, or yi greater than equal to 5, greater than 10, etc. So if we are selecting an initial sample of size small n, say 4. So these are the units which are marked star. Suppose they are our initially selected sample. So we will just check the units which satisfy our pre-specified condition. If we consider the pre-specified condition yi greater than 0. So we have marked units which satisfy this condition C by this yellow color. So now we look at its neighborhood unit. Neighborhood units means we will just look at the north, south, east, and west. If these units also satisfy this pre-specified condition, then we include these units in our sample. Okay. So these all units are satisfying the pre-specified condition, which is yi greater than 0. So we included these units in the sample. Now we again look for its neighborhood units. So we again included these units which are satisfying the pre-specified condition. And this procedure will continue till there is no neighboring unit available which are satisfying the pre-specified condition C, which is yi is greater than 0. So the unit shown in the yellow color is known as network, and green colored units are known as edge unit. And together, network and edge units make a cluster. Now, if our study area is divided into different strata, then adaptive cluster sampling applied to these stratified population is known as stratified adaptive cluster sampling. So stratified adaptive cluster sampling is discussed by first Thompson in 1991. So suppose UH is our finite population of size NH in the hth stratum, and we can define YHIJ as a jth observation on the study variable for the ith network of the jth stratum. In the same way, we can define XHIJ as a jth observation on the auxiliary variable for the ith network in the hth stratum. And we can define the network, ith network, YAHI, ith network that include the initial unit I, which we have considered in the step 1 in the hth stratum, and NH is the initial sample size in the hth stratum, and MHI will be the number of unit in the ith network of the hth stratum, and we define average number of values of the steady variable in the ith network of the hth stratum by WYHI. And in the same way, we can define the average values corresponding to auxiliary variable in ith network of the hth stratum by WXHI. And we compute the average of the steady variable and auxiliary variable in the hth stratum by W bar Y bar H and W bar XH. So this is some existing estimators which we have considered in this study. This is the usual combined ratio estimator in case of stratified sampling. And this is the estimator given by Kadila and Ching in 2005. And Thomson in 1991 considered the usual stratified estimator in case of adaptive cluster sampling scheme. And Driver and Chaos in 2007 considered the combined ratio type estimator in adaptive cluster sampling. And Chattiman in 2010 considered the thus modify the estimator given by the Kadilar and Chingi. So before going further, let me just discuss about the calibration approach. So what is this calibration approach? These days, lots of research is going on this calibration approach for estimating the different population parameter in sample survey. So in sample survey, we can define this calibration approach in terms of an optimization problem, considering calibration function, or we can call them the calibration constraint, which utilize some additional auxiliary information which are available on the auxiliary variable. So the calibration approach is a methodology for finding alternative sampling weights, and we assume that these weights are close as possible to some predetermined initial weights, which satisfying the calibration constant. So these calibration constant use auxiliary variable for which we assume that population corresponding population parameters are known. So we can define this calibration approach as a method for improving the estimators for different parameters under different sampling schemes. So Devlin and Sandal in 1992 first introduced this calibration approach, which actually formed the basis for most of the research which are going on the calibration approach. So here pi I is a inclusion probability of the ith unit to be included in the sample, and di is a design weight, or sometimes we call it as a base weight, which are equal to the inverse of the inclusion probability. So corresponding to this Harvey's and Thompson estimator, Devlin and Sandal suggested this calibration approach, calibration estimators for estimating the population total. For this, Devlin and Sandal use this chi-square type distance function and the calibration constant, which are based on the weight of, based on the total of the auxiliary information. And this is a, so we can obtain this calibrated weight Wi, which minimizes chi-square function subject to this calibration constant. So this is a calibrated weight obtained by optimizing this calibration, this chi-square type distance function. So this gives a generalized regression type estimator for population total. So to evaluate the closeness between these calibrated weight and design weight, some form of measure is required. So Devil and Sandal in 1992 also promoted the choice of different kinds of distance functions like I-square type distance function, Hellinger minimum entropy, modify minimum entropy type distance functions. So now let's move ahead to our proposed calibration estimators in case of stratified adaptive cluster sampling scheme. So in this study, we have considered 3 different forms of calibration estimators. In case of adaptive cluster stratified sampling, this is the first form for calibration estimator where omega mh is a calibration weight. And this is a chi-square type distance function. And this is a constant, calibration constant. So in the first form, we have just considered the mean of the auxiliary variable. This is a mean corresponding to sample values, and this is the mean corresponding to population values. In the second form, we consider the calibration constant by considering logarithmic function of the mean of the auxiliary variable. And in third form, we have considered the exponential function of this mean form. So now we can define the Lagrangian function, which minimizes chi-square type distance function by considering the calibration constant. Here we have considered the 3 form of this calibration constant. So in this slide, this lambda is a Lagrangian multiplier, and we will first obtain the value of lambda. So we will just differentiate this Lagrangian function with respect to calibrated weight omega h, and then equate to the 0, and we will just substitute the value of this lambda in our calibration constant equation, and by solving this equation you can obtain the calibrated weight omega h. So these are calibrated weights for the 3 forms of suggested calibration estimators. So in this way, we can, after substituting the value of calibrated weight, we can obtain the 3 forms of calibrated estimator. This is the first form of estimator, and this is the second form, and this is the third form of the estimator. We have also derived the expression for bias and mean square error up to 2nd degree of approximation. And for the simulation study, we have considered the data given in Chettiman 2010 papers, in which the population size is of 400, and there are 4 strata of size of 100 units. They are divided into 20 by 5 of grid. So, and we have generated different samples by using R software. We have computed absolute bias and empirical percentage relative root mean square error by considering 5,000, 10,000, and 15,000 repeated samples. So this is a computed value of absolute bias by considering different sample sizes for n is equal to 16, 20, 24, and 28, and by considering 3 set of replications, 5,000, 10,000, and 15,000. In the same way, we computed percentage relative root mean square error for different sample sizes and by varying the number of repetitions. And this is a percentage relative efficiency. So by this table, it is clear that the proposed estimators is having less bias and percentage root mean square error. So the relative efficiency corresponding to suggested estimator C1, CM, CL, CM, and CE are more than the other existing estimators. These are the references which we have followed for this study. That is all. Thank you.
Who is there? Nobody there. Jayashree, any questions? Because any questions from audience? Thank you, Neha, for your nice presentation. I think because the Anup Chaturvedi I didn't come, so okay. Anyhow, so thank you, Dr. Neha, for your again very interesting topic on the subject of this sampling. Okay, thank you.
Thank you so much, sir. Thank you.
Madam, 1 minute.
Yeah.
Hello.
Yes, ma'am.
Thank you, madam, for your wonderful talk. Now, any questions from the audience? Hello. Any questions from the audience? If no, then I request Neha, madam, to chair a session for the contributory papers, madam.
Okay. Thank you so much, ma'am. Thank you.
Thank you, ma'am. Thank you for presenting.
Thank you.
Thank you. But madam,
Thank you so much. Now I welcome everyone to this contributory paper session. In this session,
now I request Dr. Neha from Indira Gandhi National Open University. I request to chair and start the contributory paper sessions. As for actually they are having that time is from 12 o'clock onwards, so you can give them more time. So it is flexible to you.
yeah.
And whatever you check it once, madam, how many members are already ready are there. If there are any members are not ready, we can give the chance for.
Sure, sir.
Okay, madam.
Yeah. Okay. Thank you so much, sir. Thank you. Yeah.
Occupy the chair and please conduct.
Yeah. Okay, sir. Thank you.
Thank you, madam.
Thank you.
Hello.
So I once again welcome everyone to this contributory paper session. In this session, we will have total 7 presentations starting from serial number 115 to 124. Just let me check who is present from serial number 115 to 124.
All are going to present now.
So kindly let me know who is present from.
Ma'am, I'm Abhijit Vishwakarma. My serial number is 115.
115. Okay.
Yes.
Okay. So welcome, Mr. Abhijit Vishwakarma. So we'll start with your presentation. So Mr. Vishwakarma will talk about the generalized class of difference and regression type estimators in double sampling for the estimation of finite population variance.
Yes, ma'am.
So over to you, Mr. Vishwakarma. You can start your presentation.
Thank you, ma'am. Ma'am, is it visible? My PPT?
Yes, it is visible.
So good afternoon, everyone. Warm greetings to you all. I welcome you to. Am I audible? Hello.
Make it full screen, sir.
Okay.
Yes, please continue.
Ma'am, this is full screen.
No, sir.
Is it visible?
No, this is not a full screen.
Slideshow, sir. Select slideshow.
Just click on the slideshow.
Sir, upstairs in menu bar, slideshow is there.
So
Just press F5.
is it visible?
Yeah, it's okay. It's okay. We can see it. It is clear. You can continue.
Ma'am, is it visible?
Slides are visible, but not in full screen. You can continue. No issue.
Okay, ma'am. So good morning, everyone. Warm greetings to you all. I welcome you to International Conference on Statistics and Data Science. I am Abhijit Vishwakarma, research scholar from Department of Statistics, University of Lucknow. I am presenting my paper entitled as Generalized Class of Difference and Deviation Type of Estimators in Double Sampling for Estimation of Finite Population Variance. And the following work is done under the supervision of Dr. S.A.H. Rizvi from Department of Statistics, Shia PG College, Lucknow. I would be covering my presentation under the following outlines. These are introduction, followed by a review of literature, proposed estimator, numerical example, conclusion, and will end with the references. So coming to the introduction, as we all know in sampling theory, the efficiency of the estimator can be increased by using auxiliary information, which is highly correlated with the variable of our interest. In this context, a lot of work has been done by various authors like Kushwaha Singh, Banarsi et al., Singh and Singh, etc. These authors have discussed the problem of estimation using the mean, using the information on auxiliary variable in the context of systematic sampling. Given the sample observation.
Yeah, just a minute. Abhijit, I think your slides are stuck. Just I exit the slideshow. It happens sometime. Just exit the slideshow and just click on the left panel. Yeah. Now it is fine. Yeah.
So various authors like Kushwaha, in this context, a lot of work has been done by various authors like Kushwaha Singh, Banarsi et al., etc. So given the sample observation, our problem is how to choose a function of sample values, or we can simply say that estimator, so that we can estimate efficient result about the variable of our interest with maximum accuracy. So considering y as a study variable and capital X as an auxiliary variable, which is highly correlated to our study variable. So certain situation arises when the population mean of the auxiliary variable is not known. So what we do is we adopt a sampling technique known as double sampling, where we first draw a first phase sample is used to estimate the mean of the auxiliary variable, and the second phase units are used to estimate the characteristic under study. So in this work, we have proposed a difference and regression type of estimator in the double sampling to estimate a finite population variance. Further, the bias and the mean of the MSE of the proposed estimator are calculated and are studied. Also, the optimum estimator with the optimum estimated value is also investigated, and a comparative study has been carried out. An empirical study has also been made to support our findings. Now, coming to literature of review, prior information has been extensively used by many authors in improved estimation procedure. Prior information in the form of coefficient of variation has been used by various authors like those are mentioned like Searle, Koopmans, LH, Owen, DVW, Rosenbatter, etc.
Sir, this sir. Have to press arrow keys, sir. Then it will go to next file.
Sorry, plus? What should I press?
Arrow, down arrow.
Okay. So prior information in the form of coefficient of variation has been used by various authors like Searle, Koopman, LH, Owen Rosenbelt, J.J. Khan, etc.
Just a minute, Abhijit, I think your slides has stuck again. So just change your slide by clicking on the left panel, I think. It's happened sometime.
Is it visible, ma'am?
Yeah, it's showing only third slide. You are on which slide?
Ma'am, I am on fourth slide.
Just click on the fourth slide in left panel.
Which is, sir,
Yes, ma'am.
down button is there, sir, round button. Down there.
Ma'am, I don't understand why this is happening.
So have you exited from the slideshow mode?
Uh,
No, ma'am, he is in PPT mode only.
In PPT mode, sometime it's happened. So just exit from the slide presentation mode. Okay.
okay, ma'am. I've exited.
Exit. Yeah. And yeah, now it's fine. So don't go in the presentation mode. It happens sometime. Just change the slide by clicking on the left panel.
Okay. So is it visible now?
Yeah, now it is visible.
Okay. So I was on literature review. Yes, ma'am. So coming to literature review, prior information has been extensively used by many authors in improved sampling estimation procedure. Prior information in the form of coefficient of variation has been used by various authors like Searle, Roser, Koopman, L.H. Owen, Rosenbelt, etc. Now, prior information in the form of known parameters like mean variance has been used by various authors for developing ratio type and product type difference type, difference and regression type estimators. In this context, various estimation procedures and the properties are studied by Robson, Motis, Singh, Srivastava, etc. Now coming to proposed estimator, consider capital N be the population size, where capital Y the study variable of our interest, capital X be the auxiliary variable which is highly correlated to our study variable, and capital small n dash the large primary first phase sample from the capital N, which is used to estimate the population mean of the auxiliary variable, and small n with the second phase sample which is used to estimate our study variable. Further, we have assumed that small y bar and small x bar be the sample means, and x bar dash the sample mean of first phase sample, and theta cap is a function of yi square, which is an unbiased estimate of theta. So the proposed estimator of the finite population variance in double sampling is proposed as sigma GD cap square is equal to G y bar x bar dash theta cap. That is, the proposed estimator is a generalized estimator and is a function of sample mean of the study variable y bar, sample mean of the auxiliary variable x bar, sample mean of the first phase auxiliary variable x bar dash, and theta cap, where this function satisfy the validity conditions of Taylor expansion and have first, second, and third order partial derivative bounded at point y bar, x bar, and theta. These conditions are at the function at this point P attains the population value of parameter sigma y square. The first order partial derivative are given there with respect to y bar, x bar dash, and theta cap, while the second order partial derivatives are mentioned there. These derivatives we have calculated. Now we have calculated the bias and mean square error of the proposed estimator. Expanding the proposed estimator by Taylor series expansion under the first order approximation, the bias and MSE of the proposed estimator are calculated, which is mentioned below. The bias, this is the bias of the proposed estimator, and this is the MSE of the proposed estimator. Here we can see this term is nothing but the MSE of the usual conventional estimator. So our estimator consists of two terms. The first term consists of the MSE or the usual consistent estimator, and second function, we will talk about it later. So we have calculated the optimum estimated optimum value. Here we can see from the previous slide that this MSE of GD cap square is a function which consists of G1. So what we did in the next slide, we minimized this function of MSE sigma GD cap square, and we get the optimum value of G1 as G1 star is equal to minus mu21 upon mu naught 2. So the minimum MSE of our proposed estimator is MSE of SY square and minus 1 upon n dash mu21 square upon mu naught 2. Practically, in many situations arises that this value of G1 star is not always known. So what we do is we replace the unknown parameters involved by their unbalanced consistent estimators, leading to G1 star. This one is G1 star, which is the function of unbalanced consistent estimators for estimating these population parameters mu21 and mu naught 2, where mu21 and mu naught 2 are the unbalanced consistent estimator of mu21 and mu naught 2 respectively. So replacing the optimum functional value by its estimated optimum value G cap, we get the following estimator: sigma G DE is equal to G star y bar x bar dash theta cap G star. So now this new function is a function consists of a new term G cap square, which is a function of G1 star. Now the mean square of the estimator based on optimum value has been calculated, and what we found that the mean square of the estimated optimum estimator comes out to be same as the mean square error of our proposed estimator. So the above equation shows that the MSE of GD cap square is equal to MSE of GDE cap square, that is MSE of the optimum value of the proposed estimator. And further, we can see that from this equation that MSE of GD cap E square is less than the MSE of conventional estimator, which suggests that our proposed estimator is efficient than the conventional estimator in the sense of having lesser mean square. Now coming to numerical example, for empirical study to support our findings, data from Cochrane 1977 has been taken, which dealt with paralytic polio cases. Here, our study variable Y is placebo cases, and our auxiliary variable is paralytic polio cases, which is not inoculated group. Based on the given data, computations has been made, and we calculated the following result. That is, for sample size of these are the data that we have calculated. For sample size of n is equal to 34, we have calculated the mean square error of conventional estimator, that is 21.61, and the mean square error of the proposed estimator, which is equal to the mean square error of the optimum value of the proposed estimator, which is calculated as 13.422. This shows that the mean square error of the proposed estimator is less than the mean square error of the consistent estimator, conventional estimator. Also, the percentage relative efficiency is also calculated, and the PRE of percentage relative efficiency of proposed estimator comes out to be 160.9953, which shows our proposed estimator sigma G cap square GD and sigma GDE cap square are more efficient with high percentage relative efficiency over the conventional estimator. Now coming to conclusion, the following conclusion has been made. Number one, the conventional estimator SY square of the population variance is SY square 1 upon n mu2 naught square beta 2 minus 1, while the proposed estimator GD cap square has its minimum mean square error as mu2 naught square of beta 2 y minus 1 1 upon n minus 1 upon n dash mu2 naught square upon 1. This first term is MSE of this conventional estimator, and it got subtracted from my mu2 square upon mu naught time. So the MSE become less. So now our second conclusion is the MSE of sigma GD cap square and MSE of GD cap square is less than MSE of SY square. which shows that the proposed estimator sigma GD cap square and GDE cap square are more efficient as a conventional estimator of the S phi square population value. Further, a PRE has been calculated, which is as 160.9973, which indicates that the proposed estimator are more efficient with high PRE values. These are the references which I've considered for my paperwork. Thank you. That's all.
Any question from the participants? Any questions or any observation? Okay, so Abhijit, I just have a small query, not a question. So
Yes,
you have just consider optimum value for your G1, okay, and consider
Yes,
G in your function.
yes, ma'am.
Have you tried for another value of G1?
Ma'am, we are considering this in our next paper.
Okay.
Yes, ma'am.
And for this numerical illustration, you have compared with the MAC of S by square only. So which is without auxiliary information, right?
Which without no, ma'am, which consists of an auxiliary variable S phi square, which is
Okay.
in the form of a auxiliary variable.
So what is the form of this S by square from which you have compared?
Sorry, ma'am, sorry, ma'am. This S phi square consists of the steady variable, and the our function, which consists of auxiliary variable, consists of basically we have considered the steady variable.
Okay, so for this numerical illustration, which form of your function you have considered? Ratio type or regression type?
Ma'am, regression type.
Regression type. Okay, so you have not compared with the usual regression estimator for S by square?
Ma'am, usual regression estimator, we have done work in our paper, but due to less slides, we are unable to show it there.
That's okay. So nice presentation, Abhijit.
Thank you.
Thank you. So next contributive paper number 116, B Sangeeta or B KS Korenia, who is available here?
Yes, ma'am.
Okay, so your country paper number is 116?
Yes, ma'am.
Okay, so your name is?
Karanya.
Okay, so now I would like to invite KS Karunya for the presentation. Her title of presentation is a design for double sampling plan 01 under fuzzy environment. So Karunya, you can share your presentation.
Okay. Good morning, everyone. Myself, Karnya from PhD College of Arts and Science, under the guidance of Sangeeta. My topic is a design for multiple dependent set sampling plan under fuzzy environment. And my abstract is acceptance sampling is an effective tool in decision making, and it is useful in destructive testing of samples, reducing 100% inspection. Usually, parameters of the sampling plan are known, but in some cases, it is difficult to define parameters. In these cases, parameters are defined as linguistic variables with the use of fuzzy set theory. In this paper, we introduced a new design for multiple dependent set sampling plan when their main parameters are fuzzy probability acceptance, and fuzzy operating characteristic curve of a multiple dependent set sampling plan using fuzzy Poisson distribution is derived in this paper. Introduction. Acceptance sampling is a methodology that deals with the procedure for taking decision to accept or reject the manufacturing products based on the inspection of same.
Just a minute, Karnya, your slides is not changing.
And now?
No, just change the slide from the left panel. I think there is some problem. So you are in presentation mode? Yeah, now it is changing. Yeah, now it's fine.
And the major areas of acceptance sampling are lot by lot sampling by method of attributes, lot by lot sampling by method of variables, continuous sampling plan, and special purpose samplings. Introduction for fuzzy set theory. Fuzzy set theory is a mathematical model of vague data generated by the experiments, and it is powerful tool to analyze the parameters that cannot be estimated accurately. Here, we are using fuzzy set theory in acceptance sampling plan to determine the uncertainty existing in quality characteristics by defining the impulses parameter as fuzzy number to achieve the higher certainty in quality characteristics. This work mainly relates to the study of multiple dependent state sampling plan using fuzzy set theory. Multiple dependent state sampling is derived by Baker in 1976, and the acceptance and rejection in multiple dependent state sampling is not only based on the results from current lot, but also the sample results of the past and future lots. The operating procedures of multiple dependent state sampling plan are: from each lot, select a random sample of n units and observe the number of non-conforming units d. And if d is less than or equal to r, accept the lot. If d is greater than r plus b, reject the lot. If d lies in between r plus 1 and r plus b, accept the lot if the forthcoming m lots in a series are all accepted. The OC function of the multiple dependent state sampling is provided. Here, we are considering the parameters of the multiple dependent state or as triangular fuzzy number using fuzzy set theory. In the case when the fraction defective of a multiple dependent state sampling plan is uncertain, and we are considering this fraction defective as fuzzy triangular number, and further the fuzzy probability of x events in n events are calculated using the formula, and considering a situation when multiple dependent state sampling plan is performed where the probability of events be the number of events and the number of preceding or succeeding lots are fuzzy. And in these situations, the parameters are considered as triangular fuzzy number, and the fuzzy probability of n events using fuzzy Poisson distribution is calculated using the equation. Using these equations, we can calculate probability of acceptance of a multiple dependent state sampling plan. The fuzzy OCO. The fuzzy probability of acceptance of a lot in terms of fuzzy parameter is a band with upper and lower bounds. A bandwidth depends on the degree of uncertainty. The OC bandwidth is wider when the lot quality is in good state, when the OC bandwidth is in narrow when the lot quality is in undesirable state. For example, when we are performing multiple dependent state sampling plan, the fraction defective approximately 0.01 and the number of events is approximately 10, then the fuzzy probability of acceptance using fuzzy Poisson distribution is calculated and the OC curve is presented. The OC curve, by viewing the OC curve, we can say that the fuzzy OC curve is a band with upper and lower bounds. The conclusion is the multiple dependent state sampling plan is designed with fuzzy parameter, sample size, acceptance number, and the fraction of non-conforming is flexibly defined with the use of fuzzy set theory. The obtained OC curve, from the obtained OC curve, we can see that we can select the samples. We can select the samples by viewing the OC bandwidth and helps in reducing the sampling cost. By viewing the fuzzy OC curve of multiple dependent state sampling, we are having a whole possibilities of OC curve with the effects of fuzzy parameters. These are my references. Thank you.
Any question? Any questions from the participants? Okay, Karunya, just a small query. Have you checked your fuzzy model with by bearing the different parameters?
Yes, ma'am.
Okay, so you have considered 3 parameters in this.
Yes, ma'am.
So you have checked the effect by varying these all 3 parameters.
Yes, ma'am.
Okay, so your model, this is coming better.
Yes, ma'am.
Okay, thank you, Karunya. Nice presentation.
Thank you, ma'am.
Thank you. So our next presentation is presentation number 117 by Dr. N. Sahu and S.K. Jhankar. So are you available here?
Yes, ma'am, I am present.
Okay, so Dr. Nirupna Sahu,
Yes, ma'am.
please share your screen, and your presentation will be on an exponential ratio type estimator for estimating population variance with its efficiency. So please share your screen.
Is it visible to ma'am?
Yes, yes, it is visible.
Thank you, ma'am. A very good afternoon to all, respected madam and all the dignitaries present here. My name is Nirupama Sahu from School of Statistics, Gangadhar Mehra University, Odisha. So my topic is an exponential ratio type estimator for estimating population variance with its efficiency. So here I have proposed a new exponential ratio type estimator for estimating population variance using auxiliary information, which is based on simple random sampling scheme. And here I have derived bias and mean square error of the proposed estimator and compared with the existing estimators. So the theoretical findings are also supported by an empirical study. And again, an efficiency of the newly proposed estimator in comparison to the existing estimators is also obtained through simulation study. And for better understanding that the graphical layout also carried out on the basis of percent relative efficiency and mean square error. So these are the key words I have taken: that simple random sampling, variance estimation, mean square error, and simulation study. Now, just introduction. So estimating the finite population variance has great significance variance in various fields such as industry, agriculture, and medical and biological science, where we come across population which are likely to be skewed. So variations are present everywhere in our day-to-day life. So our manufacturer needs constant knowledge of the level of variations in people's reaction to his product to be able to know whether to reduce or increase his price or improve the quality of the product. So ratio type estimators taken advantages of the correlation between the auxiliary variable and study variable when information is available on the auxiliary variable that is positively correlated with the study variable. So the ratio estimator is a suitable estimator to estimate the population variance. So now that here I have taken the population variance estimation, and these are the notations for this estimation procedures. And here I have carried out some of the existing estimators. So first, that existing estimator it is our usual unbiased estimator, that is population variance, and it is your variance of this T0. It is notation for this usual unbiased estimator. And then equation 2, it is due to Isaki 1983. Then I have taken also Cadiller and Singh 2006. and also Upadhyay and Singh 1990, Wahal and Tuteza 1991. So these are the 7 type of estimators, that is existing estimators, in which I have compared the newly exponential ratio type estimator for population variance. So then I have proposed an exponential ratio type estimator for population variance, that is TRE hat. So noted this the notation for newly proposed estimator. This is where A is suitably chosen constant. That equation 14 is my proposed estimator. And by expanding this equation 14 and substituting the values of E0, E1, where the introduction part I have already taken that E0 and E1, this is already defined, so that we can get the expansion of TRE hat, where alpha is 1 by A. Now the bias of the proposed estimator up to the first degree of approximation is found as this, like the equation 15. And mean square error of TRE hat, this is equation 16. So from equation 16, or that is mean square error of TRE hat, I have found the optimum value of alpha. So by partial differentiating the equation 16. So with respect to alpha, I have got that alpha optimum, it is our lambda 22 minus 1 minus lambda 04 minus 1, which is divided by lambda 04 minus 1. This is the optimum value of alpha. Again, that is efficiency comparison of the estimator. So in this section, the minimum mean square error of the proposed estimator, that is TRE hat, with usual estimator, that is SY square, and other competing estimator has been compared. So under these conditions, the newly proposed estimator gives more accuracy with respect to, that is our usual estimator and also other competing estimators. So these are the conditions from equation 18 to equation 25. These all are the conditions. Now for empirical study, I consider the following data, which is taken from the authentic sources published by Management Society, Paradip Fishing Harbour, Odisha, India. And it is duration in 2016 to 17. Here I have taken that Y as the marine fish landing in the month of November and X as the marine fish landing in the month of October. So that means here I have got that is the positive correlation between this Y and that is study variable and auxiliary variable. That's why I have taken this example, and from that data I have found the parameters of population. So this is N is 43 and sample size I have taken that 10, and then lambda 40, lambda 04 and lambda 22. So these are the parameters of population. So now it is for table 2, this gives percent relative efficiency of all the existing estimators and also newly proposed estimator, with respect to that population variance. So here T0, that is the usual unbiased estimator, T1 that is our Isaki estimator. So at the end, this is I have got that TRE hat, which is 443.7655, and so that it is clear that from table 2, that is the newly proposed an exponential ratio type estimator gives more efficiency in comparison to the other existing estimators. Now for better understanding, I have also the layout of this percent relative efficiency of proposed estimator as well as traditional estimator. Now further simulation study I have also carried out. So I also carried out a simulation study to verify the superiority of the proposed estimator. for that, I generate n is equal to 250. That is our population size 250. That values of xi, yi from a bifurcated normal distribution with mean 60 and 60 and standard deviation 10, 10 with fixed correlation coefficient value is 0.90. So from this population, I have taken that sample size n is equal to 20. That is by simulating the data 500 times, I have generated a finite population of size 250 and also calculate the following simulated mean, standard deviation and other parameters for the fixed correlation coefficient value. So in table 3, it represents the parameters values for the simulated data where I have taken that rho is 0.90. I have kept as the that is our fixed rho that 0.90 and found that x bar, y bar, sx, sy, lambda 40, lambda 04, lambda 22. So by using these parameter values for the simulation data, again I have calculated that mean square error for the existing estimator and also the proposed estimator. So these are the table 4. It represents the estimators and also mean square error for the values, that is rho is 0.90 and sample size n is equal to 20. So see, this is T0 up to T7. These are the existing estimator, or you can say it is a traditional estimator. And where I have found TRE hat, that is newly proposed estimator, it is 286.4353. So this mean square error is minimum in comparison to other traditional estimators. So this is again a graph, that is a graph which represents the mean square error values both for proposed and existing estimators in case of simulation study. So so from table 2 and from table 4, that means it is observed that superiority of proposed estimator over the existing estimator is gained. That means in total, I have got that is the newly proposed estimator gives more efficiency in comparison to the usual unbiased estimator and also other competing estimators. So these are the references I have taken. Thank you.
Any questions from the participants? Or any observation? Okay, Dr. Nirupama, just a small query. You have generated a population of size 250, population of size 500 or 250?
Yes. 250.
250, okay. And so you have generated 500 times, you have generated population 500 times? Or selected samples?
Simulated, madam. This is the simulation of data 500 times. So that generate population size is 250.
Okay. In simulation, you have generated population 500 times. 500 populations means, right?
Not madam. It is 500. It is 500 times I have simulated the data.
The data for the population, not the sample. Yeah.
Yes. Yes.
Okay, and you have also selected sample, or on the basis of these 500 populations, you have computed the values of.
Madam, from this this sample size, I have considered the population size is 250, and
okay.
Again I have taken that sample size n is equal to small n is equal to 20.
Okay. Okay. Thank you, Dr. Nirupama. Nice presentation.
Thank you, madam.
And our next presentation is again Dr. N. Sahu and Dr. S. Das, who will be presenting. S. Das, Mr. S. Das, yeah?
Yes, ma'am.
Yeah, okay. So the title of this presentation is Population Mean Estimation of Sensitive Variable Using Non-Sensitive Auxiliary Information in Post-Stratification under Two-Phase Sampling.
Yes,
so, Mr. Das, please share your presentation.
Yes, it is visible, ma'am.
Yeah, it is visible.
Okay. A very good afternoon to everyone. Means the chairperson and all the delegates present over here. Myself, Suman Das, as a research scholar from the School of Statistics, Gangadhar Mere University, and my topic is population mean estimation of sensitive variable in post-stratified two-phase sampling using non-sensitive auxiliary information. So in my study, this study is actually based on the estimation of the population mean of sensitive variable in post-stratified random sampling using the two-stage sampling based on the randomized response sampling. So in this study, we have actually introduced the ratio and regression type estimator for estimating the mean of the sensitive variable using the non-sensitive auxiliary variable based on the randomized response technique in case of the post-stratified two-phase sampling. And in this study, we have actually computed the bias and mean square error, and we have seen their efficiency using the one of the numerical example. So before going to actually the proposed estimator, I would like to enlighten the idea about what is the actually randomized response.
I think your slide is stuck. Please.
Yes, ma'am. Let me check. So where it is actually stuck, ma'am?
Yes, it's showing slide number 3 now.
Okay. Then it's fine. Yeah. So in the social science research, many times it occurs that the respondent actually hesitate to answer some of the questions which are actually sensitive. So in that case, we cannot able to find the accurate data in our survey due to the hesitancy of the respondent. So in that case, we are actually for this problem, the Warner in 1965 introduced the technique that is known as your randomized response technique, which actually helps us to extract the data from the corresponding to the sensitive questions. This is the basically all things about the randomized response technique, and this was actually developed by the Warner in 1965. And the two-phase sampling, two-phase sampling is the procedure in which we can obtain the information about the auxiliary variable from the larger sample at the first phase and relatively small sample in the second phase. So we can find some of the work regarding the two-phase sampling on the ratio and regression and product type estimator in different journals like Sukhatme in 1962, Singh and Biswakarma 2007, and etc. Then the next thing is the stratification. What is stratification? The stratification is actually a technique in the sample survey, and where we are actually presuming the knowledge that the strata size and the sampling frame for each of the stratum are known. But in many situations, it happens that the overall population size, also the percentage of unit that falls in that strata are known, but the sampling frame for the stratum may not be available, or it quite time consumable for preparing. In such situation, we cannot support to use the stratified sampling. So to overcome this type of problem, we are actually introducing the post-stratification technique, and in which the sample size n is drawn by the simple random sampling. This sampling is stratified in different strata and used as the stratified sample. So in this particular actually study, we are actually presented a ratio regression type estimator in the population means using the sensitive variable, using the non-sensitive auxiliary information or the variable, using the randomized response technique in the post-stratification two-phase sampling. So the these terms which are actually used in this study, that we are actually assuming there are n for the population size is n, and that population size is classified into L strata, and each of the strata are denoted like this n1, n2 up to nl, and such that the summation over s equal to 1 to l ns is equal to capital N. And the small nh be the sample size falling in the hth stratum, such that the summation over s equal to 1 to nh should be equals to the small n. Then we are actually considering that capital Y as the study variable and a sensitive variable. This Y is a sensitive variable which cannot be observed directly due to the respondent hesitancy, you may say, or the bias. So, and the X is the non-sensitive auxiliary variable which is positively correlated with the study variable Y. And again we are actually defining a scrambling variable S, which is independent to the both the study variable and the auxiliary variable X. And the reported response for the S we are actually defining as Z, and that will be equals to the summation of the Y and the scrambling variable S. And now we are actually defining the YHI with the observations of the population in that falling in the ith unit of the hth stratum for the study variable Y, and XHI with the observations in the ith unit of the hth stratum for the auxiliary variable X. And when the information on the XH head bar is unknown, a fast large sample of size NH dash is selected from the hth stratum to estimate the XH bar. Actually, some problem is occurring. Okay, so for the estimation of the population mean, we should estimate the X bar that will be equals to summation over I is equal to 1 to NH WH XH bar, where this WH is equal to NH divided by N, and we are defining this Z bar will be equals to summation over I is equal to 1 to NH WH ZH bar. So is the population mean for the reported variable Z. So to get the mean square error under the post-stratified two-phase sampling, we are defining the some of the notation, that is your small ZH bar is equal to capital ZH bar 1 plus E0 and so on, and the expectation of E0, expectation of E1 and expectation of E1 dash is equal to 0, and some of the notation for the expectation of E0 square, expectation of the E1 square, expectation of the E1 H dash square, expectation of the E0 E1, and expectation of the E0 E1 dash. Then our proposed estimator is actually this estimator we have proposed by following the Sosa et al. At in 2014, and the M. Nadia, Nur ul Amin, and H. Mohammed in 2016. We have introduced the ratio and regression type estimator of the sensitive variable in case of the post-stratified two-phase sampling, and that estimator is your TRPS will be equals to K1 Z bar PS plus K2 multiplied with your X bar PS dash minus X bar PS multiplied with alpha, that as I have mentioned here. And here this K1 and K2 are the weights that can be determined by choosing this alpha is equal to 0 or 1, and in this estimator the B is used as a real number, and that is known as the that is the known parameter of the auxiliary variable. So using that previous notations, you have actually expressing that estimator like this TRPS will be equals to K1 Y bar and so on in the equation 3.2, where we have actually introduced this G that will be equals to your capital X bar divided by X bar plus B. And for this expression, if we are going to calculate
your screen is on 6 number slide, isn't it?
Let me see, ma'am. No, ma'am, I'm in 8th.
Okay, so it was stuck then.
Okay. Is it visible, ma'am, now?
Yeah, it's showing 8, slide number 8 now.
Okay. So by using that previous notation of the expectation of the E0, E1 and the E1 dash, and the expectation of A0 square expectation and all these notations, you are actually expressing that estimator that we have defined in that equation 3.1 that is expressed as TRPS will be equals to like this. That is your K1 Y bar plus K1 Y bar and so on, as it is mentioned in the 3.2, where you have actually used the another term G, which is defined as this capital X bar divided by capital X bar plus B. And again, from these expressions, the biased and the mean square error for the estimator were actually calculated. That is, your bias of the TRPS is expressed in that equation 3.3, and the MSE is expressed in that equation 3.4. And then to get the optimum value for the K1 and K2, we have taken the differentiation of the mean square error with respect to the K1 and K2, and we have got the optimum value for the K1 and K2 like this. And by using the value of the K1, K2, we have found the MSE of the proposed estimator is like this, as it is mentioned in the equation 3.5. So for this, we have actually introduced a numerical example, and where we have defined the two stratum, and we have got the percent relative efficiency of the proposed estimator is found to be 171.19 as compared to the existing estimators. And from this result, we have concluded that our proposed estimator is having the better efficiency as compared to the other existing estimator, as I have mentioned earlier. And these are my conclusions. Sorry, these are my references, which I have actually referred during this study. And thank you.
Please, once again, go to the slide number 7.
Okay. Okay, ma'am. Is it visible, ma'am?
Yeah, it is visible. This is your estimator. Okay.
Yeah.
So, any questions from the participant? So today there is no questions from the participant, I think. You have considered real data for this numerical illustration. So have you tried you have computed only your relative efficiency and mean square error?
Yes,
So
yes,
what is about your bias?
Since the percent relative efficiency is actually higher as compared to the existing estimator, so up to that I have actually calculated that bias thing. Obviously, if it is percent relative efficiency is higher as compared to the existing, so definitely it will perform better.
Okay. So
I'm also
yeah.
I am planning to have the simulations study, but I have not done yet.
Yeah, for simulation study, you can try by varying the sample sizes for different sample size. You can consider and for different values of rho.
Yes.
And you have computed for the optimum value of alpha. Your result is for. Huh?
Yes.
Okay. Okay. Thank you. A nice presentation.
Thank you, ma'am. Thank you. Thank you so much.
And now our next presentation is 121 partial product estimators of population mean under simple random sampling by Mr. Gagandeep and Sarabjit Singh Brar. Are you there?
Yes, ma'am. Good afternoon.
Yeah, very good afternoon. So Ms. Gagandeep, please share your screen.
Yes, ma'am. 15 minutes. Is my screen visible?
Yes, yes, it is visible.
Okay, may I start?
Yeah, sure.
Okay. Good afternoon, everyone. I am Gagandeep Kaur, research scholar under the supervision of Dr. Sarabjit Singh Barat from Department of Statistics, Punjabi University, Patiala. Today, I am here to present my topic, partial product estimators of population mean under simple random sampling. Here is the layout of my today's presentation. First of all, introduction. After that, notations followed by proposed estimators, then approximate expressions for bias and variance, efficiency comparison, simulation study, and the last is conclusion and references. First of all, introduction. The main objective of sampling theory is to construct efficient sampling strategies so one can estimate population parameters more accurately. In the literature of sampling theory, many sampling strategies are available in which only characteristic understudy is directly used to estimate population mean. In some situations, the characteristic understudy highly correlates with the another non-characteristic called as auxiliary variable. The information on auxiliary available in one form or the other or can be made available by diverting a part of survey resources at a moderate cost. In many repetitive surveys, the value
Your voice is not coming. Yeah.
is usually taken as the value of the auxiliary. Hello?
Yeah, your voice is breaking in between.
Okay, ma'am. It is well known that when auxiliary is available,
I think Miss Gagandeep is having network issue. So let's wait for 2 minutes. Otherwise, we will move towards the next presentation.
hello, now am I audible?
Yes, you are now.
Sorry, ma'am, I was disconnected.
Yeah, it's okay. Please continue.
Okay. There may arise some practical situations where auxiliary information is not available for the whole population. To deal with such situation, Brad et al. Proposed partial ratio estimators when auxiliary information is partially available, relevant, and positively correlated with study variable at estimation stage. In the present paper, partial product method of estimation is proposed when partial auxiliary information is available and is negatively correlated with the study variable. For example, an investigator wants to estimate the per capita income, which may be correlated with the time spent on domestic work. In general, a country like India, only women are considered to contribute to the domestic work. When the income of a working woman increases, their time spent on the domestic work decreases. However, men generally are not considered for any kind of the domestic work, whether they are working or not. Thus, due to social norms, the income of women is highly negatively correlated with the time spent on domestic variable, and working hours spent at home is auxiliary variable, and these variables are partially correlated. These are the notations which I used in my present paper. Capital N with the size of population, Y and X are the study and auxiliary study variable and auxiliary variables, and auxiliary information is available or useful for subpopulation or for class A of size N1, and for the remaining class A dash of size N2 it is not. W1 is and W2 are the proportion of units belonging to class A and A dash. Capital Y bar 1 and Y bar 2 are the means of study variable for class A and A dash, as it is X bar 1 and X bar 2 are the means of auxiliary variable for class A and A dash. Y SY1 square, SX1 square, SY2 square, SX2 square with the mean squares of the study and auxiliary variables for class A and A dash respectively. And these are the notations which I used in my paper. Now, proposed estimator, partial product estimator of population mean suggested when only partial auxiliary information is available or useful. Here arise two cases. Case 1, when W1 and W2, when weights are unknown, a partial product estimator of population mean is defined as Y bar PP is equal to W1 Y bar P1 plus W2 Y bar 2. And in case 2, when weights are unknown, the estimated values of capital W1 and capital W2 is used in first equation, as we will get Y bar dash PP is equal to small w1 Y bar P1 plus W2 Y bar 2, where Y bar P1 is usual ratio estimator. Sorry, usual product estimator. Case 1, when W1 and W2 are known, to obtain the approximate expression for bias, the proposed estimator is Y bar PP. This is equal to capital W1 and Y bar P1 plus W2 Y bar 2. After the calculation, we will get the approximate bias as given in equation number 3, and for large N, this bias will be equal as given in equation number 4. And approximate expression for its variance is given in equation number 5. Now, in case 2, when W1 and W2 are unknown, when weights are unknown, then we will use the estimated values of weights. So our new proposed estimator is Y bar PP dash. This is equal to small w1 Y bar P1 plus W2 Y bar 2. Now, after calculations or derivation, we get bias as given in equation number 8, and for the large N, this bias is given in equation number 9. And approximate expression for variance is given in equation number 10. Now, in both the cases, expression for bias of Y bar PP of partial product estimator when weights are known and weights are unknown up to approximate order n-1. However, there is increase in variance when weights are unknown due to loss of actual values of W1 and W2. Now, efficiency comparison of partial product estimator with mean per unit estimator. As we know, the variance for large N of mean per unit estimator is Y bar square Cy square upon N. And the variance of our proposed estimator is given in equation number 12. After comparing these two variances, I get the condition 13. If this condition is true, then our proposed estimator is more efficient than the mean per unit estimator. Next is efficiency comparison between partial product estimator when weights are unknown with the mean per unit estimator. Now, comparing the equation 11 and 12, we will get the equation number 14. If this condition is true, then proposed estimator is more efficient than the mean per unit estimator. Next is efficiency comparison between partial product estimator when weights are known with the post-stratified strategy. When weights of class A and A dash are known, it is more sensible to compare the proposed strategy with the post-stratified strategy. And expression for variance for post-stratified strategy is given in equation number 15. After comparison, we will get the equation number 16. If this condition is true, then our proposed estimator is more efficient than the post-stratified strategy. Here is the simulation study. To confirm the theoretical results, a simulation study was conducted using R software. For this purpose, the stratified population of size 500 generated from a normal distribution as given below. So here is the biases for various estimators. Here we can see when sample size is 7, here is the bias for mean per unit estimator. Here is the bias for post stratified estimator. Here is the bias for partial product estimator when weights are known, when weights are unknown. Here is bias for the simple product estimator. We can see here in all, bias is approximately equal to 0. Mean square error. When sample size is 7, as sample size increases 7, 15, 13, mean square error decreases for every estimator, and the mean square error of our proposed estimator is minimum than the other estimators. When correlation is minus 0.536, when correlation is moderate, then these are the mean square errors. As correlation is minus 0.735, correlation increases, is more negative, then mean square error decreases. Next is the efficiencies of various estimators. As sample size increases and correlation is highly negative, as correlation's negativity increasing, proposed estimator give us the best results as compared to the other estimators. Here we can see 114.0169 for the post-stratified strategy. This is for the partial product estimator when weights are known, and this is for when weights are unknown. So the results of the simulation study. From figure 2, all estimators are almost unbiased for the given population. For row 1, when minus 0.536 and minus 0.91, there is a gain in the precision of the proposed estimators over the corresponding existing estimator, and this gain increases as correlation increases. When W1 and W2 are known, the gain in precision is much higher, and the rate of increase in the gain of precision with respect to correlation 1 is more than the when weights are unknown. And efficiency of Y bar PP partial product estimator when weights are known increasing as n increases. However, efficiency of when weights are unknown almost constant as n increases. Next is conclusion. When only partial information is useful or relevant at estimation stage in simple random sampling, the proposed estimators are more efficient than the mean per unit estimator under certain conditions. Furthermore, when actual weights of classes or strata are known, then proposed estimator when weights are known is more efficient than the usual weighted estimators under post-stratified sampling, provided the correlation coefficient between auxiliary and study variable for the given class is less than minus 1 by 2 Cx1 upon Cy1. Hence, the proposed sampling strategy is more beneficial than the existing ones in the following real-life situations. First one is when study and auxiliary variables are partially and negatively correlated, and due to administration inconvenience or due to any other reason, only partial auxiliary information is available. Here is the references. These are the papers which I used. Thank you.
What are the values of W1 and W2 you used for the known case? I think she has disconnected again. Sorry, I missed 2 of the papers in between, 119 and 120. So next we consider paper 119, improved chain ratio type and chain product type estimators for population mode through linear transformation under double sampling.
Yes, ma'am. W1 is equal to N1 upon N.
Okay.
As I given, just wait, ma'am. I was again disconnected. Just wait.
It's okay.
So sorry, ma'am.
No, it's okay. So you have considered the proportion of observations, yeah?
Yes, ma'am. N1
W1
upon N. Yes, and W2 is N2 upon N.
Okay. And for the unknown cases, you obtain the optimized value of W?
Yes, ma'am.
Okay. So you also tried for another values of W? Another combinations?
No, ma'am.
So have you also tried for this positively correlated?
Yes, ma'am. Yes. For positive, I used a partial ratio estimator.
Yeah.
Yes, ma'am. Yes, ma'am.
Okay. So any questions from the audience? So again, no question. Okay. Now thank you, Ms. Gagandeep, for the nice presentation. So now let me invite Mr. Akhilesh Yadav to share his work.
Sorry for the inconvenience.
No problem. It's okay.
Good afternoon, everyone.
Good afternoon.
Ma'am, is it visible, my screen?
It's not fully visible. It's only black screen is visible.
Okay, I'm sharing it. Now is it visible, ma'am?
Yes, now it is visible.
Okay. Myself, Akhilesh Yadav. I am research scholar under Dr. Sanjay Kumar. I am from Central University of Rajasthan. So topic of my research, this article is improved chain ratio type and chain product type estimators for population mode through linear transformation under double sampling. So starting from the introduction, the aim of survey sampling is to obtain statistical information about the finite population by selecting probability sample from the finite population and measuring the required information about the units in the sample and estimating the finite population parameters such as mean, median, totals, variance, and coefficient of variation of a study variable. The efficiency of the estimator is improved by using auxiliary information on one or more than one variable. Proper use of auxiliary information for estimating population mean of the study variable has greater applicability in survey research. In 1942, Cochrane was the first who used ratio estimator to estimate population mean of the study variable when the population mean of auxiliary variable is known, while Cook and Mack in 1989 used the ratio estimator for estimating median of the study variable. In 2014, Sidori and Singh was the first who estimated population mode using ratio estimator under simple random sampling. After that, Lamy, Channe and Singh in 2016, and S. Kumar and N. Tiwari in 2019 estimated population mode using ratio estimator under two-phase sampling. So motivated from Chand in 1975 and Yadav and Kumar suggested chain ratio and product type estimators for estimating population mode. So the suggested estimators are given in equation 1.1 and 1.2. And the expressions of bias and MSC of the equation 1.1 is given in equation 1.3, and expression for MSC of the suggested estimator is given in equation 1.4. Similarly, bias and MSC for the product type estimator is given in equation 1.5 and 1.6. So Monti and Sahu in 1995 have defined two ratio estimators by making the transformation on auxiliary variable X using its minimum and maximum values in the population. When the values x minimum and x maximum in addition to its population mean are available in advance. Now using these auxiliary information, we transform the auxiliary variable x to new variables u and v through linear transformation using the known auxiliary information. So the transformed variables are given below. So motivated from Mohanty and Sahu, we have suggested chain ratio and product type estimator, which is given in equation 1.1 and 1.2. And using linear transformation, we have proposed transformed estimator, which is given in equation 2.1 and 2.2. And this is the transformed product estimators, which is given in equation 2.3 and 2.4. So the expressions for proposed estimator are given as follows, which is expression for bias is given in equation 2.5 for the transformed ratio estimator, and expression for MSC for transformed estimator, which is given in equation 2.6. And another transformed estimator which is represented by TS, and expression for bias is given in equation 2.7, and expression for MSC is given in equation 2.8. So the MSCs of the proposed estimator capital TR and capital TS can also be defined as follows, which is given in equation 2.9 and 2.10, where R1 is equal to Rx by A1 and R2 is equal to Rx by A2, while A1 is equal to 1 plus X minimum divided by X curl, and A2 is equal to 1 plus X max divided by X curl, where A1 lies in interval 1, 2 and A2 is greater than 2. So in this section, we have compared the efficiency. We have compared the efficiencies of the proposed ratio type estimators curl TR and curl TS with the existing estimators small tr and y curl under two preference region we are usually considered in practice. So the region of preference of small tr over t, that is k greater than half and k1 greater than half, and another reason is when k less than half and k1 less than half, where k is equal to rho yx cy by cx and k1 is rho yz cy by cz. So considering the first reason, on comparing the MSC of capital TR and TS, we observe that capital TR is better than TS when equation 3.1 is satisfied. However, when TS is better than TR, the above inequality condition will be reversed. So further comparing the MSC of capital TR and TS with that of small tr, it is noted that both capital TR and capital TS have better precision over small tr when equation 3.2 and 3.3 satisfied. On combining equation 3.1, 3.2 and 3.3, it is observed that capital TR is preferred over capital TS and small tr when equation 3.4 satisfied, and when capital TS is preferred over capital TR and small tr when equation 3.5 satisfied, and small tr is preferred over capital TR and capital TS when equation 3.6 satisfied. It should be mentioned here the spread of the regions of preference capital TR, capital TS and small tr is given in equation 3.4, 3.5 and 3.6, and their validity depend on the values of A1 and A2, as 1 plus A1 by A1 and 1 plus A2 by A2 are always greater than 1. Their validity under these preference region depends upon A1 plus A2 divided by A1 into A2, which takes value greater than 1 when curl x square is greater than x minimum and x maximum, and less than 1 when curl x square is less than x minimum into x maximum. It is to be noted here that regions of preference given for curl TR and curl TS remain unchanged when curl x square greater than x minimum into x maximum. However, when curl x square less than x minimum into x maximum, the inequality 3.5 does not hold, as the right hand side of this inequality becomes less than the left hand side. Hence, under this condition, the case TS does not arise in this region of preference. Thus, when x square less than x minimum into x maximum, the three regions of preference narrowed down to two regions of preference. which are given in equation 3.7 and 3.8. So we can see that curl TR is preferred over TR when equation 3.7 satisfied, and small tr is preferred over capital TR when equation 3.8 satisfied. So taking another reason of preference, the transformed ratio estimator capital TR and TS are preferred over small tr when the condition 3.2 and 3.3 are satisfied, since 1 plus A1 divided by 2A1 and 1 plus A2 divided by 2A2 are always greater than half. The conditions 3.2 and 3.3 holds true in this region of preference. Hence, capital TR and TS are always better than TR. Under this region of preference, capital TR and TS are better than Y when condition 3.9 and 3.10 satisfied respectively. Combining the preference region of capital TR and TS, that is given in equation 3.1, and TS over capital TR with region given above, we obtain that capital TR is preferred over capital TS and Y when equation 3.11 satisfied, and TS is preferred over capital TR and Y when equation 3.12 satisfied, and small y curl is preferred over both transformed estimator when equation 3.13 satisfied. So when curl x square less than x minimum into x maximum, the region of preferred mentioned above remain unchanged. However, curl x square into x minimum, the inequality 3.11 does not hold, as the left hand side arise under this region of preference. So when curl x square less than x minimum into x maximum, we have two regions of preference against three mentioned as above, that is given in equation 3.14 and 3.15. So as we can see that proposed transformed estimator capital TS is preferred over y curl when equation 3.14 satisfied, and small y curl is preferred over transformed estimator capital TS when equation 3.15 satisfied. So we have combined all the estimators for their according to their preference region when a small tr is preferred under this preference region, which is given in one number, and capital TR and capital TS preferred under this preference region, and small y curl will be preferred under this preference region. So thus it is noted that these regions of preference may increase or decrease depending upon the values of A1 and A2. So we have done simulation study. We have generated the random variables for secondary auxiliary variable Z using these parameters for gamma distribution by using R software, and we estimated the main auxiliary variable using this linear relation. In the same way, we estimated a steady variable using this linear relation where E1 and E2 are the standard normal variate. The choice of coefficients is made to generate all the 10,000 non-negative values such that the steady variable and main auxiliary variable is highly correlated. The population correlation between steady variable and main auxiliary variable, that is row wise x, is 0.96, and the population correlation coefficient between the steady variable and additional auxiliary variable is row wise z is 0.93, as well as population correlation coefficient between main auxiliary variable and additional auxiliary variable is 0.96, which is required for our study. So we have here made the table for generated descriptive parameters for the generated data sets, and here we have plotted density over histogram for skewed population that we have generated. So in this section we have given the table for simulated values of relative efficiencies and MSE and absolute relative bias. So here we can see that these are capital TR and capital TS are our proposed transformed estimator. We can see that relative efficiency of these two proposed estimator is higher than other existing estimators. The MSE is minimum for these two proposed estimator as compared to other two estimators. As we are increasing the sample size, MSE is going to decrease and the efficiency is also increasing. And another format, we can see the absolute relative bias of these two proposed estimator is minimum as compared to the other existing estimator. And as we are increasing sample size, absolute relative bias is going to decrease. And in this section, we have also calculated the ratio of simulated values and exact values of MSE, which is close to 1. It means that we can use the mean square simulated mean square. We can use the exact mean square error in place of simulated values of mean square errors. Here we have plotted the MSE and sample size. We can see that these are the two proposed estimator and these are two existing estimator. As we are increasing the sample size, MSE is going to decrease. In this, we have also calculated the exact values of mean square error and absolute relative bias. Here we can see that proposed estimator is showing a higher efficiency as compared to the other existing estimator. As we are increasing the sample size, mean square error is decreasing and absolute relative bias is also decreasing. This is the plot for the exact MSE and sample size. When we are increasing the sample, the MSE is going to decrease. We have also calculated the confidence interval and other estimates, and here we can see that coverage of the proposed estimator, proposed transformed estimator, is higher than other existing estimator. So we can see that transformation using transformation efficiency and coverage percentage of the transformed estimator is higher than other existing estimators. So with the help of artificially generated data set, we can conclude that the proposed estimator of population mode using two linear transformation has a lower mean square error than that of existing estimators. That is, relative efficiency of proposed estimator has greater than that of another existing estimators. These are the references which I have used for my study. Thank you.
Participants, any question? So Akhilesh, just a small query.
Yes,
You have generated data by using a model A1 plus B1X.
Yes.
So in this model, the A1 is same as which you have used in your derivation?
No, ma'am. Here A1 is different.
Okay.
Okay. Yes, ma'am.
Okay, thank you, Akhilesh. Nice presentation.
Thank you, ma'am.
So now our next presentation is 120, enhancement of exponential ratio type and product type estimator in two-phase sampling by Dr. N. Sahu and S.K. Jhankar.
Yes, ma'am, I'm present.
Yeah, please share your presentation.
Yes. Ma'am, it is visible?
Yes, yes, it is visible.
Yes, this is Shamna Kumar Hankar from School of Statistics, Gangadhar Mehra University, Sambalpur. So my topic is enhancement of exponential ratio type and product type estimator in two-phase sampling. And so we know that various types of authors and resource scholars have been already worked on this space, and we are also by motivated their work, we are also trying to propose some ratio and ratio and proposed product type of estimator in this case. And we know that what happened there. So sometimes we can come across the situation where we face some problems regarding taking samples. You may say that sometimes what happened there, we can come across the situation when the auxiliary variable X is not known in advance, or it is relatively cheaper to obtain information on X. Okay. So in such a situation,
I think your slide is not changing.
Okay.
Which slide?
Okay, ma'am. I'm actually telling you that things that why actually we are considering our two phase. So I will come in the start part later. So in such a situation, to eradicate the such types of problems, actually you actually comes to the two-phase sampling. So this is my abstract part that is. So in this study, we have proposed an exponential ratio and product type estimator to estimate the mean of study variable y by incorporating auxiliary variable under two-phase sampling scheme. The expression of y's and mean square error has been obtained up to the first order of approximation, and an empirical study has been carried out to check the to show the superiority of our estimate. Okay. So it is observed that the estimator considered by various authors as equal unbiased estimator is less efficient than our proposed estimator. So for the theoretical supports, we also carried out a simulation study by using R programming. So these are my keywords, that is simple sampling, mean square error, two-phase sampling, and simulation study. In the next slides, you can see that these are my notation that I have been taken for my study, and that is comes to the important part that which I have interest. So this is first one. Here you can see that in the red color there are two kinds of estimator that we have been considered. First one is our ratio type estimator, and second one is product type estimator. So so these are my proposed estimator, and in the next next content you can see that your existing estimator that I have been taken to compare with my proposed estimator. So these are my existing estimator and proposed estimator which I have been carried out for my studies, and let us check the mean square error of the proposed estimator and existing estimator that I have been find by taking the expected value of that estimator value minus y bar, then take the square of this to then take the whole square of this value. Okay, so I have to find out the mean square error of my residue estimator and product estimator, which have been mentioned here. You can see that, and I have also find out the alpha optimum value in this case for the residue kinds of estimator and for the product kind of estimator. So apart from that, we have also find out the mean square error of that existing estimator that I have been considered, that is mean square error of T1, mean square error of T2, and mean square error of T3. Okay, so I have so now our study is to compare these two estimators, that is our traditional estimator with our proposed estimator. So let us come to the data sets parts that I have been considered. So in this content, you can see that for the theoretical comparison, the proposed estimator, yeah, sorry, I need to change it is typing mistake. So this will be the TR. TR is optimality condition is more efficient than existing estimator if and only if the following condition are both. Okay, so we know that if our mean square error of proposed estimator will be less as compared to our existing estimator, then we can say that the proposed estimator has been more reliable or more efficient or more sophisticated. We can say that. Okay. So that is why if these conditions are satisfied, we can see that simply our proposed estimator has more percentage. Our proposed estimator has more reliable as compared to other. So for this population, for this study, we have considered a data set by taking since 1967. Okay, so that the variables are where we have considered here. We can see that y, x, and z. Y is nothing but our number of female employees, and x is our number of female in service, and number of Z is nothing. Z is a number of educated females. So I have find out the number required parameter which which is necessary for my study. That is, you can see that your population, sample, capital N and S, and all things there which is required for my study. That actually I have been find out from the data sets, and I have used this value to compare my mean square error of the proposed estimator as well as our existing estimator, which will actually tells us to that which one is our best estimator. So by using this data set, I have find out the value of, I have find out the mean square error of proposed estimator and our existing estimator. So you can see that here our percent relative efficiency of estimator that have been found in this case. You can see that I have here four estimator, that is T1, T2, T3, and TR. So for T1 is nothing. T1 is our existing estimator 1, and T2 is also second existing estimator, and T3 is third existing estimator. Okay, so TR is our proposed estimator that we have proposed newly. So you can see that our proposed our percent relative efficiency of our proposed estimator is more as compared to our existing estimator, and we know that whenever a percent relative efficiency of a estimator is more, we can see that at the time the estimator has more reliable as compared to the considering estimator. So you can see that the proposed estimator has more percent relative efficiency in this case. We can say that our proposed estimator has more reliable as compared to the existing ones. So next slide, we have carried out a simulation study, which is our interest. And in this case, what we have did that the simulation study has been studied by generating random population of from a wide normal distribution. For this study, a random population of size 50,000 and 60,000 was generated for auxiliary variable x and z. Okay, so from standard bivariate normal distribution, using these auxiliary variables, the study variable y is generated by generating by using this condition, that is y is equal to xi plus zi plus a. Okay, this will help us to creating sample space in our programming, and it will help to simulating. It also helps to simulating the data into multiple times that we are actually considering. So from this population, for this population, two phase samples were generated by using three differential phases and second phases. As for population 1, 20% of 50,000 were considered for N1 selection, and then 50% of 10,000 has been considered for N2. Okay, and for on the same way, you can consider for 60,000 population, that is N capital N. By considering this value and taking this value, we are actually simulating this data into multiple times for better results. Okay, so for the each of the sample, various estimator were computed. The procedure were actually repeated 50,000 times, and the mean square error of the proposed estimator as well as our existing estimator has been found. Okay, so for this purpose, we have actually built nearly 210 codes in our programming to find out this value, and we are actually focusing on more interesting things like we are trying to currently operate these things in Python that we are looking forward, and we have find out the mean square error by using this simulation. So you can see that T1, T2, TR that we have been considered four types of estimator. So you can see that in the first case, the mean square error of this value, you can see that the mean square error of T1, T2, T3, and simply you can see that our proposed estimator has less mean square error, which you can see clearly. So from here, you can also say that our proposed estimator is more reliable or more convenient as compared to the traditional estimator. So these are my studies that I have been considered to show our proposed estimator is more reliable. So in the conclusion part, from two tables that I have been considered, it is observed that in table 1, the most proposed estimator gives more reliable results, more efficient results compared to the existing estimator. On the other hand, you can see that from the table 2, it is clear that the mean square error of our proposed estimator and other table of estimator has been compared. It is observed from the table 2 that the mean square error of our proposed estimator is minimum or in all simulated populations, and that I have been studied in this case. Okay, so these are my conclusion parts, and here's some references that I have been taken for my studies, and this is my overall work that I have been done in this case. So thank you.
So have you studied the effect of bias?
Yes, man, I have already checked this bias also due to some problem. I did not mention it here. So,
so your bias is the bias of suggested estimator are less?
Yes, bias of ratio estimator is less as compared to my traditional estimator. The most important thing is that we are also actually trying to focusing on more on programming language. We are also trying to incorporating these things into Python programming language that which are also going to be more interesting.
Because in most of the papers, what I have seen that in case of exponential estimators, they are efficient, but bias increase.
Okay.
So in your case, bias decrease or increase?
Ma'am, my bias has been decreased.
Okay, because as you use exponential type estimators, bias increase most of the time. So any question from the audience? So no question. Now let me thank Mr. Sunanda for the nice presentation. Thank you.
Thank you, madam.
Thank you. So now let me call upon the next speaker. The next is the quartile-based cumulative T-Salis entropy for maximum rank set sampling with unequal samples by Dr. David Chris Raju.
Yes, ma'am. Yes, ma'am. I present.
Yeah.
Can you hear?
Yeah. Please share your screen.
Okay, ma'am. Is it visible? Hello, ma'am. Can you see?
Yes, it is visible.
Good afternoon, everyone. The topic of my presentation is cumulative Salis entropy for maximum ranked set sampling with unequal samples using quantile function. So this is my content, and first we move on to introduction. So first we move on to understand what is ranked set sampling. So in ranked set sampling, what we will do is we will select n set of simple random sampling, and we will select from the first set the first one, and in the second set the second one, and in the nth set the nth one. It was first introduced by McIntyre, and he used it to estimate the mean pasture yield, and found that RSS is a more efficient sampling method than compared to the simple random sampling method. The various applications of RSS as given in different areas such as industrial statistics, environmental, etc. The PDF of the RSS of the ith order statistic is given in point number 4. And the maximum ranked set sampling was introduced by Biradar. And what we will do is we will select in the first set we will select only one sample, and we will select the first one, and in the second set we will select two sample, and we will find out the maximum of that, and we will select the second one, and in the nth set we will find the nth maximum of the sample set. It was used by Biradar to estimate the mean of exponential distribution, and showed that MRSSU is a better estimator compared to the SRS. And under the assumption of perfect judgment ranking, we can find out the probability density function as well as distribution function, which is given in the equation number 3 and 4, which is given in the equation number 1 and 2. And the number of samples that should be measured is n into n plus 1 by 2 if we need to have n samples. And now we move on to the Shannon entropy. The Shannon entropy is defined in equation number 3. One of the important property of Shannon entropy is that it is additive in nature, and it has revolutionized the information. It has introduced a new area called statistics mechanics. And although it has many advantages, the Shannon entropy have certain drawbacks, that it is very difficult to estimate, and it is always it will have negative values. So Rao et al. Introduced another version of cumulative residual entropy, which is given in equation number 5. It has many advantages over Shannon entropy, that it is always non-negative, and it can be easily computed using sample data. And Salis found out a non-additive generalization of Shannon entropy, which is given in equation number 6, where alpha is the entropic index, and when alpha tends to 1, the Salis entropy converges to the Shannon entropy. And when there are two independent random variables, the Salis entropy can be calculated using equation number 7. The applications and results of Salis entropy can be referred under the following paper, which is given in point number 4. Now, motivated by the wide applicability of the Salis entropy as well as the cumulative residual entropy, Sadi and Gupta introduced the cumulative version of Salis entropy, which is given in equation number 8. However, Rajesh and Sunoj introduced an alternative measure of cumulative residual Salis entropy, which is given in equation number 9. But the measure proposed by Rajesh and Sunoj, of course, has some important, interesting properties like simple relationship with other information and reliability measures compared to the cumulative Salis entropy. Now we move on to the quantile function. And it is well known that a probability distribution can be specified either by distribution function or by a quantile function. So in some cases or in some probability model, the distribution model or the distribution function do not have a closed form. In certain, in that model, we can use the quantile function. And so in the present paper, we introduce a quantile-based Salis entropy for maximum ranked set sampling and study its various properties. These are the various works that is under the field of ranked set sampling as well as entropy. Eskandar Sa et al. Considered the information measures of MRSSU in Shannon, Rennie, and Kullback-Leber information. Tahmasabi obtained some results on residual entropy for ranked set, and Rakab and Q considered the problem of information content of RSS data based on entropy measure. Although, if you think that all this work has been done in the distribution part, so a little work has been done on the quantile part. So that is the reason that we introduced this study. Now we move on to the second topic, that is quantile-based cumulative Salis entropy for maximum ranked set sampling. And before that, we need to introduce the quantile version of Shannon entropy, which is introduced by Shankaran and Sunoj, and it is given in equation number 11. The dynamic version of them is also proposed by them, which is given in equation number 2. And Krishnan et al. Proposed the quantile-based cumulative Salis entropy, which is given in equation number 13. And in equation number 14, we show the equation for the dynamic version, which is proposed by Krishnan et al. Now, in equation 15, we had defined the quantile-based cumulative Salis entropy for simple random sampling. And in equation number 17, we define the quantile-based cumulative Salis entropy for maximum ranked set sampling. And we call it as tau alpha XRS and tau alpha X MRSSU. In the theorem 1, we found out that for the Salis index 0 less than alpha less than 1, the information content proposed by the tau alpha X MRSSU is less than the tau alpha XRS. And we also found out the relation between the hazard quantile ordering between the tau alpha. If two random variables have a hazard quantile ordering, then if n alpha is an even number, we will have the the tau alpha X MRSSU is greater than tau alpha Y MRSSU, and vice versa for n alpha is an whole number. In the example 4, we found out the quantile-based Salis entropy for YMRSSU. If Y has the Y equal to Y has a transformation 1 by X, and the equation is given in example number 4. And in example 5, we used a power distribution, and we found out the tau alpha XRS and tau alpha XMRSSU in equation number 18 and equation number 19. And the difference between them is given in equation number 20. And by looking at the equation, we could find out that the lemma 3.1 is verified by simply looking at the equation. We had also used another example called Tucky lambda distribution. We found out tau alpha XRS and tau alpha XMRSSU in equation number 21 and 22. The difference between these two is obtained in equation number 23. And to elucidate the concept further, we had drawn the graph for 0 less than alpha less than 1. We could see that the difference is in the negative part, and for alpha greater than 1, it is in the positive part, which also confirms the theorem or lemma 3.1. Now we move on to the dynamic version of the quantile-based cumulative Salis entropy. The dynamic version was proposed by Krishnan et al., as we shown in the previous slide, and the corresponding quantile-based dynamic cumulative Salis entropy for Ma'am, hello.
Yes, yes.
Okay. Can I continue?
Yeah, please continue.
The corresponding quantile-based dynamic
Please,
cumulative.
try to finish within 2-3 minutes. Yeah?
Okay. It's given in equation number 24 and equation number 25. And in equation number 26 and 27, we find out the relations between the entropy of quantile based cumulative Salis entropy, and in equation number 28 we find out the derivative with respect to u, and in theorem 8 we show some characterization theorem. In the theorem 8 we show the characterization theorem of power distribution, and in corollary 9 we show the characterization result of the exponential distribution, and in theorem 10, 11, and 12, we found out the characterization using tau alpha x SRSN, the dynamic version of the quantile-based cumulative Salis entropy in SRS. And in theorem 13, we show the relationship between the quantile-based dynamic cumulative entropy and the XSRS, the SRS version and the MRSSU version. Now, in application, we found out that it is it is imperative to decide the size of the sample, but it can be seen that from the equation, it converges to a quantity 1 by alpha minus 1 when the sample size n reaches a certain value. This is because as n increases, the measure converges to 0. And we can say that the maximum information can be obtained by system will be at that sample point. That means if we further add sample point, the maximum information will be converges to 1 by alpha minus 1. And but in the case of SRS, when the integral value is greater than 1, there is a possibility that it will diverges to minus infinity. So the convergence or divergence of the tau alpha XRS depends upon the parameters of Q of P. And we had used Govindarajulu power and skew lambda distributions to show the concept, and we could see that for the different parameters, the sample sizes has been given. And this is next is conclusion. The paper introduced a quantile-based cumulative Salis entropy under MRSSU sample scheme. We also introduced the dynamic version, and we also derived some certain characterization. And the comparison between SR sample scheme and MRSS scheme is also been given in this paper. So this is my bibliography. Thank you.
Thank you so much. So have you, in the application part, have you applied for the real life data or?
It's an ongoing part. We are trying to do it in the theoretical one, and in the next work we will try to do it in the, we'll propose an estimator and we will try to do it in the real life.
So any question from the audience? So nice work, Mr. David.
Thank you, ma'am. Thank you.
Thank you so much for your presentation. So our next presentation is predictive estimation of variance through product estimator by Mr. Ajit Kumar Sabat. Are you there?
Yes, madam, I'm present.
Yeah, please
Yes, madam, I'm
share.
present.
Yeah, please share your screen.
Yes, madam. This one is visible. And this one is visible.
Your presentation is not visible. Yeah, now it is visible. Yeah.
Good afternoon to all. My topic is predictive estimation.
Just go back to the presentation. Just click on the presentation. Yeah, now it is fine.
My topic is predictive estimation of variance through product estimator, and that one will be presented by me, Ajit Kumar Sabat. And In this paper, we explore new estimation technique for estimating variance of the conventional product estimator under simple random sampling, assuming that the population mean and population variance of the auxiliary variable are known prior to sampling. Accordingly, we formulate some new variance estimator under classical as well as the predictive approach, and we test the capability of our estimator empirically by means of the simulation study in respect to bias, efficiency, coverage rate based on 95% confidence interval and stability. And in my introduction part, in population 1 to n, let y and x be denote the study variable and auxiliary variable, taking value yi and xi respectively on ith unit, and from 1 to n with the yi minus whole divided by n minus 1 and xx square summation I from xi minus x whole divided by n minus 1 be the population variance of y and x, and syx summation I varying from 1 to n yi minus y bar x into xi minus x bar whole divided by n minus 1 population covariance between y and x, and we consider a sample as of n units drawn from u according to simple random sampling without displacement method for the purpose of estimating the unknown mean of y bar. Define y bar equal to summation I varying from 1 to n yi by n, and x bar is equal to summation I varying from 1 to n xi by n as the sample means, and sy square equal to summation I varying from 1 to n yi minus y bar whole square whole divided by n minus 1, and xx square equal to summation I varying from 1 to I varying from 1 to I y xi minus x bar whole square whole divided by n minus 1 is the sample variance, and xy x is equal to summation I varying from 1 to n y minus y bar into xi minus x bar whole divided by minus 1 is the sample covariance. And here in this sample survey, the product method of estimation has received considerable attention when there is a negatively highly correlated between y and x. In this context, the traditional or conventional product estimator y bar that utilizes known value of x bar is defined by TP equal to y bar x bar whole divided by x bar, which is considerable efficiency gain over the direct estimator of y bar when beta yx is less than equal to minus 1 by 2r. And the given expression that one variance of TP that equal to n minus n divided by n plus 2 syx plus r square sx square, that will be equation 1, and from Cochrane 1973, my suggested estimation method rewrite the equation 1 variance of TP equal to n minus n divided by n sy square plus 2rs sx square beta yx by 2r, and my estimated variance of TP is that equal to n minus n divided by nn sy square plus 2r sx square and beta yx plus 1 by 2 r this one, and we get a equation for this one as n minus n divided by nn sy square eta cap s xx square, where eta cap is equal to 2r cap byx plus 1 by 2 r. And my we construct a new estimator. This one the proposed estimator of v, this one will be selection of sy square, this one v3 v4 v5 v6 and v, and we estimated the variance of tr in n minus n divided by nn sy square plus eta cap s square, and we got v cap v4 cap v5 cap v6 cap and v7 cap. And for performance the report has been made here to compare the performance of the proposed estimator empirically by carrying out the simulation study by taking bias expected value of v minus vtp, and standard will be of v, this one will be plus root over of expected value square minus expected value of vi whole square, and average rate based 95% confidence interval, and coefficient based
Mr. Ajit had disconnected, so let's wait for 1 minute. So our last presentation will be 124 log type ratio estimator of population mean in stratified sampling using calibration approach by Meenakshi Kochari.
Yes, ma'am. Hello. Yes,
Yeah.
ma'am. Present.
Yeah.
Yes, ma'am.
Yeah. Please share your screen.
Okay, ma'am. Hello, ma'am. Is it visible?
Yes, it is visible.
Okay, ma'am. Good afternoon, everyone. I'm research scholar Meenakshi Kochari. I'm doing my PhD under guidance of Dr. Neha, ma'am. Now, my topic for today's presentation is log type ratio estimator of population mean stratified sampling using calibration approach. What is calibration? Calibration, it can be just defined as the method of adjusting the weights in survey sampling in order to just estimate the population parameters like mean, total, and etc. of the auxiliary variables. The revolutionary article under this calibration approach, it was given by Devlin and Sandal in 1992, and they just proposed the more good estimator comparison to the existing traditional estimator like Horvitz and Thompson. The main purpose was to just use the auxiliary information and obtain approximately unbiased estimator. Now, it was the estimator, the proposed estimator was YCAP-DS, Devlin and Sandal for the Horvitz and Thompson estimator. The calibrated weights are given as, and the process was to just minimize the chi-square type distance function, that is summation wi minus di whole square upon di qi, subject to some calibration constraint. And here they use the calibration constraint as population total, and the choice of the qi on it depends, the proposed estimate depends on the choice of the qi, and after following the procedure of minimization, this leads to the calibrated weight as wi, and we get the proposed calibrated estimator. Now, for the study purpose, we have used the Tracy et al. Estimator given by Tracy and all in 2003. What they have done, they have just proposed the calibrated estimator under stratified random sampling, and they have extended the result for stratified double also, and subject to the calibration constraint in which they have used the mean and variance of the auxiliary variables. And by making use of these calibration constraint and minimizing the chi-square distance type function, they got the proposed estimator, and where beta cap T1 and beta cap T2 in this form of the regression type estimator. Now, second estimator for the study purpose we have used is the Singh et al. In 2003. What they have done, they have in fact considered simpler form of calibration constraint, means they have used mean as the calibration constraint, and after applying this calibration constraint, they just found the proposed estimator as y bar m, subject to this calibration constraint as mean. Now, the proposed estimator, what we have done here is we have just considered in this strength, what we have done, we have applied this technique under the stratified random sampling. Yes, we have divided the heterogeneous population into homogeneous subgroups. These are called the stratas, such that the sum of all the stratas is equal to the capital N, that is a population size. And from each strata, we just draw a simple random sampling without replacement, such that the sum of all the samples from each strata is equal to the required sample size N. Yeah, Y is the study variable and X is the auxiliary variable, and they are positively correlated, and WH is the stratum weight and FH is the fraction weight. Now, the proposed estimator here, y bar RL is equal to summation omega h y bar RH, where y bar RH is the estimator for the ratio. And now, subject to the calibration, we have minimizing the chi-square type distance function, that is summation omega h minus WH whole square upon WH subject to the following calibration constraint. One is, first constraint is summation omega h is equal to summation WH, and second one is using the log, means Tracy used the variance and mean, and Singh used mean. We have used here is the log of mean, logarithmic function we have used. And after applying the process, the Lagrangian function is given as this, and where this lambda1 and lambda2 are the Lagrange's multiplier. And after just differentiating this, we will just obtain the optimum calibrated weight as omega h. This is the optimum calibrated weight. And after putting this calibrated weight in the proposed estimator, our proposed estimator gets the form as summation WH y bar RH plus beta cap RL into summation WH cap into capital log x bar h minus log x small x bar h, where beta cap RL is equal to summation WHQH into summation WHQH y bar h. And here the form depends on the various values of QH. Generally, we take QH is equal to but it depends on our choice. We can take any value of QH. Like here for QH is equal to 1, the estimator gets the form as this, where where in beta cap we have put the value of QH as 1. Now for QH is equal to 1 upon mean, here the form of the proposed estimator gets this form. Here we can put any value. For 1 upon log n, log x bar h we have put. Now for the simulation study purpose.
Just a minute, Nakshi. Mr. Ajit, you can continue after finishing this presentation. Okay?
Yes, madam. Yes, madam. Yes, madam. Some network problem is there. Sorry, madam.
Yeah, you can continue after this. Yeah, continue, Meenakshi.
Okay, thank you, ma'am. Now, for the simulation study purpose, we have used here the real population, and the real population used here is MU28 population that is given in Sandal Appendix like 2003. It comprises of 284 units that has been divided into varying stratas, means 8 stratas of varying sizes, and X and Y are the Y is the study variable and X is the auxiliary variable. Now, following the technique of simple random sampling without replacement, we have just drawn the sample from each stratum using proportional allocation. That is, small nh is directly proportional to the capital NH. Now, using the R software, we have generated a 25,000 samples, and in the description of the population for the real population is as follows. Here X, this is the auxiliary variable is REV84, that is the real state value according to 1984 assessment, and Y is the study variable, that is the RMT85, that is revenues from 1985 municipal taxation, and the description of X and Y is this. Now this is the plotting between all the stratas, various stratas of the real population, that is the 8 stratas. Now for the empirical study, we have just applied this formula of this is the percentage and relative bias, and this is the percentage relative root mean square error for 25,000 samples generated. There trace TR is the Tracy one, S is the Singh one, and R is for the ratio. Tracy ratio we have considered, and SR is for the Singh ratio we have considered, and then the RL is our proposed estimator of log type in case of ratio. Now this table 1 depicts the percentage absolute relative bias for the real data set. That's it. This is for varying sizes of sample, varying sample sizes, and this table 2 depicts the percentage relative root mean square error. In this table, it shows that as we are increasing the sample size, our RRMSC is decreasing, and in comparison to all the estimator, we are getting a very good RRMSC, that is the percentage relative root mean square error. Now for the artificial, that was for the real population. Now for the artificial population, what we have done, we have just generated an exponential, using the exponential distribution, we have generated a population of size 3000 for 3 stratas. And again, we are following the using the simple random sampling without replacement. We have just drawn the sample from each strata, and the Y variable, that is the variable of interest, that is the study variable, we have generated using this model X1, X2, and X3 for all these stratas using the exponential distribution. Now, after just getting the values, we have just plotted this is the relative bias, absolute relative bias for the artificial data set. And this one is the percentage relative root mean square error. Again, this table is showing that as we are increasing sample size, the RRMSC is decreasing. And for comparison to all the other estimators, that is the existing estimators, our RRMSC, that is Y bar RL, is coming out very good. Thus, this concludes our study, that using the simulation study on both the data set, that is on the real one, MU284, and the artificial one, exponential. Our proposed estimator is performing very good as compared to the existing estimators that we have considered, Tracy and Singh. And as we are increasing the sample size, our RRMSC is decreasing. and efficiency is coming out good. Now, these are the references which we have considered for the study. Thank you.
Any questions? I used to ask so many questions to her daily. So anybody from the audience can ask any question. Dr. Nirupma, do you have any question?
No, madam, thank you. It's a nice presentation. I think your research scholar.
Yeah. So I used to ask so many questions daily, so I don't want to ask today.
Actually, little bit I skip that, so that's a problem. So I can ask any question. Okay, thank you, ma'am.
So thank you, Meenakshi.
Thank you, ma'am.
Thank you for your presentation.
Thank you, ma'am.
Okay, so now, Ajit, you can share your presentation.
Yes, ma'am. Yes, ma'am. Madam, now this one is visible.
Your presentation is not visible. Just come out the Zoom meeting and yeah, share your PPT.
Yes, madam, got it.
Yeah.
Just 1 minute. Madam, this one right now. Hello, madam.
Yeah, now your presentation is visible.
Yes, madam. Actually, I am continued from this. We construct the new estimator.
Yes.
This one, my proposed estimator VTR will be V3, V4, V5, V6, and V7 selection of the SY square, and we calculate VTR cap that is equal to n minus n divided by nn. SY square plus eta cap SX square, and we got V3 cap, V4 cap, V5, V6, and V7 cap. And my performance of the proposed estimator for calculating bias, we use expected value of VI cap minus VTP, and standard error root over of expected value of VI square minus expected value of VI cap whole square, and the coverage rate and the coefficient of variation CB VI cap equal to 100 into expected value of VI minus VTR whole square divided by VTG whole square. And on the description of this the simulation study, we use the data of 25. We use data of 25 bivariate natural population in which the variables of y and x are negatively correlated, and the source of size the population is capital N, and definitions of y and x for these population are presented in table 2 in the next slide. We consider 3000 independent sample of size n equal to 2, 4, 6, and 8 drawn without replacement for each population when NCN is greater than equal to 3000. Otherwise, all NCN possible sample are considered based on the observed value of y and x. Each sample, the estimated TP and VI cap I varying from 0 to 7 are calculated. And here my table 2 represents the population under study, and here we have a capital N value of 35, 35, 32, 32 like that for 25 for population number 1 to 25. And we calculate the bias of my variance estimator for sample size n equal to 4 and 6 here, and like we calculate the standard deviation standard error of the variance estimator for sample size n equal to 4 and 6, and we calculate the coverage rate for n equal to 4 and 6 also. And we also calculate the coefficient of variation. That one is my reference for showing the table in presentation. And we may finding that the base finding on the bias from the table, computed value on the bias of the competing estimators displayed on table 3 reveal that for n equal to 4, the conventional estimator V0 cap is the best, is the least bias in 12 population, whereas V6 cap and V7 are respectively the same in 4 and 8 population. 4 and 8 populations, a similar trend was also noticed for n equal to sample size n equal to 2, but for n equal to 6, V7 cap emerges out as the best performance, as it will be decidedly the least bias and second least bias and third least bias in 12, 7 and 2 population respectively. On the other hand, V6 cap turns out as the second best performer, as it will be the least bias and second least bias and third least bias in 6, 4 and 6 cases respectively. And when we and in from the standard error findings from the summarized simulated results given in table 4, we see that standard error of all estimator with few exceptions usually decrease with enlargement of the sample size over on the average of V6 cap, which emerges as the best performer because on the magnitude of standard error it occupies the first, second and third position in 10, 11 and 3 cases respectively for n equal to 4 and in 14, 9 and 2 cases respectively for n equal to 6. And for findings on the coverage rate from the summarized simulated result given in table 4, we see that the standard of all estimator with few exceptions usually decrease with enlargement of the sample size on the average V6 cap, which emerges as the best performer because of the magnitude of standard error. It occupies the first, second and third position in 10, 11, 10 and 3 cases respectively for n equal to 4 and in 14, 9 and 2 cases respectively. And for n equal to 6, on the same ground, we identify V7 cap and V0 cap as the second and third best performer, which are the most efficient in 7 and 5 population for n equal to 4 and 8 and 3 population for n equal to 6 respectively. And for finding coefficient of variation, the results given in table 6 reveal that the behaviors of the estimator in respect of coefficient of variation are more or less similar to those of the standard error. And this one is my conclusion. Findings of the simulation study clearly indicate that no estimator is uniformly better than the others on the ground of all the 4 effort means our bias, relative efficiency, standard error and coverage rate performance criteria. However, analysis of the simulation results shows that out of 8 comparable estimator, overall performance of only 3 estimator through V0 cap, V6 cap and V7 cap may be taken into consideration. This one is my conclusion and some references I will taking here for my this paper work. Thank you.
Any question from the audience? Okay, thank you, Ajit. Nice presentation. You have considered so many population for your study.
Thank you, ma'am.
Okay. So now I would like to thank all the presenters for sharing their research work with us. I also thank you on the behalf of organizing committee and my personal behalf. All presentations are very nice and very informative. Thank you all.
Thank you, ma'am.
Thank you, ma'am.
Thank you for chairing the session. Thank you, ma'am.
Thank you. The next session will start at 2:30 after the lunch break.
Thank you, madam.
Thank you, madam.
Chalo.
Good afternoon. Good afternoon, all of you. I think both the speakers are have joined.
Yes.
Due to some disturbance, sir couldn't join. The chairperson, Professor V. Pandit Garu, could not join. So I am starting the session. I myself am Dr. G. Sirisha from Department of Statistics, Osmania University. The first speaker is Dr. Isha Pathik Das.
Yeah, hello.
Let me introduce Dr. Isha Pathik Das. He is Assistant Professor from Department of Mathematics and Statistics, Indian Institute of Technology, Tirupati, Andhra Pradesh. He has completed his postdoctoral research in Duke University, USA. PhD he has awarded from IIT, Indian Institute of Technology, Bombay. He has done his MSc also from IIT Kharagpur. Then his research areas are generalized linear models, machine learning, clinical trials, design of experiments, multivariate distributions, and so on. He has published 5 papers in international journals. Thank you, sir. And now I request sir to start the presentation.
Thank you, madam, for introducing me. I thank you, the organizer also, for giving me opportunity for presenting here. I'll share the presentation file. 1 minute.
So you can start the presentation.
Yes. I'm sharing the presentation. Yes. Yeah. Okay. I think it is visible. I just share. Now you can see I have a slide. So is it visible, this slide?
Yes.
I have shared. Just
now it is visible.
Yeah. Thank you, ma'am. Thank you for confirming. So the topic here I am going to present. It is multiple inflated multivariate negative binomial regression using copula. So this is a research work we are doing. Some other co-authors also there. I am presenting here. So now the goal of this research work is to provide a method of regression for multiple inflated multivariate negative binomial responses. So first, one by one, we'll discuss the terminology. So basically, some of the students also may be attending. So keeping in mind, I will discuss very basic things also here. So what is count data models? Studies involving count data appear frequently in society, social and natural sciences. Moreover, this data often has a non-normal structure, making it difficult to model. We usually model such data assuming that the responses follow Poisson distribution or negative binomial distribution. So we'll discuss in details. So what is count data? So for example, here the number of aircraft or road accidents in any time interval. Suppose if we consider number of road accidents, so this is known as count data. Number of arrivals in any service facility like at an ATM, bank, railway station, petrol pump, the number of patients in a doctor clinic, the number of visitors to a mall exhibition, the number of services completed per unit time at a bank or any other service facility. So these are some of the examples. So where we count like a number of something, so then we say it is a count responses. So that we want to model. So you may all know it is a Poisson distribution. A random variable x is called a Poisson random variable with parameter lambda greater than 0 if its probability mass function is given by this. So this is some of the probability mass function for parameter if lambda equal to 1 and lambda equal to 4. So here something you can notice that whatever the values of lambda, there is this distribution. Actually, if data is unimodal, the mode is 1 only. And also if you make a smooth curve, because these are discrete, just we are joining between the points, and then we see that, so this is somewhere it is a mode, and it is increasing or decreasing after that. So now if you consider a negative binomial distribution also to model such data, the random variable x is called a negative binomial random variate with parameter rp. If its probability mass function is given by this, if you see this curve also, here also similarly, it is also unimodal for different values of parameter p equal to 0.2 this red color, p equal to 0.5 this green color, and p equal to 0.8 this blue color. But here also it is unimodal, and around the mode this frequency just slowly increasing or decreasing. So there is no such cases that suddenly it is increased or decreased, or again it is increased. That means bimodal case we cannot get for any kind of parameter here also. So now sometimes we get some data, we say count data with excess zeros. So many real world phenomena produces counts that are almost always zero. For example, number of times a machine fails is month. The number of Earth-like exoplanets discovered per month. The number of billionaires living in every single city in the world. So if you consider this kind of data, then you will see that here the number of Earth-like exoplanets discovered per month from 2011 to 2017. You can see that 84 it is 0. Then count 1 is 10, 2 is 1, and 3 is 1. So here this frequency of 0 is much higher than the other values. So if you model using usual Poisson or negative binomial, the any parameter value, it may not be appropriate for such kind data, such type of data. So then researchers propose zero inflated model. Such data are hard to deal with using traditional models for count data. This is because such data sets contains more number of zero valued counts than what one would expect to observe using the traditional models probability distribution. Several researchers modified the existing default distribution and proposed a zero inflated model to deal with such data. So actually this kind of data they consider, researcher usually proposed in different ways. One such method is consider a mixture model, mixture distribution. One responses that is coming from for the zero only it is observing, and another for the Poisson. So this kind of mixture it can work. So this is a zero inflated model we say. But sometimes we can get some multiple inflated count data also. Many of these data have more than one inflation point centered around zero. If the data is multivariate, then we need to modify existing distribution to model such data. Here we propose a multiple inflated negative binomial regression using a copula. So this is our goal here whenever these multiple inflation points exist in a data. So let us consider one such example here. You can see that a Dr. US data set, this is from this R package, containing a study done at Australian hospital from 1977 to 1978. Two variables here it is considered. One is act days, the number of days of reduced activities in past 2 weeks due to illness or injury. And then another variable is illness, the number of days a given patient was sick in the previous 2 weeks. The total number of observations n is 5190. So here there are two variables, and these two variables may be correlated. So then we cannot consider they are independently distributed. We have to find the multivariate distribution. But this data, if you see here, this data set is given act days in cross illness. Then you can see that this frequency, this 00 cell and 01 cell, these two cells are much more higher than the other cell. Other values are like this 1543, it is 1375. Then this is 763, 71, 420. So other values are very close to 1 or 0, but these two cells are very much higher than the other cells. So then we can think it is a doubly inflated, not like zero inflated only. It is a two inflations are there. Two cells are more higher observation. Frequency is higher than the other cells. So another example, it is a CPS 91 data set, world rich package in R, containing study on work hours of couples. The two variables are here. HUHRS, it is husband's weekly hours, and this is Y2 is the wife's weekly hours. So their covariate we can consider education, age, ethnicity, and income. So these are the independent variable. We can see how they are related. First, we have to think that how Y1, Y2 are correlated. They are the hours, weekly hours of work hours for the husband or wife. So this is the data for a couple. So there may be a relation, and this may be related to the they may be correlated the responses, and also these responses may be dependent on these independent variables that we want to study here. Now, the total number of observation in this data is 5,634, and this data, it is not explicitly given here. Only the highest count. So how 10 points with highest count it is given. So this point 40,0, this is 851. 40,40, this point it is 781. Then 0,0468, 0,40 it is 214, and these values are less than these values. So we can consider that then we have to model. It is a multiple inflated data. It looks like it may be zero inflated. You can consider it may be doubly inflated. It may be, it is not zero inflated, it is one inflation. This point is not zero. So 0, 0 is this 468. So we can consider inflation point 3 also, inflation point 4 also. But we don't know which which model will provide a best fit. We have to first introduce how to model this kind of data, because it does not exist in the literature. We are here trying to propose to model such data. So if you model this data using usual multivariate negative binomial distribution using a cupula, then it will be ignored that some of the cells are have more number of data points than the others. So a multivariate distribution for count data. So dependent multivariate count data can be modeled by multivariate Poisson or negative binomial distribution. Models have to be updated if some of the cells are much larger than other cells. The above data contains inflation in multiple cells. We need to find an appropriate model addressing the problem of inflation. So that is the here we are going to trying to introduce. So let us discuss some of the basic how to find the multivariate distribution function using a cupula. So cupula, some of you may have already studied the cupula. Cupula is a function, is said to be, it is a function from q dimensional space 0, 1 cross 0, 1 cross q times 2, 0, 1 is said to be q dimensional cupula if any value, suppose y is a vector in the q dimension, then the yj is the jth coordinate of the vector y. Any value belongs to 0, 1, or some j belongs to 1 to q. If you take this function, this value will be exactly equal to yj if this value is yj. And if you consider y equal to this value in q dimensional space, at one point is 0, any z coordinate is 0, so then this cupula function will be 0. And not only that, if we consider 2 points like this, where one point is less than equal to another, the coordinate, two coordinate actually, coordinate wise it is ordered. So then if you consider this function, it may be considered as a volume under this function c of this point, 2 points under these 2 points. So then this will be equator equal to 0. So if these three conditions are satisfied by C, then it is called the two-dimensional cupula. So now why cupula is important? Cupula is important because of this Clark's theorem. So Clark's theorem says that suppose y is a q-dimensional random variable having the joint CDF f and the marginal CDF jth component of yj is fj. So suppose usually we know the marginal distribution function of Poisson, marginal distribution function of negative binomial distribution. But if we say that suppose there are correlated responses, count responses, what will be the multivariate multivariate distribution, Poisson distribution function? So that is not it usually exists as a standard form. Like normal distribution, we have the multivariate normal distribution. For a binomial case, we also have the multivariate extension, that is multinomial distribution. But for the Poisson or negative binomial, there are many approaches to find the multivariate distribution function. Here one approach to use this cupula's function. This cupula function says that if f is a joint distribution function and fj is the jth component of this variable random vector and fj is the marginal distribution function, then there exists a q-dimensional cupula sees that C such that you can write this joint distribution function as the function of their marginal, like C of F1 Y1, C of F2 Y2, and FQ YK. So this is this class theorem. And also not only that, it is unique if it is continuous, these distribution functions are continuous, but if it is not continuous, then C can be uniquely determined in the Q-dimensional space. For example, in the Poisson and negative binomial cases, these are discrete. So we can uniquely determine in this space range of F1 cross range of F2 cross range of FQ. So here we give one example. A cuvariate Gaussian cupola is defined by this. So here CR of U1 into UK, it is phi r is the cumulative distribution function. It is multivariate cumulative distribution, multivariate normal distribution function, cumulative distribution function of multivariate normal with some mean 0, 0 and the correlation matrix R. And this capital this phi, this is the CDF of this standard normal variant, normal 0, 1. So then if you write in this way, U1, U2, UK, CR of, it is phi r of phi inverse of U1, phi inverse of U2, and phi inverse of UK, the UQ, then phi is the CDF of the standard normal variant. So then we get this copula. This copula is known as Gaussian copula. So, but here, if you want to model in using this Gaussian copula, then this correlation matrix, suppose it is Q dimension, then this unknown will be this much. So Q into Q minus 1 by 2. So it is very higher, and the number of unknown elements actually increasing with Q exponentially. So for this reason, number of parameters will be very large, and we have to estimate from the data. So instead of that, some researchers proposed to use some kind of particular correlation matrix. For example, ER1 structure, it is proposed by this Changanti 1997. This ij element of the correlation R under this structure is given by Rij, R to the power absolute value was I minus j, where R belongs to 0, 1. And the equicorrelation structure, it is proposed by this author Olkin and Pratt 1958. The IQ, the identity matrix of order Q cross Q, then the equicorrelation structure is given by this. So sometimes we can use this kind of correlation structure to model using Gaussian copula also. So here some curve is, it is given a bivariate Gaussian copula density function. And now we'll show how to find a multivariate joint distribution function using a copula. So this Clark's theorem, it says that whenever you have some marginal distribution functions and a joint distribution function, there exists a C satisfying this relation. Now we can suppose we don't have this multivariate distribution function. For example, in negative binomial distribution or Poisson distribution, we don't have usually the standard form of the multivariate Poisson distribution or multivariate negative binomial distribution, because if the data are correlated, we cannot assume that they are independent and multiply the marginal distribution to find the multivariate distribution function. We cannot do always. For this reason, so we can take a copula, and then using this copula we can find this multivariate distribution function. So here it is exactly, it is done here. So a joint CDF of Y from its marginal CDF Fj, it is given by this. So here we can use this Gaussian copula, but you can use any other copula also. For example, here we have used Gaussian copula. Suppose these marginal distribution function, these are known to us, and then all these values will be known to us, and then we can get the multivariate distribution function of the suppose if you use this F1, F2, FQ, these are negative binomial, then this we will get a multivariate negative binomial distribution. If you use a Poisson marginal, then we will get a multivariate Poisson distribution function. So then how to get this probability mass function? As CDF is known, so then with using this formula, we can get the probability mass function for this multivariate probability mass function for this random vector. So this is the from Clark's theorem we can do this. So now, for example, if we use negative binomial distribution as a marginal, suppose n1, n2, nq, we q random variables with each ni has negative binomial distribution with parameter si and pi, then the probability mass function of ni is given by this. So we know that this is the probability mass function for univariate negative binomial distribution. Then we can derive CDF of ni from this probability mass function above. So because hello, any questions? Hello. Okay. So I hope you are following, and if you have any question, you can stop me or you can ask also. So basically this is the probability mass function. Also, if we take this sum up to the value where we want to get the CDF, CDF probability distribution function, we can get that. Using this CDF marginal, we can use this method here using this relationship that we got from the Clark's theorem. We can find the multivariate probability mass function for the negative binomial distribution. So this multivariate negative binomial distribution, random variate, we get probability mass function. So these are basically extensive computational techniques. So, but we can use here in our data set where it may be very appropriate to use this kind of models. So here are some bivariate joint negative binomial distribution curve is given. This is CDF actually. The bivariate negative binomial probability mass function using Gaussian cupola. It is given here. So now the question is that up to this actually we it is exist in literature. Here we are improving to accommodate the nature of the data we have, that is the inflation, multiple inflation point in the data. So how to do that? So multiple inflated distributions. Here we are taking a mixture of two distributions. One is the jet, this random variate. It is a multinomial distribution function. The multiple inflated multivariate distribution is constructed using the latent variate jet, having the probability mass function this. So it has, yeah.
Excuse me, sir. Isha Patil, sir.
Yes, yes, yeah.
Try to conclude within 5 minutes, sir.
Okay, yeah, sure, yes, yes. So,
Time, sir.
yes.
5 minutes, please.
Yeah, within 5 minutes I will complete that. Yeah. So here we have considered this. Suppose there are m inflation points and with probability P1, P2, Pm, and then these inflation points are generating with this value, and the if z is equal to 0, then it is coming from the multivariate negative binomial distribution. If you consider that, so then using this conditional probability mass function, we have derived how to find this inflated multiple inflated multivariate random variate here. So these are all the usual technique of conditional distribution. From conditional distribution we get this joint distribution, and then we take this sum to get the only multiple inflated multivariate random variable probability mass function. So it is given here. So then here one curve is given for doubly inflated bivariate negative binomial distribution function. Here two inflation points are given, 0, 1 and 7, 2 are the two inflation point. From this curve we get that. So then we can find the marginal distribution function. If we take the sum of the other variable, then we can get the multiple inflated marginal distribution function yj here. And these are the curve here, it is given, and then we can find the expected value of yj. This expected value of yj is, it is nothing but this value lambda j, this is related with this, and this mu j, this is expected value of the negative binomial marginal random variable. It is actually related with this relation. So now we want to model the regression. Suppose we have some data yi and xi, then we take a log link function to relate the linear predictor, and then this from this relation, this mu j, we will get this relation also, and also we have to estimate this probability, this p1, p2, pm. So that also we can model in this multivariate logistic regression model. So we have done in our example, we have initially we discussed. So there are 5,000 data sets, 634 data set. This is husband hours and wife hours, and these are the explanatory variables. And we consider 5 models. So where M0 model is that usual multivariate negative binomial regression model using the copula without considering the inflation points, and M1 is that we consider 1 inflation point in the data, M2 is that 2 inflation point in the data. Similarly, 4 is that M4 is that 4 inflation points in the data. So we consider this model M0 here. You can see that no inflation point, only there are bivariate. So 2 linear predictors are there, and there are 2 independent variables. So these many parameters are there, and here these maximum likelihood estimates are given, and the EIC values also and log likelihood values also it is computed. And then we consider this model 1 inflation point. So 1 p probability we have to estimate. So this is the linear predictor we consider, and the similar linear predictor for the expected values of eta 1x and eta 2x for lambda 1 and lambda 2 also. And then this is the maximum likelihood estimate, and the EIC value is given here. And the model 2 is 2 inflation points we consider, and this is the estimated values. And if you consider model 3, there are 3 inflation points and 3 linear predictors are given. And similarly, these parameters are estimated using maximal likelihood estimation technique. And model 4 also we consider here 4 inflation points are considered in the model. So then this P1, P2, P3, and P4 is estimated using these linear predictors. And then these are the estimated values. Now, if you compare the AIC values and log likelihood values and difference of their deviances also, we see that this model 4 provides significantly better fit than the other models. So this is the conclusion. We studied the regression method for multivariate count data having inflation in the multiple cells. A regression method is provided for multiple multivariate negative binomial random variable. We fit 5 different models to real data and observe that model 4 provides a significantly better fit than other models. So actually, whenever we did not have this kind of models to fit this data, we usually fit the multivariate negative binomial distribution or multivariate Poisson distribution using copula, like one copula. So here we see that if you use this, if you address the problem of inflation points in the data, and if you modify our model, and we see that our model provides significantly better fit. Hence, a multiple inflated multivariate negative binomial model may be used to have a significantly better fit in the presence of numerous inflation points in the data. So that can be used when if you see a count data have inflation points. So these are the references. Okay. So hope you have some of you may have followed the topic here we covered, try to explain. So if you have any questions, you can ask.
Thank you, sir, for explaining new method regression models with respect to the multiple count data. You have given a even illustrated with respect to good examples you have considered. Thank you, sir.
Yeah, thank you, ma'am. Thank you, ma'am.
Now, I want to introduce Dr. K.K. Jose Kanichukattu. He is the Honorable Director of School of Mathematics and Statistics, School of Data Analytics at Mahatma Gandhi University, Kottayam, and his areas of specializations are stochastic processes, time series modeling, multivariate statistical methods, design of experiments, statistical inference, queuing theory, matrix algebra, distribution theory, probability theory, etc. He has been awarded with the best principal. He has got many awards like Best Principal Award, then Srimati Indira Gandhi Shuddhodhavana Award and Rajiv Gandhi Shiromani Award, then elected as Fellow of the Royal Statistical Society. He also got Global Achievers Award. He is a member of Statistical Society UK, then International Statistical Institute Netherlands, Indian Society for Medical Statistics, and so forth. He has he has guided 25 PhD students, 2 research projects, and he has authorized 14 books, 150 research papers he has published. Sir, thank you for accepting our invitation. Now, sir, you can start your presentation, sir.
So thank you, madam. Thank you. Hello, you can hear? Hello, it's audible?
Yes,
hello.
Sir.
Okay.
Yes, sir.
Share the slide. Can see my slides?
No, sir. Right. And now we can see, sir.
Is coming?
Yes, sir. Now we can see, sir.
Can see it?
Yes, sir.
Okay. So So my topic of the present talk is COVID-19 epidemic, statistical modeling, forecasting, and risk analysis. And I'm certainly grateful to the organizers, Professor Jayasri and Professor, all the professors, Professor Rajeshwar Reddy, Professor N. Balakrishna, and the head of the department, and all others for giving this opportunity. So thank you. I will make the presentation. So in the late 2019, a disease outbreak emerged in a city called Wuhan in China, and the culprit was a certain strain
Excuse
called
me, sir.
coronavirus disease.
Excuse me, sir.
COVID-19.
Excuse me,
This
sir.
virus has been identified to cause fever, cough, shortness of breath.
Excuse me, sir.
Hello?
You need to present within half an hour, sir.
It's not visible. I am actually trying.
We have time up till 3:40, sir.
It's
visible.
Visible.
Yeah.
It's visible, sir.
Yeah, this is visible. Introduction page is visible.
Okay. I'm trying. And the virus has been identified to cause fever, cough, shortness of breath, etc. All those things, you know. A family of coronaviruses that cause disease in humans and animals, ranging from the common cold to more severe diseases. Although only 7 coronaviruses are known to cause disease in humans, 3 of these, COVID-19 included, can cause a much severe infection and some fatal to humans. The other 2 were SARS and the Middle East Respiratory Syndrome, or MERS, originated decades ago, so in Saudi Arabia. So like MERS and SARS, COVID-19 is a zoonotic virus and believed to be originated from bats transmitted to humans. In comparison with the SARS, MERS, and the COVID-19 appears to be less deadly. However, the World Health Organization reported that it has already infected and killed more people than its predecessors. Also, COVID-19 spreads much faster than SARS and MERS. It only took over a month before it surpassed the number of cases recorded by the SARS outbreak in 2012. According to WHO, it only took 67 days from the beginning of the outbreak in China last December 2019 for the virus to infect the virus, the first 1 lakh people worldwide. As of 25th March of 2020, sister, the cumulative total of 3,72,000 confirmed cases were there, and more than 16,000 deaths. And all these were actually history, and we know the number of deaths crossed about 5 lakhs. Now, last 30 years, or the 2020, 30th of January, WHO characterized COVID-19 as a public health emergency of international concern and urged countries to put in place strong measures to detect disease early, isolate and treat cases, trace contacts, and promote social distancing measures commensurate with the risk. In response, the world implemented its actions to reduce the spread of the virus. Limitations on mobility, social distancing, and self-quarantine have been applied. And we know the national lockout also in India for about 2 months. Moreover, health institutions advised people to practice good hygiene to keep from being infected. All these efforts have been made to reduce the transmission rate of the virus. For the time being, COVID-19 infection is still on the rise. Government and research institutions scrambled to seek antiviral treatment and vaccines to combat the disease. And all these were history, and now we are having control over the disease in the national and international level. And different models were applied to model, different mathematical as well as statistical models were applied to study the dynamics of the growth of this model, of this species. And the first one was actually the most commonly used epidemic model is SIR model. SIR model is a compartmental model in which individuals are separated into compartments based on their infections status and track the corresponding population sizes. Here S actually means susceptible, and I means infectious, and R means recover. Susceptible is the group of people who are vulnerable to exposure with infectious people. Infected are those with the disease and can transmit it to the susceptible. Recovered are those who recovered from the disease, developed immunity, and not susceptible to the same illness anymore. And beta is a transmission parameter, which is the average number of individuals that one infected individual will infect per time unit. It is determined by the chance of contact and the probability of disease transmission. Gamma is the rate of recovery in a specific period. And dx, the average time period during which an infected individual remain infectious, which is derived from gamma into d. And d is actually 1 upon gamma. And the ratio R0, that is beta by gamma, that is the basic reproduction factor, production number, and R is the average number. And we are having 3 differential equations in the SIR model. ds by dt equal to minus of dt into s, dt by di by dt equal to minus beta into I into s minus gamma I, dr by dt equal to gamma I. And you can solve this. Actually, the solution is easy to obtain, and the results are available in the websites. So we can use R software to estimate the parameters. Now, as far as this model is concerned, so certain modifications were also made by different statisticians. Among the models susceptible, exposed, and infection and recover, that is SEIR model has attracted more importance, and which has proved to be a more realistic one. And certainly along with that, many other models were also considered, like the agent-based models and curve fitting, statistical logistic growth models due to the exponential nature of growth of the epidemic, or extrapolation models are commonly adopted using different biological and social processes. All such models were used here in the COVID case also. Especially the logistic growth curve model could be relevant for short-term projection, while SIR models could be useful to estimate the maximum number of active cases and the peak time of attaining it. Though the SIR model is used widely in COVID-19, there is not much information about how the SIR model performed in China and other countries where the pandemic is stabilizing or indicating a declining trend. So therefore, it is essential to validate the SIR model. And few researchers have used the exponential growth model to predict the number of cumulative cases, and that also proved to be true in the beginning, in the initial stages. But these models do not have an upper bound and therefore does not get stabilized, rather likely to go on increasing. So in this scenario, the logistic growth models are better preferred option. And Chowdhury 2020 had predicted the estimated cases very early in 2020 April, some 2 years back. So in the beginning stages, using time series models also. However, it was found to be a gross underestimation. In spite of the limitations, considering the unprecedented nature of the pandemic, uncertainties about the disease, and the need for urgent but appropriate social, economic, and public health responses, accurate forecasting of the size, severity, and duration of the epidemic is critical to inform policies or to formulate policies and programs and strategies. Now, SEIR model. So we adopted the model created and calibrated for many countries at the start of the pandemic. And the main compartments are, so in the SEIR model, the main compartments are susceptible, then exposed, then symptomatic infected, denoted by AS, asymptomatic infected by IA, under treatment U, and recover R. So these are actually the things. So SEIR, SE means susceptible, exposed, then symptomatic, or that means infected. Infected may be symptomatic and asymptomatic, then under treatment and recover. And here we separate the U compartment into hospitalized and quarantine. We point out, however, that our this model does not consider the effect of reinfection. And we can distinguish the hospitalization rate from the testing rate. The hospitalization rate, CS, is due to hospitalized symptomatic infected individuals, not because of COVID-19, but because of other diseases. In reality, these infects with comorbidity are exacerbated by COVID-19. On the other hand, the testing rate nu is due to hospitalized symptomatic infected individuals after testing positive for COVID-19. And all this actually led to some differential equations, and the picture is also very clear. The dynamics is governed by a system of 7 ordinary differential equations, and the solutions can be obtained by means of sophisticated software programs. And now we are coming to the Indian scenario. As far as the Indian scenario is concerned, the spread of the novel coronavirus has accelerated with the new cases and deaths being reported daily. Following the first confirmed positive case reported in Kerala on January 30th of 2020, the epidemic has spread fast and set its footprints in the whole country. As of December 10, 2021, last year, India has confirmed 93,277 active COVID-19 cases and 4,75,128 deaths. So now it has crossed about 5 lakhs. So it has been more than 19 months since the World Health Organization announced COVID-19 as a pandemic on March 11, 2020, which is continuing to damage public life all over the world. And there was a second wave of COVID also. The second wave of COVID-19, which began around February 11, 2021, last year, caused havoc in India, with daily cases reaching nearly triple the first week on April 19, 2021. Due to regional heterogeneity and the spread of many coronavirus variants, the epidemic evolution in India is quite complicated. The second wave, in comparison to the first, created more havoc. While countries are taking enormous measures to speed up vaccination campaigns in order to control the pandemic as quickly as possible, the SARS-CoV-2 virus has developed mutations that make it highly contagious, posing a public health threat. Now, there has been another variant. The emergence of specific SARS-CoV-2 variants are characterized as variant of interest, VOI, and variant of concern, VOC. The WHO announced on November 26 last year, 2021, that a new SARS-CoV variant of concern, which they labeled as Omicron, seemed to be increasing in almost all of the provinces in South Africa, and India also witnessed it. So India had reported a total of 32 cases Omicron variant till December 10, 2021. For all previous variants, the majority of COVID-19 vaccines have remained effective in avoiding severe COVID-19 hospitalization and death. Inferences based on known mutations and preliminary observations suggest that Omicron can spread more quickly and elude antibodies more easily than prior variants, resulting in an increase in the number of cases. According to the data from prior VOCs, vaccinated people have a considerably less chance of serious sickness from Omicron infection. And now these things have become history, and you know. And now we are actually not much afraid of COVID, and our country also has regained strength, and we have been successful in curbing COVID. Certainly, it is actually causing threats all over the world. So the crude fatality rate, that is actually one of the statistical measures or epidemiological measures to measure the risk. To understand the severity of the epidemic among cases, a common epidemiological practice is to estimate the case fatality rate. This study speaks briefly about the CFR estimation of the top 10 ranked states in the Nidhi Aayog Health Index. The strategy utilized in acquiring the CFR is the Yoshikura technique. The evaluated Yoshikura estimate is compared along with the general equation of CFR to check the precision of the model. Also in this study, deaths based on the daily reported data are fitted to various distributions in order to find the best fit model. And we have considered time series forecasting also. CFR is beneficial to find the severity of the COVID-19 cases and death. The small fluctuation in the value of CFR is depicted through forecasting. In this study, a time series model is also developed and then employed for forecasting future demise in India. The ARIMA model is helpful to predict the likely development of the pandemic. Materials and methods. So the COVID-19 data set of India is collected from JHU CSSE and the GitHub repository provided from March 12, 2020 to July 31, 2020. The variables included confirmed cases, fewer cases, and deaths. This data is further used to compare the mortality using CFR and then to forecast and fit the COVID-19 deaths. And mortality rate and recovery rate. These are epidemiological measures. Here, the mortality rate of the pandemic of the first 10 ranked states in the Nidhi Aayog Health Index are compared. The states are Kerala, Andhra Pradesh, Maharashtra, Gujarat, Punjab, Himachal Pradesh, Jammu and Kashmir, Karnataka, Tamil Nadu, and Telangana. These were the 10 top ranked states as far as COVID pandemic in India is concerned. Besides the fatality, it is of significance to incorporate measures such as mortality rate and recovery rate. which gives a better idea about the strict measures and the care taken by health professionals in preventing deaths due to COVID-19. Among these three measures, CFR is the most important marker for mirroring the infection severity dependent on the mortality, case fatality ratio. To recognize the severity of the infection, we determine the effects of public health measures and anticipate the probable number of deaths in the population given the total number of people infected. It is of utmost importance to measure the real time during the early stage of an epidemic. CFR is obtained as the proportion of cases of a specified condition that are fatal within a specific time. CFR is actually number of deaths due to COVID-19 divided by total number of cases of COVID-19 in a specific period of time multiplied by 100 or expressed as a percentage. But this value is often known to be flawed, frequently underestimating the actual CFR. The study is put forward to obtain a precise estimate by employing the Yoshikura method. Yoshikura estimator or CFR. Let X be the cumulative number of cases and Y be the cumulative number of deaths respectively. Yoshikura method involves the linear relation between log X and log Y. And the model is represented as follows. Log Y equal to K log X plus L. And the CFR estimate can be obtained as rho cap is equal to X by N0 raised to K divided by X, where N0 that is E raised to minus of the intercept divided by slope. The coefficient K is the slope of the straight line and N0 is the number of those confirmed cases that occurred before the first pandemic related. Hence, the CFR of the top 10 ranked states is obtained. Thereby, the states with the most and least values of CFR are obtained. The higher CFR value suggests a significant death toll. In the case of COVID-19, the CFR acts as a better estimate for understanding the outbreak and epidemiological features of the disease, and thus get more ideas on the severity of the disease. Now, mortality rate and recovery rate. Mortality rate is equal to number of deaths due to COVID-19 divided by the total population, expressed in terms of, you can say 10,000. And recovery rate also, that is a percentage, number of people recovered from COVID-19 divided by number of COVID-19 cases with outcomes. So these are actually the measures which are used for measuring the risk involved. And now we will be considering some distribution modeling also. In the next stage, statistical distributions that best fits the data of COVID-19 mortality in India is evaluated using the MLE method. The first step is the choice of candidate distributions for fitting distributions to the data. Henceforth, the histogram and empirical distribution were plotted to check the normality, and then the data was found to be right skewed. In order to model the data using a set of parametric distributions, various characteristic statistics are used. Accordingly, variable, gamma, and log normal distributions were chosen in order to find the best fitted distribution among them. And the PDF was fitted to the data. So each PDF was fitted to the data one at a time after selecting one or more parametric distributions. And the distribution models which we considered were the variable distribution, the gamma distribution, and the log normal distribution. And the best fitting models, distribution parameters were estimated using method of maximum likelihood, and we have made use of the classical goodness of fit plots. Then the plots help to determine the best fit distribution. The goodness of it is done using Kolmogorov statistic. A maximum log likelihood value and lower AIC and BIC values were the criteria for finding the best fit among the distributions. In this study, the Akkaike information criteria, that is AIC values of the three distributions are compared, and the distributions with the lowest AIC value was selected as the best one. And box time series modeling, the trend and forecasting pattern of mortality of infection in India due to COVID-19 is obtained using time series modeling. Box-Jenkins ARIMA modeling is one of the best modeling techniques for forecasting a time series. The main step in time series analysis and modeling was done by computing autocorrelation and partial autocorrelation coefficient. ARMA models combine autocorrelation methods and moving averages and time-dependent parameters. When differencing is needed, the procedure is to make the series stationary. It becomes then an ARIMA PDQ model or Box-Jenkins model, where P stands for the order of autoregression, D stands for the degree of trend, difference. So how many differences, how many stages of differencing we have to do. And Q, that is the order of the moving average model. And the ARMA PQ model, that is the most convenient one. And that can be obtained after making the ARIMA model somewhat stationary. In this model, the time pattern changes after a specific point and is examined further to find out the nature of change and potential causes. Box-Jenkins modeling primarily includes the checking of stationarity of data using augmented Dickey-Fuller test. The existence of trend and periodicity would result in non-stationarity. In order to remove the effects, the differencing stage is included until the time series becomes stationary. Then the autocovariance function, the partial autocovariance function, etc. are plotted, which are useful in identifying and modeling the patterns in the time series model. When modeling is completed, the result will be analyzed or integrated to produce the estimation and the forecast values. The ARIMA model is fitted to the resulting time series by using an automated process. And the ARMA PQ model is having a general structure of this form. Yt is equal to some constant plus phi1 yt minus 1 plus y2 phi2 into yt minus 2, etc. Phi p into yt minus p plus the innovation terms, that is epsilon t minus theta 1 epsilon t, t minus 1 theta 2 t minus 2 epsilon t minus 2, etc. minus theta q epsilon t minus 2. So here the y values are there, that's the process values. Then the epsilons are there. Epsilon t's are actually called the innovations. Usually in regression, we refer to them as errors or residuals, etc. So, but here in time series analysis, they are referred to as innovations. And ARIMA PDQ model. In the ARIMA PDQ model, so we are having the same structure, but what we do is actually we will be making this transformation, that is differences, so that we will be getting yt prime. So yt prime, that is the difference one. So that is actually the net one. So initially yt is there, that is the original data. So that is actually difference, and we will be getting the model yt dash equal to c plus phi1 yt minus 1 dash prime, then plus phi2 into yt minus 2 prime, etc. Theta t minus theta 1, epsilon t minus theta 1 into epsilon t minus 1, etc. minus theta q epsilon t minus 2. And we will be making use of the archaic information value and other criteria for determining the best one. So anyway, so we are having a non-stationary model like an ARIMA PDQ model. So after these transformations, we have to reduce it to an ARMA PQ model. And the next step in time series analysis is diagnostic checking. After model estimation, diagnostic checking of the model is conducted, which involves residual analysis. The model adequacy is primarily related to the assumption that residuals should be independent and identically distributed. Also, the residuals should be uncorrelated. They were examined by using the autocorrelation function, partial autocorrelation function, ADF test, Anderson, Darling, that distance function, then Young box test, and so on. And the statistical analysis was actually carried out using R. So that way, we have carried out all the preliminary works, and I have just reviewed those things. And the results and discussion. The table below, so we will be showing the table. So shown below represents the obtained values of MR, RR, pooled CFR, and then mortality rate, and all those things. Oshikara estimate. Then Kerala has the least CFR of 0.4%, including the least severity, and Gujarat has the highest CFR of 5.25, representing the severity of the disease. And the states which comparatively low CFR other than Kerala, Himachal Pradesh, Maharashtra is the state with comparatively high CFR. Next to Gujarat, Kerala is one among the states with the lowest mortality rate also. And these are the values of the mortality rate and MRs, RR, CFR, the crude mortality rate also. So this actually shows that Kerala has the least one, and Telangana also has, in some respects, Telangana, Yoshikura, CFR is actually lowest for Telangana. So crude CFR and Yoshikura CFR. So that is actually plotted here, and the results are the evaluating the statistical distribution. That is are the results of the model fitting. So, so we are having 142 daily data of India at that time when these computations were made 1 year back. So we have obtained the estimates and we have seen that the kurtosis is very high. Estimated skewness is 2.1750. So this actually implies that indicating deviation from normality to right skewed distribution. And the figures also indicates some right skewed distribution. And we considered variable, gamma, and log normal distributions. And the empirical PDF and CDFs were plotted. Then the QQ plot and PP plot were also plotted. Then the goodness of its statistics were considered and demonstrates the estimate and standard of the unknown parameters. And we are having the variable parameters, gamma parameters, and log normal parameters. And we can see that the log likelihood is least for 889, that is for gamma, and the AIC value is also least for the gamma distribution, and BIC value is also least for the gamma distribution, showing that gamma distribution may be the most suitable one. So all are actually equally competent, but among these three, gamma distribution seems to be more appropriate. And the goodness of comparison. So you can make use of the Kolmogorov distance statistic. And there also, we have seen that the gamma case, it is least 0.0877. And the AIC values also, for gamma, it is least. And the fitted model, the time series model is here. For forecasting the future COVID-19 deaths, the daily deaths in India has been collected. And there also, we have obtained the ARIMA model 011 model was obtained, and ZT is equal to ZT minus 1 plus epsilon t plus 0.8923 epsilon t minus 1. That is actually an ARMA 11 model. So to forecast the future mortality of COVID-19 using the ARIMA 011 model, the values were plotted, and this actually had a very high peak at a particular value between June and July, so June 15. And that was also observed to be true. And the plots of ACF and PSCF are here. And based on that, actually, we have justification for using the AR11 model. And the forecast values are also here. And the values were found to be true, somewhat true at that time. And the forecast. So as far as time series modeling or forecasting is concerned, so as far as a statistician is concerned, what we can forecast is only for a short duration. So we cannot forecast COVID for next 10 years, next 1 year. So certainly it depends on various other factors, various other intrinsic factors. It's not only natural. So the state intervention is there, the medical intervention is there. So certainly there will be those factors will be affecting, or those factors will be more serious than random factors. So that is why we are making a prediction for just for 1 month. So even for 1 month, it is not at all suitable. Just for 1 week, you can say that will be more suitable or more accurate. So why this type of forecasting is needed? Certainly to make arrangements by the government departments and the administrative people to make care of, to arrange necessary facilities for treatment and other things. So forecast error, certainly there were some errors in the forecast. And now we're coming to the conclusion. The patterns from the data reveal the prompt and effective approaches being taken and to be taken to minimize the mortality of the human population. This study mainly focuses on evaluating the severity of COVID-19 in the top 10 ranked states. We studied Niti Aayog Health Index using Yoshikura estimator CFR. Kerala has the least CFR estimate of 0.40, and Maharashtra has the second most elevated CFR estimate of 4.21%. Gujarat tops the list with a higher CFR value of 5.25%. The Yoshikura CFR values corresponding to Maharashtra and Gujarat does not show much significant difference, and thus it might shift in like manner sooner rather than later. Since Kerala has the least CFR, it can be presumed that the system, including treatment, infrastructure, awareness, is more worthy than other states. And we have some more conclusions. The demonstration based on the distribution of COVID-19. Daily deaths in India was done with variable, gamma, and log normal distributions in order to validate the best fitted model. Gamma distribution was obtained as the best fitted distribution among the other distributions, as it is satisfied the criteria of having lower AIC value, having lower value for the Kolmogorov Smirnov test statistic, and so on. Here, the estimated shape parameter of gamma distribution has a low value of 0.653, indicating that the data is right skewed. The smaller the shape parameter, the more the distribution tends to be skewed to the right, suggesting least probability of deaths. Therefore, if the shape parameter becomes much smaller than the current, then there could be possible decrease in the probability of death even further. Hence, in the present study, the gamma distribution indicates that the number of deaths is smaller and could possibly be the same with appropriate stringent measures. The ARMA model helps to forecast future values. And conclusions continued. Forecasting future deaths to strengthen the measures for minimizing the death toll is a criterion to know the effect of an epidemic in the near future. An estimate of future death on a daily basis is obtained by employing the time series to propound mortality in India. An ARIMA 011 model with low AIC value is obtained and is used to forecast COVID-19 deaths. Based on the known number of deaths, an increasing pattern of the predicted death is obtained. Even during the restricted lockdown period, it shows an increasing trend of demise, which indicates that death risk will reduce for the next few months. So that's also history. So now we have the experience. Forecast values of COVID infection patients and the future deaths are exceptionally vital to support the medical authorities to be prepared for the upcoming events and more readiness in the healthcare system. Vaccines are to be developed and applied for different age groups, including children and even infants. More data-driven analytic models are to be developed to have a thorough understanding of the emerging situation. Data science and data analytics methods can be employed for developing more heuristic methods and realistic models. IIT Chennai had developed such models and they were found to be suitable at that time. So anyway, certainly there is more future for data science and data analytics methods to study the secrets, the dynamics of the disease. And these are the references. And Ashade and many others, and Johnson, Norman, and so on. Then Marimuthu, Malaviga, Marimuthu, etc. They were our students working at Vellore, CMC Vellore. Thank you. So we have also published some papers on COVID-19 analysis and forecasting and so on. So thank you. Thank you.
Good afternoon, sir.
Any questions?
Any questions? Good afternoon, sir. Good afternoon, sir.
Good afternoon. Good afternoon. Good afternoon.
Any questions from the delegates? Let us thank the speaker, Professor Jose.
Sir, I have one doubt.
Yes.
Actually, usually for time series model, we use MLE to estimate. So,
MLEs, we have to make use of numerical methods certainly. So we cannot directly obtain. As far as you know, for the log normal, etc., we have standard methods. For the variable, etc.
What about mathematical models? They are also
even R codes are available, so freely available as far as these variable and gamma distributions are concerned. So
I'm asking, what about the mathematical models, right? SAR or other models you discussed, how to estimate the parameters?
Hello.
Yeah, hello. So I'm not sure I'm audible. So I have seen that MLE you are using for estimating this time series modeling, other modeling. But what about the mathematical modeling? Like SAR modeling, initially you explained how to estimate the parameters.
Estimate the
parameters, SAR models.
So using R programming, we can estimate. So R pods were actually used actually. So that's it. And these are available in the R directories. So as far as gamma, so these are the standard distributions for them. These are available, so we can make use of those methods and using the data we have so easily obtained. So, but what I can say is actually these are not sufficient. That is actually the thing. So certainly So to study about the intricacies, the dynamics, so we need actually more things. Actually.
Okay, sir. Thank you. Thank you, sir.
Thank you.
Any more questions?
Hello?
Any more questions? If not, let us thank our speaker, Professor Jose. Sir, this is Professor Jayasri. I came to Pala once. Yes, sir. When we had a telephonic conversation on that day, you reminded of that, sir.
So thank you, Professor Jayasri.
Thank you, sir. Thank you very much for accepting our invitation and giving this lecture, sir. And that too on the recent.
Swami. So was my friend while hosting the conference at Pali. So he was the general secretary at that time.
Yes. Yes, sir. Thank you very much, sir.
Are there Swamis attending this program?
Yes, sir. Sir knew about it, but sir is in abroad. So sir said if it is comfortable for him, he will join in some of the sessions.
Okay.
And thank you very much, sir.
Thank you all.
Thank you, sir. The next chair for this particular session 3:45 to 5:30 p.m. is Dr. Subha Nair. Dr. Subha Nair, madam, she is an associate professor in statistics at HHMSPB in NSS College for Women, University of Kerala. Madam did her PhD in statistics, completed it in 2019, and madam also completed her MPhil in 2005. And we are very happy, madam, because you have accepted our invitation. Thank you, ma'am.
Thank you.
Please,
Thank you.
Yes, ma'am, please start the session. Thank you, ma'am.
Okay, thank you. A very good afternoon to all of you. So we are going to start our next session, and that session is on reliability, and it's a session of contributory papers. I think we have got 11 presenters here. First of all, I would like to thank all the coordinators of this program for giving me this wonderful opportunity to chair a session in this conference. I'm extremely thankful for the opportunity. So I think we are right on time. Our time starts at 3:45. So without wasting much time, let us start the session. So as far as I know, there are 11 contributory papers in this session, and our total time is from 3:45 to 5:30 p.m. Each contributory paper, a speaker can take 10 minutes to present their paper, and we can have maybe 2 minutes of interaction. So I hope that all the presenters are already here. They have joined the session. So shall we start? Okay, I think we'll start. So the first paper is actually by Lakshmi Krishnan, and the paper is on smooth kernel estimation of conditional dynamic survival extropy. Lakshmi Menon, Lakshmi Krishnan, are you here?
Yes, ma'am. Yes, ma'am. I'm here.
Okay. So just give a 1 minute introduction and you can start the presentation.
Okay, ma'am. First I present the paper, then I introduce myself.
Lakshmi ma'am.
Yes.
Present your presentation, ma'am. It's visible now. You can carry on.
Good afternoon, everyone. Is this visible?
Yes, it is visible. You can proceed.
Nice. Myself, Lakshmi Krishnan, Department of Statistics, University of Kerala, under the supervision of Dr. E.I. Abdul Sattar, Professor and Head of the Department. My topic of presentation is smooth kernel estimation of conditional dynamic survival entropy. These are my outline. Abstract. Recently, Ladd et al. Introduced entropy as a complement dual of Shannon entropy in the univariate case. This article extends the concept of entropy to the bivariate case, including the conditionally specified models and some essential properties. Apart from this, characterization of some lifetime distributions are also done in this paper. Introduction. Shannon introduced a measure of uncertainty associated with a probability distribution called entropy for a non-negative absolutely continuous random variable x with the probability density function f. It is defined in equation 1.1. Ladd et al. Observed that the entropy measure on its own does not provide a complete summary of the information in a distribution, and hence a complementary measure needs to be monitored concomitantly with the entropy measure. This idea led to an alternative measure of uncertainty called entropy, which is the complementary dual of Shannon entropy. The entropy measure introduced by Ladd et al. And Shannon's entropy contribute to characterizing the information. Entropy has a wide range of applications, such as scoring the forecasting distributions in commercial or scientific areas like astronomical measurements of heat distributions in galaxies. Entropy can also be used to compare the uncertainties of two random variables. For a non-negative absolutely continuous random variable x with the density function f, entropy is defined in the following equation. Clearly, j of x is less than or equal to 0. Entropy cannot be used in the context of a random variable that has survived for some time, and in this context, Q and Gia suggested the measure of residual entropy, which is defined in the following equation. Danya and Sattar recently proposed a measure of uncertainty based on survival function called survival entropy and is defined in the following equation. The authors are also studied survival entropy for a residual lifetime and is called dynamic survival entropy. The initiative for using the survival function in the new measures of definition is that survival function exists when density does not exist. To study the reliability aspects of a multi-component system, with each component having a lifetime depending on the other, we use multivariate life distributions. Hence, the reliability characteristic in the univariate case extended suitably to high dimensions. This study aims to establish information measures for multivariate lifetime distributions whose support is truncated at the present ages of the system components. This paper discusses the bivariate setup of dynamic survival entropy and its various properties. Although in most life testing experiments, information on the current age of the components under consideration is typically available, examining the effects of a remaining lifetime is important in many situations. Information measures that include the HR functions of T, and hence it is called dynamic. So we define the bivariate dynamic survival entropy. In definition 2.1, we give the definition for the bivariate dynamic survival entropy. When considering bivariate measure, the calculation based on one variable must not be influenced by incomplete or inaccurate data on the other. Thus, we consider the component-wise dynamic survival entropy, provided both components have survived for specific times. Since the unreliable data is excluded, this measure would be more accurate. In the following definition, we define conditional dynamic survival entropy of a conditional variable. Definition 2.2, let U be a bivariate random vector with the distribution function k, then the conditional dynamic survival entropy for the conditional random variable is given in equation 2.1 and 2.2. In the following example, we compute the conditional dynamic survival entropy for some well-known distributions. The relationship between conditional dynamic survival entropy and the bivariate hazard rate is given by dou by dou Ti of JIS U T1 T2, which is equal to 1 by 2 plus 2 into JIS U T1 T2 into HI of T1 T2, where HI of T1 T2 are the components of bivariate hazard rate function. The following theorem states that the necessary and sufficient condition for two random variables are independent. The theorem 2.1 says that if the conditional dynamic survival entropy equal to the component based entropy, then the two variables are independent on each other. The following definition might be helpful in proving theorem 2.2. Definition 2.3. In definition 2.3, we say that if U is a random vector with a distribution function K, then the conditional dynamic survival entropy is an increasing or a decreasing function of Ti. Then the distribution function is also an increasing or a decreasing function of the conditional dynamic survival entropy. Then the following theorem presents the expression for increasing or decreasing conditional dynamic survival entropy based on definition 2.3. Let U be a non-negative random vector having an increasing or a decreasing conditional dynamic survival entropy if and only if JIS U T1 T2, which is greater than or equal to or less than or equal to minus 1 by 4 HI of T1 T2. The following theorem gives a lower bound for conditional dynamic survival entropy based on bivariate mean residual life function. Then, in the next theorem, we focus attention on characterizing bivariate models using a possible relationship between the two conditional dynamic survival entropy. If J1S U T1 T2, which is equal to a constant into J2S U T1 T2, hold for all real T1 and T2, if and only if K bar of T1 T2, the survival function is of the form given. Then the following theorem characterizes bivariate exponential distribution using conditional dynamic survival entropy. That is, if the conditional dynamic survival entropy is a constant, if and only if it follows the bivariate exponential distribution with the independent exponential marginals. The following theorem characterizes certain distribution using the functional relationship between conditional dynamic survival entropy and the bivariate mean residual life function. That is, if the conditional dynamic survival entropy equal to a constant into Mi of T1 T2, where Mi of T1 T2 are the components of mean residual life function, then it follows any one of the following distributions. Then the non-parametric estimation. Here we discuss two non-parametric estimators for the conditional dynamic survival entropy. In definition 4.1, let U1i, U2i, I equal to 1 to etc. n be a random sample taken from a population with a joint distribution function k. Using 2.1 and 2.2, we define the empirical estimator of conditional dynamic survival entropy and is given in equation 4.1 and 4.2. Next, we propose a non-parametric estimator for conditional dynamic survival entropy using kernel density method that U1i, U2i, I equal to 1 to etc. and be a random sample taken from a population with a survival function k bar, a non-parametric kernel estimator of conditional dynamic survival entropy.
Excuse me, Krishna, you have got 2 more minutes, okay?
Oh, okay, ma'am. Then the kernel estimator is given in equation 4.3 and 4.4. Then the theorem 4.1 says that the kernel density estimator is a consistent estimator of conditional dynamic survival entropy, and theorem 4.2 gave the bias and mean square error of the kernel density estimator. Now we find a numerical illustration of the two estimators. Here we simulated a data using the bivariate exponential distribution, and the bias and mean square error for both the estimators is given in table 1. Then conclusion. In most life testing experiment, information on the current age of the components under consideration is available. Then the remaining lifetime of the components are considered as an important data. In the present work, we extend the concept proposed by Danya and Sattar to the bivariate case and discuss some of its properties. Also, we find a lower bound for the proposed measure. Finally, some of the characterization results based on proposed measure has been discussed for various distributions using the interrelationship among other uncertainty measures measure. A numerical illustration of the proposed measure is also discussed in this paper. From the study, we informed that the kernel estimator gives better performance in terms of mean square error when compared to empirical estimators. These are my references. Thank you.
Thank you, Krishna. Actually, I've kept the time wonderfully well. Now it's time for queries. If someone have any questions or anything to discuss, please. Okay, Krishna, thank you very much.
Thank you, ma'am.
So I think, yeah, we'll move to the second presenter of the session. Mr. Nilesh Kumar H. Yadav, I hope you are in here.
Yes, madam, I'm present in.
Okay. So the next session is on a new inverse Gaussian linearized ridge estimator in the presence of multicollinearity by Mr. Nilesh Kumar H. Yadav. I invite you to present your work.
Yes, thank you, madam. Is my screen is visible?
Yes, it is. Yes.
Okay. Thank you, madam. Thank you. As madam introduced, myself Nilesh Kumar Yadav. I am working as an assistant professor of statistics in DRK College of Commerce, Kolhapur, Maharashtra, India. I am going to present my research work entitled "A New Inverse Gaussian Linearized Ridge Estimator in the Presence of Multicollinearity." The outline of my presentation is: I will introduce the inverse Gaussian regression model and then some existing estimators which are available to tackle the problem of multicollinearity in the presence of in inverse Gaussian regression model will be introduced. Then we will discuss the new proposed inverse Gaussian linearized ridge estimator and the selection of shrinkage parameter. The presentation ends with simulation study and real life applications. As we know, in most of the applications of industrial engineering, in lab testing, reliability, medical, agricultural, or management and social sciences, the dependent variable under study is continuous and extremely skewed, and it is well fitted by the inverse Gaussian distribution. Okay, we can see various references in the literature which they have used inverse Gaussian distribution to fit the extremely skewed data. You can see the density form, probability density function of the inverse Gaussian distribution on the screen. Yes, this inverse Gaussian distribution belongs to the member of exponential family. We can easily write this inverse Gaussian regression model in the form of exponential family. You can see this equivalence here. After comparing this density with the general form of exponential family, we can find theta is equal to -1/2 mu square. B theta is -√-2 theta, and phi is tau. To model the response variable in inverse Gaussian regression model, the canonical link function mu I is equal to 1/√of neta is used to linearize the predictors. We can write this inverse Gaussian regression model by using log likelihood function L beta. You can see the form of log likelihood function of inverse Gaussian regression model on the screen. To identify or to find or to estimate the unknown parameter beta, a well-known method, maximum likelihood estimation method, is used to identify this beta. But this L beta, after minimizing, after differentiating above this equation, log likelihood with respect to beta, we can find this form. This is the non-linear equation in beta. So the iterative reweighted least square method is used to obtain the maximum likelihood estimator of beta. After iterative method, at convergence, at final iteration, the form of maximum likelihood estimator, you can see the form of beta hat ML as x prime w hat x inverse x prime w hat z hat, where the z hat and w hat are given in this way. The covariance and MSE of this maximum likelihood estimator is obtained asymptotically by using the properties. You can find these formulas, or we can find these expressions in the literature. But the problem is here, when the problem of multicollinearity, that is near singularity, near linear relationship between the covariates, dramatically affect the covariance as well as MSE of the maximum likelihood estimator in inverse Gaussian regression. So when the problem of multicollinearity exists in the data, this ML estimator gives poor estimates. To tackle the problem of multi-quantity in inverse Gaussian regression model, Algamal in 2019 have proposed inverse Gaussian ridge estimator. The form of inverse Gaussian ridge estimator is here. Beta hat IGR is equal to x prime w at x plus ki inverse x prime w at x beta hat ml. Based on this estimator and by using the asymptotic properties of maximum likelihood estimator, this Algamal obtained the bias, covariant, and MSE of this proposed estimator. You can see the expressions on the screen. Later on, Navid and others in 2020 proposed inverse Gaussian Liu estimator to tackle the problem of multi-quantity in inverse Gaussian regression model. The form of inverse Gaussian Liu estimator is here. So similarly, Navid and others obtained the bias, covariance, and MSE of this proposed estimator based on the asymptotic properties of maximum likelihood estimator. In 2021, Lukman and others also proposed a new estimator designated as beta hat IGKL, inverse Gaussian KL estimator, to tackle the problem of multi-quantity. The form of this estimator and its bias, covariance, and MSE based on the asymptotic properties of ML estimator are obtained by Lukman, and they are presented in their article. On the similar line, we have proposed the inverse Gaussian linearized ridge estimator. By considering the research paper, Liu and Gao proposed estimator in linearized ridge regression estimator in linear setup. The same setup we have considered, and we have applied its shrinkage quantity in inverse Gaussian linearized ridge regression estimator. So by using Liu and Gao, we propose inverse Gaussian linearized ridge estimator for the inverse Gaussian regression model. The form of inverse Gaussian linearized ridge estimator is here. And its parameter setups are here. Also, we have obtained the bias, covariance, and MSE of this proposed estimator based on the asymptotic properties of maximum likelihood estimator. Now, there is one thing we have to consider, that is selection of shrinkage parameter. To obtain inverse Gaussian ridge estimator, Algamal used the shrinkage parameter K is estimated by using this formula. In inverse Gaussian Liu estimator, Navid and others used this formula to obtain shrinkage parameter and ultimately its proposed estimator. In inverse Gaussian KL estimator, Lukman and others have proposed the value of estimate of K hat by using this way. This tau hat, that is scaling parameter, is obtained in this way by all these authors. On the similar line, we have also obtained the shrinkage parameter by minimizing the MSE of proposed estimator, asymptotic MSE of proposed estimator. These are the steps involved in the identifying the estimation of shrinkage parameter by minimizing the MSE. Here we have considered MSE of estimator as a function of our shrinkage parameter. We have differentiated it and obtained its optimal choice, and we can find that the second derivative is negative, so this d hat is optimal way by minimizing MSE. Now, to study the performance of proposed and existing estimator, a simulation study is carried out. Yes, of course, to introduce the multi-quantity in the model, we have used a model given by McDonald and Glareno, Navid and others. The same model we have considered to introduce multi-quantity in the independent variables, where this mu I are generated by using this setup, by using this link function, and different values of parameters and setups are considered, different sample sizes, different number of independent variables, and degree of multi-quantity. To vary the collinearity level, we use different degrees of multi-quantity. We can find the values on the screen. By using this simulation study, we have obtained the estimated MSE and average estimated MSE of each estimator for 1000 replication. For example, the estimated MSE of inverse Gaussian linearized estimator is obtained by replacing the unknown values by their estimate based on their
two more minutes.
Yes, ma'am. Thank you. By using this average estimated MSE, we have done a simulation study 1000 times and obtained the average estimated MSE of each estimator for different values of n, rho, and p. And you can see the result on the screen. It is found that the average estimated MSE of proposed estimator is smaller than the remaining considered estimator for all combinations of n, rho, and p. Also, we have obtained a ratio of average estimated MSE of the different estimator over the proposed estimator, and these all ratios shows the values less than 1. That implies our estimator's average estimated MSE is smaller. The same thing is depicted graphically. Also, real life data is considered to evaluate the performance of proposed and existing estimator. This data set is widely analyzed by different researchers in the literature. Same data set we have considered, and this data for this data set we have applied our estimator and existing estimator and obtained the estimated MSE. You can see here that the estimated MSE of this proposed estimator, inverse Gaussian linear ridge estimator, is smaller as compared to the other existing estimator. And finally, the conclusion is the performance of the proposed estimator is better than the existing maximum likelihood estimator, inverse Gaussian ridge estimator, inverse Gaussian Liu estimator, and inverse Gaussian Kale estimator in the MSE sense when the problem of multi-quantity arises in the data. Thank you. Thank you. These are the key references. Thank you. Yes, madam. I'm over.
Thank you. Yeah, thank you, Mr. Nilesh Kumar, because you have, again, it's right on time.
Thank you.
Any queries? Any queries? Okay, thank you once again. So I think we'll go on to our next presenter. Actually, the work is on some aging notions based on the Laplace transforms of bivariate residual life, which is actually a joint work of Professor Rajesh Ji, Professor Unikishan Nair, and Jayalakshmi S. I think Jayalakshmi will be presenting it, right? Because Jayalakshmi, are you there?
Not a joiner.
Jayalakshmi. Jayalakshmi, are you there? The second, third presenter of the day. I hope it's Jayalakshmi. Are you there? I'm not able to hear you if you're there.
No, ma'am, she has not joined.
Okay, okay then. Okay, then we will go to the next contributor. It is actually the work is on the performance analysis of cold standby redundant system with different failure models subject to refreshment facility. Actually, I'm sorry that I'm stumbling here and there.
Ajay Kumar, yes, ma'am, present here.
Okay, okay. So Ajay Kumar, you will be presenting it.
Okay, ma'am.
Okay, okay. So I invite Mr. Ajay Kumar to present the paper on performance analysis of cold standby redundant system with different failure. Is it models, sir?
Yes, ma'am.
Model subject to refreshment facility. Actually, there is some printing problem in the paper given to me. That is why I'm stumbling when it comes to the names. I'm sorry. So, Mr. Ajay Kumar, you can take over the stage now. You have got 10 minutes, sir.
Screen is visible, ma'am?
Your screen, yeah, it is visible.
Okay, ma'am. First of all, good afternoon, all of you. Myself, Ajay Kumar, from Department of Mathematics, J.C. Bose University of Science and Technology, YMCA, Faridabad, Haryana, India. And today my topic is performance analysis of cold standby redundant systems with different failure modes subjected to refreshment facility. In this paper, exhibits the reliability measure of a cold standby system which having two identical units with the help of regenerative point technique and semi-Markov approach. The whole system have one operative and another unit as a cold standby. When operative unit fail, then cold standby unit come into existence and start working. Sometimes refreshment is offered to the server to improve his efficiency, and we have observed that sometimes operative unit may be failed from direct standby mode or either partial failure mode or completely failure modes. This is the introduction section in which we have defined redundancy parallel path in which the system performance is improved. And many researchers have discussed the stochastic behavior of cold standby system, including Kumar and Lal in 1979 evaluated the two-unit redundant system with one standby unit under the stochastic process, failure and intermittently available repair facility. Similarly, Goel and Sharma 1989 Explore the 2 unit standby system having a stochastic process with 2 failure modes, repair and slow switch condition using the regenerative point techniques. There are some other authors which have defined their work on the regenerative point technique. This is our model in which initially we have take 2 units. One is operative and other is cold standby. First time it is observed that operative unit may be fail partially with lambda 1 rate and operative unit may be fail with lambda rate. Then cold standby unit come into existence with probability A and start working. From the system diagram,
Excuse me,
we
sir.
have.
Excuse me,
Yes,
sir. Are your slides progressing, or actually we are seeing only your first screen?
No, ma'am. I am all slides are continuously, ma'am, working.
Okay. Actually, but we are seeing only your first screen, sir.
No, ma'am.
Maybe you should go to the slideshow.
Yes, ma'am.
Go to slideshow and please try that, because we can see only your first slide.
Just 1 minute, ma'am. I again now, ma'am.
Sir, close the presentation. Sir.
I think, can you please close it and reopen it once more and see?
Just 1 minute. Now again, I am sharing.
And now the sharing is gone. Please share once more. Okay, now please go to the,
Now it is visible, ma'am.
No, I think it's, no, sir.
Ma'am, there is an option, your screen is sharing. I have seen on my desktop message that your screen is sharing.
I think you should share the other screen. Now you should stop sharing now. Start your PowerPoint presentation and then share, so that you can choose the correct screen.
No, ma'am. I am sharing my same screen of the PowerPoint presentation. So just 1 minute. Now I again.
Please try once more.
Yes,
actually, someone was giving some hints. Can you please help him? Anyone?
Ajay, sir.
Yes.
Ajay, sir, can you hear me?
Now it is visible, ma'am.
Ajay, sir.
No, actually only your first screen is still visible.
Yes, ma'am.
Ajay, sir, can you hear me?
Yeah, actually, sir, please hear, someone is helping you there. Please, yeah.
Ajay, sir.
Please say, ma'am.
Sir, press the tab key, sir. Down arrow. Press the down arrow.
No. Actually, what is happening is he's actually seeing the screen share, and we are seeing the original presentation. That's why.
Okay, ma'am.
Do it here, sir. Without going to the presentation, can you just scroll through your this thing here?
Presentation mode, sir.
Yes, ma'am.
Close the presentation mode. No, close the presentation mode, sir.
Yeah. Please select it in this way. I think that'll be easier now, because there is some confusion. Ma'am, let him do it this way. You can select your slides here, and we'll be seeing them one by one. Okay.
Okay, ma'am. State transition diagram is visible or not, ma'am?
Yeah, now it is visible. You don't go to the original presentation mode. Just stay here and go through the slides. Okay, using down arrow.
Okay. I tell my all paper which depend on this diagram. I tell about it that in the initially S0 stage, I have to take 2 units. One is operative and another is cold standby. And I have observed that lambda 1 is the failure rate with which operative unit partially failed, and lambda is the failure rate with which original operative unit failed, and A is the probability that cold standby unit is working and start functioning. And similarly, lambda is the failure rate with which operative unit fail, and B be the probability that cold standby unit is also fail and it is waiting for repair. Similarly, at the stage of S1, partially fail unit with the rate of lambda 2 and probability of A sent to S2 stage, and S3 will be the stage from which GT will be the repair rate from which our failure rate come into operative and waiting rate come into under repair. Similarly, other stages which we have defined here. Transition probability phases is visible or not, ma'am?
Actually, we are still seeing your diagram, sir. Can you select the next slide? Select it manually.
Yes, ma'am. I have not manually from the using new screen share options, and I have used it, ma'am.
Okay. See, just go to your presentation and go to the next slide. You can see your slides on the left hand side, right? Okay. Now it's working.
Okay, ma'am.
Okay, now we can see the transition probabilities. I think it will work from now on.
Okay, ma'am. Okay. With the help of transition diagram, we observe that P will be the probability from the initial stage 0 to the 1 with lambda 1 upon lambda 1 plus lambda, and correspondence from all stages. We have first find out all probabilities and observe that sum of all probabilities corresponding to the given stage is equal to 1 or not. If it is 1, then it means our diagram is correct. Now next slide is mean origin time. Now it is visible or not, ma'am? Mean origin time.
Yes, now it is working. You can carry on. It is working fine now.
Okay. Mean origin time values are also verified from using the system diagram, and mu0 represent that transition from 0 to 1 and transition from 0 to 2, transition from 0 to 3, and their all sums which we have find out using the formula integration from probability t which is greater than equal to t, where t represent the times signify the failure of the systems. And similarly, we have find out for all stages mu1, mu2, mu3, all values, and mu2 dash, mu3 dash, mu6 dash, mu7 dash are the values which we have to find out using the Y probability through another stages. Mean time to the system failures. Using the above system diagram model, we have find out total time which is spent between two consecutive failures, and system availability which we have find out that system is available during the time periods, busy period of the servers, and using the above diagram calculations, we verify that mean time to the system failure diagram is visible or not, ma'am? System diagram is visible or not?
It's visible, sir.
It is visible, sir.
Okay. System diagram verify that mean time to the system failure versus refreshment rate. It means that when refreshment is offered to the server, then our mean time which is spent to the systems is increasing, and similarly availability of the system is also increasing. It means using the MTSF availability values, profit of the system is also increasing order. So we conclude that our system model is beneficial for the cold standby system models. These are the references. Thank you. Any query?
Any queries? Okay, so thank you, Mr. Ajay Kumar. Yeah, I think we'll go to the.
From where I have received the attendance links, ma'am.
I didn't get you, sir. Can you repeat what you asked?
Ma'am, from where I have filled my attendance.
Your attendance. Other options? Okay. No. There are no options. Actually, I'll be reporting it. I don't think there is any place where you can give your attendance. I'll be reporting the number of presenters. That might be enough, sir.
Okay, ma'am.
Okay. Thank you. So we'll go to our next presentation. That is by Rimpaldeep Kaur.
Yes, ma'am.
Yeah, you are there. Okay. So I'd like to welcome Ms. Rimpaldeep Kaur. She's here to present the paper, Performance Analysis of Cold Standby Redundant System with Different Failure Models. Sorry. Her paper is Probabilistic Performance Analysis of a System Using Regenerative Point Technique. So Rimpaldeep Kaur, please start your presentation.
Okay, thank you, ma'am. Good afternoon to all.
Myself, Rimpaldeep Kaur. I am a research scholar in Department of Statistics, Punjabi University, Patiala. I am pursuing my PhD under the supervision of Dr. Hatash Kumar Bhardwaj. Today, I am going to give my presentation on the topic probabilistic performance analysis of a system using regenerative point technique. The layout for my today's presentation is, first I will start with the introduction, then assumptions of model, states of the system model, notations, state transition diagram, then transition probabilities have been calculated. After that, performance measures have been calculated, and at last the conclusion has been drawn. So here I will start with the introduction. Over the past few decades, technology has advanced so remarkably that computer systems are being used by every industry to improve efficiency and stay ahead of their competitors. Therefore, computer systems have become an essential part of life, having significant impact on modern society. A system consists of hardware components that work well together and software programs that run on computer. They are used in businesses of all sizes, industries, and various IT organizations. Many IT organizations deploy servers that are only running at a fraction of their capacity because they are dedicating their physical server to a specific application. This is usually an inefficient mechanism because there is an excess capacity that is not being consumed, which leads to higher operating costs. As time goes on, technologies evolve and companies are looking for solutions that are increasingly dynamic and cheap to solve such kind of problems. Virtualization emerged as a solution to this, where companies could divide a particular hardware to run two or more different applications and thus achieve greater efficiency. This also leads to the reduction of costs and increased productivity by using fewer servers. Also, virtualization allows for faster and broader business capabilities. Few of the examples where virtualization has been used are cloud computing, software testing, and Microsoft Azure. It is Windows Azure is a Microsoft's public cloud computing platform. It provides a range of cloud services. Users can pick and choose from these services to develop or scale new applications and elsewise run existing applications in the public cloud. Once customers subscribe to Azure, they have access to all services included in Azure portal. As virtualization technologies have become a predominant paradigm of computing, there is a strong need to analyze long-run performance and aging issues in virtualized environments. Software aging in such environments can have a severe impact on millions of customers of business-critical applications as well as on end users, since virtualization is vastly being adopted. As we use a software for a longer period of time, it shows some error like degradation of software, crash or hang failure, memory leaking, data corruption, storage space fragmentation, and round of error. This constitutes a phenomenon called software aging. Software aging leads to performance degradation or application crash due to exhaustion of operating system resources, data corruption, etc. slowly with time. Aging can also be considered at different levels, such as application process, operating systems, application components, virtual machines, and virtual machine monitors. Therefore, to counteract the aging effect, a preventive technique was proposed by Huang et al. Called as software rejuvenation. Software rejuvenation occasionally stops running software, cleans its internal state, and restarts it. This is a cost-effective and time-effective method used to delay the failure of a system by cleaning up the aging effects in a system. This is the architecture of a typical virtualized server system with multiple virtual machines. Here, the system consists of two hosts. One is primary host and the second is a backup host. Host 1, which is also known as hypervisor, consists of two virtual machines, and each virtual machine consists of operating systems which runs different applications as required. Primary host and backup host share a storage area network on which the VM images or VMM source code files are stored. In the virtualized systems, certain random failures might occur while migration or when VMM goes into failure probable zone. Similarly, the failures of shared memory and direct failures of VMM are also random. So we can say that the system works in a random environment. Therefore, to understand the operating cycles of such a system, it is the need of the time to develop a conceptual model under the probabilistic rules. Keeping these facts in mind, a stochastic model of a computing system has been developed. Assumptions for the model developed are: system consists of two hosts. One host is operating and the second host is a backup host which is in a passive state. There is a single repair person or maintenance engineer who is present in our system and cannot fail while performing its duty. All VMM rejuvenations and repairs are perfect. All the random variables are statistically independent and follow general distributions. For a particular case, all the random variables are assumed to follow exponential distributions. These are the states for the model developed. These are the notations that have been used in the construction of the model. So here is the state transition diagram. Here the system is initially in the state S node. Now from state S node, there are three possibilities. The first possibility is that the system can go to the state S1 with probability density function SRT, where SRT is the PDF for the time taken by the system to go into the rejuvenation state after migration. After the rejuvenation has been done, the system from the state S1 will move back to the state S node with probability density function SCT. The second possibility from the state S node is that the system from state S node can move to state S2 with probability density function KFT, where KFT is the PDF for the failure time of virtual machine monitor. And after the virtual machine monitor has been repaired, the system will move back to the state S node from state S2 with probability density function KRT. The third possibility from the state S node is the system can go from state S node to state S3 with probability density function VFT, where VFT is the failure time of the shared memory. After the repair of the shared memory has been done, the system will move back from state S3 to state S node with probability density function VRT. Here the transition probabilities and the mean sojourn times have been calculated. Here the mean sojourn times in the state Si is given by the following: mu0, mu1, mu2 and mu3. Here the unconditional mean times has also been calculated. Next is the reliability and mean time to system failure. If let phi it be the cumulative distribution function of the passage time from regenerative state Si to a failed state, regarding the failed state as absorbing state, we have the following recursive relations. And then taking the Laplace-Dirichlet transform of the relations 2 and solving, we will have the expression for the reliability, which can be obtained by taking the inverse Laplace transformation of the equation number 3, and the mean time to system failure is given by equation star.
Excuse me, ma'am, you have got just 1.5 minutes more.
Okay, ma'am. Next is the steady state availability. Here, the equations for the recurrence relation for the availability has been given, and the availability has been calculated. Steady state availability has been calculated and is given by the equation number 5. Now we have supposed the particular case for exponential distribution with different parameters, and we have verified that the sum of all probabilities is equals to 1, and the mean sojourn times for a particular case by taking exponential distribution has also been calculated. The expression for MTSF and availability has also been calculated by considering the special case of exponential distribution. Here, the graph of mean time to system failure is given. Here, this graphically displays the trends of mean time to system failure with respect to virtual machine monitor failure rate for different levels of other parameters. It shows that for fixed values of other parameters, MTSF decreases with increasing values of failure rates of VMM. The MTSF also improves with increasing values of rate of rejuvenation from 0.1 to 0.4. The MTSF also improves for smaller values of failure rate of shared memory. That is, MTSF higher values for gamma is equals to 0.002 for rather than gamma is equals to 0.0007. This is the graph for the availability. This shows that the availability of the system increases by increasing the rate of rejuvenation from 0.1 to 0.4, and it also improves by increasing the values of repair rate of virtual
Excuse me, ma'am.
machine monitor.
Please wind up in 1 minute. Your time
and
is
the
up.
repair rate of shared memory. The system availability improves for small values of smaller values of failure rate of shared memory. Already explained. These are the references. Thank you.
Okay. Thank you, Ms. Rimpaldeep Kaur. Does anyone have any queries? We have got a minute for queries. Okay, thank you for your wonderful presentation. We will go on to our next speaker. We have got the next work is a new lifetime distribution, statistical inference and its applications. Arvind Pandey and Pawan Kumar Singh are the two co-authors of the work. I think, can I know who will be presenting it? Pawan Kumar Singh and Arvind Pandey. Okay, I think both of them are not there.
Not joined, ma'am.
Not joined. Okay, okay. Okay, then we'll go to the next next contributory paper. The paper is on reliability characteristics of a parallel cold standby system of pairwise identical 4 units with provision of priority by Mr. Puran Rati. Is the presenter here?
Yes, ma'am.
Puran Rati, are you there? Can I know whether the presenter has logged in? Okay.
Good evening, ma'am.
Yeah. Okay. 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 You are there.
Good evening, ma'am.
Yeah. Good evening. Good evening. So, can you have your 10 minutes now? Please start your presentation.
Yes, ma'am. Is my screen visible?
To share your screen, sir.
Ma'am, is my screen visible?
No.
No, no, it's not. It's not.
What?
Mr. Puranrati? I think he's having some, okay.
Is my screen visible, ma'am?
Actually, not your screen. We are seeing your, yeah, please, we are seeing your screen, but not your presentation.
Just a second, ma'am.
Yes, yes, sure. There are actually a lot of disturbances coming in.
Yes, ma'am. Sorry for disturbance, ma'am.
Okay, okay. So we are able to view your WhatsApp screen now.
Yes, ma'am. Now
okay.
is my screen
Now
visible?
it is visible. Yes, yes. So your 10
good
minutes
evening,
starts
ma'am.
now. Please continue.
Yeah, ma'am. Myself, Purati, research scholar. The topic of my today presentation is reliability characteristics of parallel core standby system of pairwise identical 4 units with provision of priority. I prepare this topic with the help of my supervisor, Professor S. E. Miller. And these are the contents of my research papers: introductions, abbreviations, notations, step descriptions, reliability measures, probability analysis, particular cases, graphical representation, and performance measures, applications, conclusions, as references. Uh, the economic progress of any country less or more depends on the industrial progress. Technology devices has played a great role for improving the degree of performance of the industrial system with maintaining an optimum balance with the costs. Everyone expects the proper functioning of machines, regular supply of electricity, and fault-free electrical and mechanical devices. Several techniques, including structural designs of the components, provision of redundancy, use of proper repair mechanism, quality of the raw material have been suggested by the engineers and scientists for the development of reliable systems. A timely research scholar work on this, Murari and Goer in 1984 used 3 types of repair facilities while analyzing a core standby system, and Goel et al. At 1984 discussed 2-unit parallel system with a standby units. Bhardwaj et al. In 2010 analyzed probabilistically a system of 2 non-identical parallel units with repair priority. And Kumar and Malik in 2018 discussed a non-identical unit repairable system. Kadan et al. In 2020 examined a non-identical repairable system of 3 units with priority for operation and simultaneous working of cold standby units. The researcher indicate that the models have been discussed either by the considering the identical units in parallel or non-identical units in pair. But there can be a situation where a single non-identical unit is not capable to bear the load of entire system, and in that situation, 2 or more units are required to work simultaneously in order to meet the system expectations. In a current paper, we determine the reliability characteristics of parallel core standby system of 4 units, and the units are in pairwise identical, which are in 2 phases. In first phase, 2 identical units, also called as main units, work in parallel, and other 2 units called redundant units are kept as a spare in the cold standby. And in the second phase, the cold standby units work simultaneously at failure of all the main units. And main units are identical, but these are dissimilar to the core standby units. A single core standby unit cannot bear the load of the system, so a single server engaged to handle all repair activities. And some significant reliability measures also, including mean sojourn time, transition probability, mean time to system failure, availability, expected numbers of repairs for both main and duplicate units, or
Excuse me, sir. I think your screen is stuck.
sorry, ma'am, there is a problems in my screen.
Okay.
Yes, ma'am. Is my screen visible?
No, it's not.
Now is visible my screen?
Yeah, it's coming.
Thank you.
Okay. Yes.
The graphical representation of the reliability characteristics have been made for arbitrary values of the rates associated with the failure and repair times. And the complication of present state can be visualized in power distribution system. These are some abbreviations and notations which I have used in my current papers. State descriptions. Initially, in our system, there are 4 units, in which two units are in operation, which we called in phase 1, and 2 units are in cold standby. At initial stage, it transits to state S1 with the failure rate of 2 lambda. At S1, the state becomes 1 unit is in operation and one other phase 1 unit is in fail under repair and other 2 units are in cold standby units. At state 4, S4 and S4, it transits to state S1 with the failure rate of lambda, where lambda is a failure rate of the phase 1 units, that is main units. And S5, it transits to state GT, which is the repair rate of the main units. And here is a and convolution occurs. These are some reliability measures, transition probabilities, mean solution times. The MTSF is instead SIR calculated by the following relations. Reliability and MTSFs and SIIT be the CDF of first passage time from regenerative state SI to a fail state regarding to fail state as a observing state. We have following recursive relations for SIIT. And by using Kramer-Rao rules, we find out the reliabilities as 1 minus psi naught S divided by S. System availability. The recursive relation for availabilities are given by the following equations. And using the Kramer-Rao rules and Laplace transform techniques, we find out the availability for steady state as by the following expressions. Expected numbers of repairs of many units by using the recursive relations are forbid. Sorry for disturbance. Expected numbers of repairs of duplicate units. The recursive relation for duplicate units are given by the following recursive relations, where S is a regenerative state to which the regenerative state I can transit through an N transition. The expected number of repairs of the duplicate units in steady state can be obtained as by using Kramer-Rao rules and taking the Laplace transformation of the above these equations, we find out the expected numbers of repairs of duplicate units, and same we can calculate the number of visits of the server. Then after busy period of the servers by use the availability busy period and visit of the server and repair rate of main and duplicate unit, we find out the profit analysis particular case. The reliability characteristics of system model have been obtained for the rates which follow negative exponential distribution, and the following results for some significant reliability measures such as MTSF, mean time to system failures, availabilities, and profit function have been obtained by giving the arbitrary values of the parameters. These are the graphical and tabulation presentation of the work, and from the graph we see that as the failure rate increases, the MTSF of the system is decreases.
So you have got 1 more minute.
This is the graph for availability and versus the failure rate of the phase 1 unit, that is main unit. From this graph we see that when the failure rate is increases, the availability becomes decreased, and when we increase the repair rate of the main unit, the availability of the system becomes increases. Same graphs follow for the profit. These are the application which we utilize in our systems. In this system, the transformer work as a phase 1 units and regenerator work as a phase 2 units. The parallel mode of operation of the transformation have been considered to supply of the power for a considerable time period, and provision of two generators have been given in order to them for their emergencies. Conclusions. The above graphical and tabulation presence reveals that MTSF availability and profit of system keeps decreasing with the increase of failure rate of main and duplicate units, while they increase with the increase of repair of the main units. And the performance of repairable percolation system of 4 units can be improved by increasing the repair rate of the main units. These are some references.
Okay.
From my side, done, ma'am.
So I think you have done your conclusion, right? Because your time is up.
Yes, ma'am. Sorry,
So
ma'am.
shall we
There is a lot
conclude?
of disturbance.
No, no. Okay, no problem. I think you're somewhere outside. It's
Yeah,
okay. So we have reached the end of your presentation, right?
Yes.
Okay. Thank you, Mr. Purandriti, for the presentation. Any queries? We have got 1 fast minute for queries. Anyone with any doubts? Okay. Thank you. We'll move on to our next.
Thank you. Thank you.
Yeah, thank you. Thank you. We'll move on to our next presenter. Ms. Vaishali Saxena. Are you there, ma'am?
Join.
She has joined?
No, ma'am. No.
She's not there, I think, right?
She has not joined, ma'am.
Okay, okay, okay. So Ms. Vaishali Saxena is also not there. So surely we'll go to the next presenter. Actually, it's a joint work by Kavya P and Manoharan, Professor Manoharan M. So I think Kavya P will be presenting. So I invite Ms. Kavya P to present her paper on a new lifetime model for non-monotone failure rate data. You have got 10 minutes, Kavya.
Okay. Is it visible, ma'am?
Yes, it is.
I'm Kavya. Sorry, good afternoon all. I'm Kavya. I'm a research scholar from University of Calicut. My topic is a new lifetime model for non-monotone failure rate. It's a joint work with my guide, Professor Dr. M. Manohar. Summary of the study: Introduction, GKM transformation, GKM exponential distribution, statistical properties, parameter estimation, simulation study, applications and conclusion. Introduction. The study of duration of life of organisms, system or devices, materials, etc. is of major importance in the biological and engineering sciences. A significant part of such a study is devoted to the mathematical description of the duration of life by a failure distribution. In early times, the distribution which showed constant and monotone hazard rates were widely used for survival analysis. Subsequently, the researchers realized that there were situations where the hazard rate turned out to be non-monotone, for example, human life. Later, the researcher generalized the existing model to obtain new lifetime distributions whose hazard rate functions are non-monotone. Notable works include those by Mudholkar et al., Gupta et al., and Gupta and Kundu. The lifetime models that exhibit inverse bathtub hazard rate find their application in survival analysis. A study of head and neck cancer data, CFRON, showed inverse bathtub hazard rates. Inverse variable, log logistic, but type 3, and log normal are some of the statistical distributions that show inverse bathtub hazard rate. For more details, readers may refer to Coates and Nadraja. Recently, Dimitropoulou et al., Sharma et al., Alkarni, Maurya et al., Kavya and Manoharan developed and studied inverse bathtub-shaped hazard rate distributions. The main objective of our work is to develop a new lifetime model which incorporates non-monotone hazard rates for different values of parameter and fits a large variety of failure time data. For this purpose, we generalized KM transformation introduced by Kavya and Manoharan. The KM transformation is defined as f of x equal to e by e minus 1, 1 minus e raised to minus g of x. Here g of x is the CDF of some baseline distribution. Generalized KM transformation. Here we generalize the KM transformation using a positive parameter alpha. The new transformation is called generalized KM transformation. The GKM transformation is defined as f of x equal to e by e minus 1, 1 minus e raised to minus g alpha x. Here g of x is the CDF of some baseline distribution. The probability density function and hazard rate functions are given in equation number 2 and 3. GKM exponential distribution. We introduce a new distribution using exponential distribution as the baseline distribution in the GKM transformation because exponential distribution has wide application in reliability theory and survival analysis. Substitute the CDF of exponential distribution in equation 1, we get a new distribution and it is called generalized KM exponential distribution. The PDF and CDF of the new distributions are given in equation number 4 and 5. This is the PDF plot of GKM distribution. Hazard rate function. The hazard rate function of the GKM distribution is given in equation number 6. For alpha greater than or greater than 1, the distribution shows inverse bathtub shape hazard rate function. When alpha less than or equal to 1, the distribution shows decreasing hazard rate function. We theoretically prove the shape of hazard rate function using Glaser method. Statistical properties. This is the rth row moment of the GKME distribution. We can compute, using this expression, we can compute the higher central moments and variance. This slide shows the conditional expression of the conditional moments. This is the mean residual function of the GKME distribution. And this is the mean past lifetime function of the GKME distribution. The pth quantile function of the proposed distribution is given in equation number 8, and we can simulate a random sample X with GKME distribution using equation number 9. Here U1, U2, etc. UN are independent random observation from the standard uniform distribution. The parameter estimation is done using maximum likelihood estimation method. This is the likelihood function, and this is the log likelihood function of the GKME distribution. And we calculate partial derivative of the log likelihood function with respect to parameter alpha and theta. Equating these partial derivative to 0 yields two nonlinear equations, and the solution provides the maximum likelihood estimation of the parameter alpha and theta. Newton-Raphson method can be used to solve these equations with the help of R language. Simulation study. We conduct a simulation study using Monte Carlo simulation method. Here we evaluate the performance of the maximal likelihood estimators of the parameters involved in the proposed distribution. In each experiment, using equation number 9, 1000 pseudo-random samples have been generated for different values of populated parameter. Here we take alpha equal to 0.6, 1.52 and theta equal to 0.51, 1.52 and sample sizes n equal to 50, 100, 500 and 1000. For 1000 repetition, the standard error of the estimated parameters are computed. This is the table. From the table, we can see that when n sample size n increases, the estimated parameter approaches to the true parameter. That means the standard error decreases when sample size n increases. Application. In this section, we compare our proposed distribution with some of the well-known distribution in the literature to prove the suitability of the GKME distribution. The distributions which used for comparison are generalized DUS exponential, KM exponential, KM variable, inverse variable, exponential and variable. For the comparison purpose, we use AAC, BIC, HQC, LL value, P value and KS test value. The definition of AAC, BAC and HQCs are given. Here, n is the sample size, k is the number of parameters, and L is the maximum value of the likelihood function for the considered distribution. The distribution which gets minimum AAC, BAC, HQC, and KS test values and maximum LL and P value is more suitable to the dataset. In this section, we analyze the introduced model using R language. First dataset. Here we consider a real dataset which represents the maximum flood level of the Susquehanna River. This is the table. This is the comparison table. From the table, we can see that our proposed model fits better with the data compared to other models. This is the comparison plot for first data set. Second data set. The data set consists of survival times of guinea pigs injected with different doses of tubercle bacilli, and the data is presented in this table. This is the comparison table. From the table, we can see that the GKME distribution shows minimum AAC, BAC, HQC and KS test value and maximum P value and LL value. So we can say that our proposed model fits better with the data compared to other models. This is the comparison plot for second data set. Conclusion. We develop a new lifetime model with a decreasing and inverse bathtub shaped hazard rate function in the present study. The distribution is obtained by generalizing the KM transformation. We derive some properties of the new distribution like moments, conditional moments, mean residual function, mean past lifetime function and quantile function. Simulation study is carried out to evaluate the performance of the maximal likelihood estimators of the parameters involved in the proposed distribution. With the help of two real data sets, we study and illustrate the flexibility of the new distribution. Our studies shows that the GKME distribution is a promising model for a large variety of lifetime data in medical and reliability areas. These are my references. Thank you.
Thank you, Kavya.
Thank you.
It was a nice presentation.
Yeah.
So any queries from anyone? Okay, so we'll go to the next presenter. It's a paper jointly by Ms. Anita Kumari and Mr. Kapil Kumar, and I hope Ms. Anita Kumari will be presenting. Are you there, ma'am?
Yes, ma'am, I'm there.
Okay. So now I invite Ms. Anita Kumari to present the work on statistic inference on multi-component stress strength from progressively censored power-Lindley distribution lifetime model. So your 10 minutes has started, ma'am. Please present.
Is my screen visible, ma'am?
Yes, it is.
Okay. Good evening to all. I am Anita Kumari, research scholar. Hello.
Yes, you are audible also. Please continue.
I'm audible, ma'am?
Yes, you are. Please continue.
Okay, ma'am. So good evening, everyone. I am Anita Kumari, research scholar, Department of Statistics. I am here to present my research work entitled as Statistical Inference for Multi-Component Stress Systems from Progressively Censored Power Lindley Lifetime Model. Life testing. Hello.
Yes, ma'am. You can continue, Anita. It's okay. We are able to hear you.
Okay, ma'am. Actually, it's not moving.
No, yeah. Yes. I think you can use the down arrow key. Yes, we are seeing it.
The life testing experiments are very time consuming and costly in the nature. So we use censoring schemes in the life testing experiments, such as type 1 censoring, type 2 censoring, and progressive censoring. Type 1 censoring and type 2 censoring does not allow the removal of the units in between the experiment. So we use progressive type 2 censoring. The progressive type 2 censoring allows the removal of the units in between the experiment. And it becomes the cost effective in nature. Mathematically, we can describe progressive type 2 censoring such as, let's we assume that we put m units on a life testing experiment, then we will prefix the number of failures and the progressive schemes S1, S2, Sm, and we will remove at the time of first failure S1 live units. Similarly, at the time of second failure, we will remove S2 live units, and the similar pattern follows up to the mth failure, and we will get the m failures. Sorry, we will get the m failures with the progressive censoring scheme. A system which components more than one, a system which contains more than one component called the multi-component system. A multi-component system is applicable in various real-life situations, such as if we have an automobile engine with 8 cylinders, then the engine will work until the 4 cylinders work. This system is known as 4 out of 8 system. Mathematical description of the multi-component stress strength reliability is given by Bhattacharya and Johnson in 1974, and it is given as probability at least U out of V items exceeds the stress Z, and the mathematical form is shown in equation 1. We have taken the power-Lindley model here for our study. The PDF and CDF of our power-Lindley model is given in equation 2 and equation 3, and with the help of the PDF and CDF, we will calculate the multi-component stress strength reliability, which is given in the form of psi UV. Now we estimate the psi UV with the help of maximum likelihood estimation method. Here we assume that we put m items on a life testing experiment, then with the help of the censoring scheme V, S1, S2, SV, from a power-Lindley distribution, we get a sample such as Y1, Y11 to YMV, and a stress component Z1, Z2, Zm. Then we have a likelihood equation using the progressive censoring given in equation 4. Then we use the PDF and CDF of the power-Lindley distribution. So we get the likelihood equation in the form of the following equation. Taking the logarithm of the above equation, we get the log likelihood equation. And to calculate the maximum likelihood estimates of the unknown parameters delta 1, delta 2, and gamma, we differentiate this log likelihood equation with respect to the parameters respectively. These are the 3 normal equations obtained respectively. Now, using the invariance property of maximum likelihood estimates, we calculate the maximum likelihood estimate of psi UV hat Also, we have constructed the asymptotic confidence intervals of the multi-component stress strength reliability psi UV using the delta method. The variance of the psi UV using delta method is obtained by variance of psi UV, where I phi is the observed Fisher information matrix. Using the above methods, we have constructed the asymptotic confidence interval of multi-component stress strength reliability, such as psi UV hat minus x alpha by 2 is multiplied by square root of the variance. Now now in the above asymptotic confidence interval, since psi UV is between 0 to 1, there may be some cases where we do not get an appropriate interval estimate. That is why we use the logic transformation suggested by Krishnamurthy and Lin in 2010. Here we assume that theta is log psi UV by 1 minus psi UV, and using this method we calculate the 100 into 1 minus alpha % asymptotic confidence interval of theta. Now also we have calculated the Bayes estimates of the psi UV. For calculating the Bayes estimates of psi UV, here we have used Lagrangian loss function introduced by Varian in 1975, and the Bayes estimate under Lagrangian loss function is given by neta beta hat. Now let us assume that our unknown parameters follows the prior densities as gamma with the hyperparameters A1, B1, A2, B2, and A3, B3 respectively. The joint prior distribution is given by equation 5. Using this joint prior distribution and the likelihood equation, here we get the joint posterior distribution in the following form. From this equation, we can see that we cannot calculate the Bayes estimates of the gamma delta 1 and delta 2 in the explicit form. That is why we use some iterative methods such as Tigne-Kadane's approximation. In 1986, Tigne and Kadane proposed a method to approximate the posterior mean. The approximation of the posterior mean is given by the following equation. Now, using some mathematical calculations, here we have calculated the estimate of psi UV using the Tigne-Kadane approximation in the following form. Also, we have used the MCMC techniques to calculate the Bayes estimate of the psi UV. Metropolis Hastings algorithm is used to generate the random numbers from the marginal posterior densities. These are the conditional marginal posterior densities of gamma, delta 1, and delta 2 respectively. These are the steps followed to use the MCMC technique. Now, this is the Bayes estimate of psi UV using MCMC techniques. Also, we have constructed the HPD credible interval, which comes out in the following form, where J is chosen in the following form. We have done a simulation study to compare the various estimates obtained in this above study. To compare the observations, we have used average bias and mean squared errors of the ML and Bayes estimates of psi UV. For the simulation study, we have taken the true values of the parameters 0.5, 0.75, and 1, and we have used two different prior values as non-informative prior and informative prior. These are some censoring schemes which we have used in this simulation study. Now, this is the table which shows the average bias and MSEs of ML and Bayes estimates of psi UV when U is equals to 1. These are the true values of the psi UV at these different censoring schemes. Now, from this table, we can see that as the sample size increases, the MSE decreases, and also the Bayes estimate in case of MCMC provides better estimates than the other estimates. This table shows the average length and coverage probability of the psi UV confidence and credible intervals of psi UV. From this table, we can see that when the sample size increases, we get the least average length, and also the HPD credible intervals provide better estimates than ACI, and at the time of informative prior, we get the better Bayes estimates. Now, these are the results which I have discussed with the tables. Also, we have done a real data analysis. Here we have taken a real data of monthly rainfall from Long Beach Airport, which was investigated in order to take the required suggested safeguards against a possible summer drought. This data set is also previously used by Mehto and Tripathi in 2020. To check the fitting of this data set, we have used Kolmogorov-Smirnov test and AD test. Also, we have compared this data set with the IERD distribution, that is inverted exponentiated Rayleigh distribution, because this data set is already used by MASCO using IERD. Now, from this table, we can see that our distribution fits better than the IERD distribution. Also, we have taken 3 different censoring schemes to use this data set under progressive censoring scheme. And these are the ML and Bayes estimates corresponding with their corresponding ACI and SPD credible intervals for different censoring schemes. In this research paper, we have constructed the multi-component stress strength reliability used under Power-Lindley model, and we have estimated the multi-component stress strength reliability using the classical and Bayesian methods. And also we have constructed the 95% ACI and HPD credible intervals. We have done a simulation study which tells us that the Bayesian estimates provide better estimates than the classical estimates, and we have also done a real data analysis for the illustrative purposes. These are the references. Thank you.
Thank you, Anita ma'am, for the wonderful presentation. So anyone, any queries?
Oh.
Actually, we are well ahead in time. Yeah, please
I
ask.
am unable to stop the sharing, ma'am.
You can just click the share button below your screen.
Actually, okay, here it is. Thank you, ma'am.
Okay, yeah, now it is gone.
Yes.
Okay. Now I think we have reached the last presenter in this contributory session. I think it's Rajesh Rajan. Mr. Rajesh Rajan, are you there? Rakesh Ranjan. Rakesh
Yeah,
Ranjan.
it's Rakesh Ranjan.
Yeah, sorry.
Okay.
So I would like to welcome Mr. Rakesh Ranjan to present his paper on Bayesian analysis of competing risk model with high dimensional covariates with an application to adenocarcinoma survival. So please.
Okay.
Mr.
Is
Rakesh.
my screen visible?
Yes, it is.
Yeah. Okay. So I am Rakesh Ranjan and I am assistant professor at DST Center for Interdisciplinary Mathematical Sciences, Institute of Science, Banaras University. The title of my presentation is Bayesian analysis of competing risk model with high dimensional covariate with an application to adenocarcinoma survival. So first I would like to define what is high dimension. So high dimension is where the number of observation is less than the number of parameters or number of covariates. So first I would like to explain background. Adenocarcinoma is one of the most common type of cancer affecting a lot of patients worldwide. Neither the risk of dying nor the response to treatment is not same for all the individual. A variety of factors, especially patient genetic makeup, can be held accountable for the differential. Using genomic data as covariate is an important strategy in the sense that they can help in obtaining individual level risk score prediction or prescribing the personalized medicine. However, high dimensional covariate space, when the number of observation is comparatively small, give rise to very typical situation statistically where most of the statistical estimates become unstable and non-unique. Patient detected with carcinoma could have already developed some other severe health conditions. As such, the situation may lead to competing risk scenario where carcinoma can be regarded as one of the risk factors. The next is the considered competing risk model. Let an individual eye is subjected to the competing cause of the specific hazard for jth cause can be given by this equation. Thus, overall survival can be given by the next equation. the effect of the covariate, here mainly the genomic data have on the survival time is represented by the Cox proportional hazard model. Thus, the specific hazard for jth cause can be given by this equation. We have assumed that if patient died followed by the relapse of disease, it can be coded as status 1. If the patient followed as a relapse-free died, it is coded as status 2. On the other hand, the patient who alive can be treated as censored observation. So the code 1 is for death due to relapse due to cancer, and code 2 is for death due to other causes. With this assumption, the likelihood can be written as the equation 4, equation below the point 4. Lifetime under each risk is assumed to follow either viable or exponential distribution, and thus a total 4 models is formed using the combination of these risks. These 4 models are exponential, viable, exponential, and viable. We have written the likelihood of viable model. It is given below the 0.5. Okay. So next is since the maximum likelihood estimate cannot be found for high dimensional data, we have directly gone for Bayesian formulation. So for Bayesian formulation, first we need to consider prior. So for shape parameters and scale parameters eta 1, eta 2, and kappa 1, kappa 2, we have considered gamma prior. Prior distribution for covariates are assumed to p-variate normal distribution. It is basically a multivariate normal distribution with mean vector 0 and variance covariance matrix D1 and D2. The resulting posterior can be given by this equation. Okay. Next, since the above posterior cannot be found in closed form, so we have used Metropolis algorithm for posterior for Bayesian computation. So we have basically draw sample from this posterior using Metropolis algorithm, and one can refer to Gelfand and Smith for more details. Okay, next is real data analysis. So we have considered a data set from gene expression omnibus site, and this is the link of the data set, and data set contain 432 lung adenocarcinoma patient, and the data set contain 22,283 covariates. So we have conducted a 2-step variable selection process, first through lasso list absolute shrinkage and selection operator, and then other by Metropolis algorithm. We have actually run lasso algorithm on 22,283 regressor and found 400 are significant. Next, we have used Metropolis algorithm with multivariate normal kernel as proposal density. In final Bayesian analysis, the mean vector of normal kernel is estimated using ML estimate and variance covariance matrix by Hessian based approximation at the ML estimates. And these are some results. We have selected finally 14 genes, and these are the list of genes that affect the lung adenocarcinoma. The posterior are studied using Metropolis algorithm carried out by considering only one cause at a time and by treating death due to other cause as censored observation. The mean vector, it is very natural. The mean vector of the multivariate normal kernel is approximated by ML estimates and the variance covariance matrix by the Hessian. And we have also calculated mean, median, and mode and highest posterior density intervals of the for the covariates, but we have not put it here because of the space restriction. Okay, because there are too many covariates, that's why we have not put the result. And our main obviously our main interest is the selection of gene, so we have put the selected selected gene in this slide. And finally, the various entertained models are compared. We have compared exponential, viable, exponential, and viable model using two important measures of model comparison. These measures are AIC and DIC. So, and these are the result, and one can see the viable model is the best among the others, and because this model has the less value of DIC than all others. Okay, next is the main objective in next is conclusion. The main objective includes determining the deriving gene that are affecting the probability of survival of a patient having adenocarcinoma at present as a clinical history. Additionally, it may be kept in mind that patients who pass away can die due to other cause, creating a situation that can be treated under competing risk. Our analysis based on all the 4 considered models reveals that the gene APOE, this is the name of gene, is most potent, followed by PDE12, RAD23B, APC, SYNE1, and DOK2. Besides age, besides the gene, age is also a vital factor affecting the patient's survival. Another significant conclusion is that both the model selection criteria uniformly favors this is a typographical error, viable model. Okay, so this is a list of references, and this is all about my presentation. So over to you, ma'am.
Thank you, Dr. Rakesh Ranjan. Any queries? Okay, so I think we have reached the end of this contributory session. I would like to see whether any of the presenters who were not there when I called their name, have any of them joined? If you have joined, you can have your time now. Have any of them joined?
Hello, excuse me, ma'am.
Yes.
Ma'am, actually, when I was registering, there was some mistake, and that is why I have written my title something mistakenly. I have written it wrong. Can I change my title so that I can get the right title on the certificate?
Okay. The title of your presentation is wrong.
Yes, ma'am. In the registration time, I have written it wrong.
I would like to request the coordinators to please answer her question.
Hello.
So, Anita ma'am. Hello.
Yes.
Anita ma'am.
Yes.
You can send your registration number along with your title, so that we can change it and send it to you, ma'am, on the certificate.
Okay, on the HOD mail I should send it, or somewhere else?
Yes. Both the mails you can send it.
Okay, ma'am. Thank you.
Okay. So thank you. I would like to thank all the presenters of the day for presenting such wonderful papers. I would also like to thank ISPS for giving me the executive members as well as the coordinators of the conference for giving me this wonderful opportunity. So thank you all once again. Good evening.
Good evening, madam. Thank you, Subha Nair, madam. for chairing this session. Thank you, ma'am.
Thank you.
Thank you.
Thank you.
Thank you, one and all.